at scale. And as we'll see, at the same time, some of the fundamental computational methods and theoretical tools have really matured. So, not only are we able to compute dramatically more interesting things at dramatically more interesting scales, but increasingly we have available to us tools for understanding when and why that will succeed. And the quest to sort of understand how these tools can guide the design of deep networks, how they can sort of help us to choose the right network components, the right training algorithms, and how we can use them to understand not only how to train large networks on huge data, but how to maybe minimize the size of the network, minimize the data cost, the computational cost, the energy cost, is going to be a theme for this tutorial and for this workshop. Okay, so, again, quest for low dimensionality in signals has very old roots: statistics, neuroscience, signal processing. What's sort of new and exciting here is our ability to do this with very large, potentially nonlinear models at very large scales. And so this new context of really big data and really potentially complex models raises some questions. And so these are kind of motivating questions for this sequence of tutorials and for the workshop. One very basic one is, how do we know we're computing the right thing, right? So when we talk about computing with various types of low dimensional structure, we want to find a sparse vector. We want to fit a subspace to data. How do we know we've got the right vector? How do we know we've got the right subspace? So how do we know we compute the right thing? Okay, so that's a kind of basic issue. At least as important, if we're talking about large data, is how we make sure that we compute that correct thing efficiently. And for us, this is going to be largely about understanding the structure and solution of optimization problems, right? We're very familiar, if we're working, either in classical signal processing or in deep learning, with the notion of fitting models to data, right? Almost everything we do boils down to optimization. Also, as we go through the tutorials, we'll see that in some situations, we can actually interpret our data processing strategies as solving optimization problems. So in my deep network, my sequence of layers actually corresponds in some sense to iterations of an optimization method. And so this really puts a premium on understanding the structure of optimization problems that we can solve, right? Because we know that optimization in general is impossible, especially in the context of fitting deep networks and learning models from data. Usually the optimization problems we encounter are non-convex. And so understanding what are non-convex structures that we can work with, when can we efficiently fit these nonlinear kind of compound hierarchical models is going to be a theme. And this is going to be a major theme for the second lecture. So the second lecture is going to be all about both structurally and computationally, what are non-convex optimization problems that we can solve efficiently in a strong sense. Okay, so motivation 1 is correctness. Motivation 2 is efficiency. Then, in addition to computational efficiency, if we're talking about large, flexible models, we have to think a lot about resource efficiency, right? A lot of the value of low-dimensional structure in problems and data sets and in models is that it allows us both to quantify what is the minimum for my problem, right? How much network do I need? How much data do I need? How much compute do I need? And can I guarantee that I'm hitting that minimum? And I think, as folks will argue across the tutorial and across the workshop, this is becoming an increasingly important direction, right? Our practice of deep learning over the past, say, 10 or so years has been largely driven by scale, right? More data, more compute, more model. But as we start to run into barriers associated with that scaling, it's becoming increasingly important that we figure out what is the minimum? What's the minimum network? What's the minimum data? What's the minimum compute? And so understanding how architectures interact with problem and data structure is going to be a theme. In particular, this is really going to be the motivation for lectures 3 and 4 of this tutorial, where we sort of try to look both in a kind of input-output perspective, and then look at the features in a deep network that are learned and see how those adapt to structure and data. Then in lecture 5, we're going to see how we can leverage that to design deep networks that are effective for particular data structures. Okay, so our third motivation is efficiency. Then a fourth motivation, which we'll see a lot of in this talk, and then in a few of the future lectures, is robustness, right? As we mentioned earlier, increasingly our data are not curated for a particular task. Rather, they're kind of uncontrolled. And so we need some way of coping with errors, with outliers, with missing data. And here, again, what we'd like to argue across the sequence of tutorials is that low-dimensional structure plays a critical dual role in robustness. If I talk about correcting for a certain type of error, say in the image at the top of the slide, I have an occlusion. Well, if I want to compensate for that error, if I want to perform recognition despite occlusion, if I want to cope with noise, with missingness, I need to leverage two types of structure. One is the structure of the clean signals, right? If the clean signals are not structured, then there's no way that I can distinguish an error from a legitimate signal. The other type of structure is the structure of the errors themselves. As we'll see, missingness, occlusion, corruption actually do have specific low-dimensional structure associated with them. And it's really by leveraging these two complementary forms of structure that we can have robustness in a strong sense. Okay, so our fourth motivator here is robustness. And maybe the fifth, which is a little bit specific to computer vision applications, but shows up in other guises, for example, in applications with physical data, audio, et cetera, is invariance, right? How do I make sure that my network architectures are invariant to the things that they should be invariant to? Here, looking at the particular example of invariance to visual transformations, say to image rotation and scale. And this is one of those kind of recurring issues where, when we design or learn deep networks, there's always going to be some component of this process that is data-driven, right? I need data to tell me what that set of clean signals or untransformed signals looks like. At the same time, there are certain nuisances that we know ahead of time will be present. And so how do we make sure that we are handling those in a principled fashion? How do we make sure that we have uniform performance across all legal perturbations of my input? Okay, and so again, this boils down to leveraging two complementary types of structure. One is structure in the clean signals. The other is structure in the allowable transformations. And here, this structure is going to be a particular type of nonlinear structure, right? If I think about transforming an object in an image, in the image space, this actually ends up cutting out a low-dimensional manifold. And so in this particular setting of invariance, we're sort of asking, how do we compute correctly with data with manifold structure? Okay, so that's kind of a mouthful, right? We have at least 5, what I would argue, pretty important motivations for looking at low-dimensional models and their interactions with deep networks. We're going to kind of walk through this at a somewhat leisurely pace across the 7 tutorial lectures. Again, the goal of this lecture is just to introduce a few of the basic models. We'll talk a little bit about sparse and low rank models and how they can be combined in interesting ways. Then in the next lecture, we'll talk about computation, in particular, non-convex optimization for low dimensional models. Then lectures 3 through 5 will look at interactions between deep learning and low dimensional structure. Again, how we can use low dimensionality to understand how generic deep networks train and how we can use it to design effective networks for tasks. And then lectures 6 and 7, you can kind of see as a deep dive both into how we design efficient networks and how we leverage connections between deep networks and inverse problems to build highly effective networks for tasks and imaging. So this is kind of the plan for the tutorial. For the first few lectures, one resource that's available is this book, which is joint with E, who introduced the talk. This is high dimensional data analysis with low dimensional models. If you'd like to learn more about some of the things that you're seeing across the tutorial, you can feel free to take a look at the book. And if you manage to grab a copy of the slides or just throw this into Google, there's a pre-production copy that you can take a look at that has all of the models that we'll talk about today. So this you can almost see as a kind of text for the tutorial and then some. Okay, so we have about 30 minutes remaining in this first lecture. And so, what we've done up to this point is more or less to set the stage. We've talked about some ways in which we would like to leverage structure in data sets and ways in which that might interact with deep learning. We've also talked a little bit about history of low dimensional models, just the fact that this notion of low dimensionality shows up in many different fields and has a very rich history associated with it. What I'd like to do next is dive into just a couple of fundamental low dimensional models. These are probably familiar to a lot of you in the audience. But if not, we'll try to just give a high-level introduction to a few models that we'll see throughout the day and throughout the workshop. Probably the most basic and most fundamental low-dimensional model is what we would call a sparse model. The notion of sparsity is just to say that a signal of interest has only a few important components. Formally, we'll say that a signal X, here we're visualizing it as a vector, is sparse if it has only a few non-zero entries. And of course, then a very important question is, what do you mean by a few, right? So we'll quantify that as we go, right? In general, we would like to be able to cope with vectors that are as complex as possible. But when we have some notion of sparsity in the problem, that's when we can really get away with estimation with limited statistical resources, limited computational resources. So sparsity, as we'll see, is going to be a structure that we're able to leverage again and again to do things that would not be possible with generic signals. Okay, so basic definition, vector is sparse if it has only a few non-zero entries. And probably the most fundamental problem associated with sparse vectors is this problem of recovering a sparse vector, here we're calling it X, from a few linear measurements, right? So here written as a matrix equation, Y equals AX. Now, of course, at least on the surface, this looks very simple compared to what we do these days in deep learning, right? This is in some sense, a shallow model, right? We just have a linear system of equations. And what we would like to do in this linear system of equations is go from Y to X using the structure of X. The thing that makes this a little bit challenging and actually quite beautiful and interesting is that in most modern applications, the systems of equations that we encounter are actually underdetermined. We typically have fewer observations than we have unknowns in X. And so, as we'll see, it's going to be really critical that we leverage low dimensional structure in X. If we know that X is sparse, then we'll actually be able to make some progress. Whereas for generic vector, we simply don't have enough information. Okay, so where does this sparse recovery problem show up? Well, we mentioned that one historical source of sparse models is neuroscience. Here, this is a kind of cartoon neuroscience problem, a sparse deconvolution problem. So I have an observation which consists of spiking patterns that are the result of multiple neurons firing. So every time a neuron fires, I have some characteristic pattern. What I see is a superposition of those patterns stamped down every time I have a firing event, plus noise. And so here, the sparsity in this model is a sparsity of the firing events, that it's only at particular times that I have a neuron that spikes. So here, my X, my sparse vector that I would like to recover, is this spike train that tells me when the neuron is firing. My Y, the observation, is the convolution of that thing with the firing pattern. I want to go from Y to X. And so this is just one example of how these kind of low-dimensional models, sparse models, show up very naturally from the physical structure of data. And one nice thing about this area is that once you sort of understand those basic tools, you start to see the same models showing up in a lot of different places. So at top, we have this sparse model for neural spikes. In the middle, we have a sparse model for microscopy data. And here, this is coming from a completely different application in material science, where folks are trying to understand high temperature superconductivity. And for our purposes, the thing to notice here is that actually this microscopy data follows exactly the same sparse model, but now in 2 dimensions. For neural spikes, my sparse model was I have my spike pattern stamped down every time I have a spiking event. For microscopy, my sparse model is that I have these kind of characteristic motifs in my data set, here corresponding to this kind of 8-looking pattern that you see in the middle of the slide. And my observation is a superposition of those things stamped down at different locations. My data analysis task is to find potentially the locations and maybe also that pattern. So anytime we're finding motifs in data, we're kind of looking at some kind of a sparse model. Okay, so this is one source of sparsity. I can get sparsity from the physical structure of data sets, especially data sets that consist of multiple motifs. Another really natural source of sparsity that we kind of alluded to earlier shows up in error correction. So here, this is a kind of cartoon example from some older work on face recognition, right? Not state of the art right now, but kind of cleanly illustrates a few concepts. So here, this is setting up an image recognition problem as a kind of regression problem, where what I'm trying to do is to take my given observation, here that's this corrupted image at left, and express it as a superposition of some things that I've seen before, this sort of training data set in the middle, plus an error, which here is capturing occlusion at top and corruption at bottom. And I like this example because it kind of illustrates how sparse structure actually can show up in 2 different places when we go to compute with unreliable data. We have a form of sparsity in recognition here, just in the sense that we're trying to pick out one or a few pictures from a big data set that can explain this observation. For those of you who like to play with classification in deep networks, you'll notice this same kind of sparsity in a one-hot class encoding, right? There's a kind of sparsity from the fact that only one class is relevant to this image. And there's a form of sparsity that shows up in both occlusion and corruption. Occlusion, for example, can be very large in magnitude, right? If I cover this part of my face, those pixels are completely changed. On the other hand, only a few of the pixels are affected, right? There are some fraction of the pixels that remain clean. So we do well in this situation to model this error as large but sparse, right? We can't trust some of our observations, but it's only a fraction of them that are wrong. So this is an example of sparsity both in the signal and in the error. Okay, and this is just some examples of recognition by solving regression problems. I see there was a chat and then it disappeared. Okay. Okay. So this is just some kind of toy example of that, basically showing that if we have the right model and the right computation, then we can do quite good error correction by leveraging structure of the error. Okay, so we've seen a couple of forms of sparsity. We saw sparsity from motifs in physical data. We saw sparsity in recognition problems, right, through the class encoding. We saw sparsity of errors, right, occlusion and corruption. Sometimes we can find sparsity not in the original signal domain, but if we go looking for it in an appropriate transform domain. So this is a kind of canonical and very important application of sort of classical sparse approximation and compressed sensing tools. This is in magnetic resonance imaging. So, here the imaging modality, the physical imaging modality is kind of complex, right? It involves putting you in this machine, subjecting you to a space and time varying magnetic field. This, sort of creates an RF signal, which we can measure. And it turns out that that signal actually corresponds to coefficients of a Fourier transform of what is essentially the density of protons inside the subject. So, here, if we're trying to image inside this person's head, what we're getting is basically some entries of the two-dimensional Fourier transform of this picture of what's inside the brain. And so the inverse problem task here, which we'll see a lot in lecture 7 of the tutorial, is to go from those few Fourier coefficients, here few because you can't sit inside this machine for very long, to an accurate and high resolution image of what's inside the body, right? So it's basically like we want to hallucinate the entire picture from just a few coefficients of its Fourier transform. So this is a great example of how physical measurement constraints give us underdetermined problems. This is underdetermined as a system of equations because, again, I have just a few measurements and I have a very large number of unknowns. I have as many unknowns as I have image pixels. So to do anything here, we're really going to need to leverage structure of that image. Okay, and it turns out if you dig into the structure of these images, because they tend to be relatively smooth with a few sharp edges, these tend to be fairly compressible in a wavelet basis. So this is an example of even if I don't see sparsity on the surface in my problem, if I can represent my data in a compact way, if I can find an appropriate transformation of the data, I may find some sparse model under the surface. So here, the sparse model is sparsity in a wavelet domain. And that's something that I can leverage to reconstruct the picture from far fewer measurements, right? The way we would do it is by casting the sparse recovery problem as one of recovering those few important wavelet coefficients from these relatively few Fourier coefficients. So that becomes a linear system of equations. That's our underdetermined linear system. And what we're trying to do is to solve for those wavelet coefficients, that's our x, so that we can reconstruct the picture. Okay, so this is actually a very important and very practical kind of classical example of these tools. It also illustrates some of the challenge here, right? Because the structure of signals doesn't always present itself right at the surface for us to see, right? We may have to dig for the right representation. And so one very tempting idea is to actually let the data kind of speak for itself. So instead of needing to analytically define a good representation, maybe I can simply learn a concise model from data. So this is an example from image denoising. So here the data are patches of a noisy image. And what's being learned here is actually a kind of transformation, or more precisely, a dictionary, which can concisely represent those image patches. So what you see at right here are actually the patches of the dictionary. Basically, the way that that's found is by saying, find me an A such that this collection of patches, yi, can simultaneously be sparsely represented as superpositions of those basic atoms in A. So basically, look for a concise representation. And if we've done a good job of it, a good job of that, that representation should capture the actual structure of the signal. And in this example, what you see in the middle is actually a denoised image. So this is the result of just keeping the sparse representation in that learned dictionary. And so what you can see is that actually, yes, the random noise in the original picture is mostly incoherent with the structure. And so because of that, when we go to learn a concise model, we keep the structure and not the noise. So it illustrates some of the utility of low-dimensional models. And it also says that if we have enough data, we can kind of let the data tell us how to find the right model, right? There are a lot of things that we may not need to model analytically. Of course, then that presents us with sort of new computational and statistical problems, because then a question is, how do we know that we've learned the right model, right? Yes, we can take our method and throw it at data, but how do we know that what we get is the right thing? How do we know that the computation is reliable? How do we make it efficient? So this is going to be largely the topic of the second lecture in this tutorial. We'll see a lot about dictionary learning, low-rank modeling, and then some generalizations of them. And we'll see actually how we can get a handle on the structure of these problems, leverage it to understand what we're computing, and leverage it to compute efficiently. Okay, so this is sort of a third guise of sparsity, right? Sparsity shows up in transform domains, and we can, in essence, learn to make those transformations. We can learn good representations for signals. Okay, now, how do we actually leverage sparsity computationally? Well, to do that, we need to be a little bit more formal, right? We've been kind of cartoony so far. We need a formal notion of a formal measure of sparsity. And probably the most natural one is the number of non-zero entries. We say that a vector is sparse if it has only a few non-zero entries. We formalize this through the so-called L0 norm, which here is just the number of non-zero entries in the vector X. So we denote this norm of X0. And as an exercise, you can convince yourself that that L0 norm is actually mathematically not a norm, but it has some of the same properties. one way to understand the connection of sort of L0 norm and more familiar norms like the L2 norm or the L1 norm is through the unit ball associated with the norm. In particular, at the bottom of the slide, we can see the unit ball of the L infinity norm, that's a cube, the L2 norm, that's a sphere, the L1 norm, that's a kind of octahedron, that's an important one. And if we take an LP norm, that's the pth root of the sum of the pth powers, and we send P down from infinity to 1 and then beyond, this norm ball sort of shrinks in and becomes more and more tightly aligned with the coordinate axes. And if you think about sparsity, sparsity says that my vector x uses only a few of the coordinate axes, right? Because only a few of the coefficients are non-zero. So you can think about LP for small p as being kind of close to those coordinate axes and hence doing a good job of capturing sparsity. Of course, as we'll see, when p is less than 1, our so-called LP norm is actually not mathematically a norm. It's no longer a convex function. And so that poses some challenges for computation. So often we'll kind of be looking for a sweet spot where we have something that is good at picking out structure, but is also well suited to computation. In particular, often for practical computation, we like the L1 norm as a convex surrogate. Okay, but in any case, L0 norm is our way of measuring sparsity. And associated with it, we can define a computational principle where we say, okay, if I want a sparse representation, right, I have some data, I'm trying to represent it efficiently, or I have a few measurements, I'm trying to find a sparse thing that agrees with them, as in the MRI example. Well, one very sensible thing that we could try to do is to look out of all signals that agree with our observations, look for the sparsest one. Find the one that minimizes the number of non-zero entries. Okay, and it turns out that often that's a sensible thing to do. So we won't go into too much detail on the actual mathematical statements, but in essence, if our measurements are generic enough, then if we look for the sparsest thing that's consistent with the measurements, that actually will be the correct solution. And generically, the number of measurements that we need is just a little bit more than twice the number of non-zero entries in the vector that we're trying to reconstruct. So what this tells us at a high level is that actually sparsity is a pretty powerful property for regularizing ill-posed problems, right? If I think about it, if I think, for example, about this magnetic resonance reconstruction example, and I ask, what dictates the number of measurements that I need to take? Is it the number of pixels in the image that I'm trying to reconstruct? That would be the case if I didn't use structure. Or is it the number of important non-zero coefficients? Is it the number of large entries in this signal's representation? What these theoretical results tell us is that it's the latter, right? What dictates the number of measurements that I need to take, the amount of data that I need to see, is not the extrinsic dimension of that signal, but actually the intrinsic dimension, the number of non-zero entries. Okay, and so that says that actually sparsity is very valuable as a regularizer. That's why, as we saw in the examples, we work so hard to find it in naturally occurring problems. On the other hand, this search for the sparsest solution kind of runs us up against some computational challenges. In particular, In general, finding the sparsest solution efficiently is impossible, right? When I think about that sparse approximation problem, right, this says out of all signals that are consistent with my observations, find me the one with the fewest number of non-zero entries. Well, this is really asking me to sort of select a few things out of many. So if you imagine intuitively how you try to do that, if we didn't know anything about the area, we would just sort of say, okay, try all collections of 1 entry, 2 entries, 3 entries, right? There's kind of a combinatorial nature to this search. And unfortunately, or maybe fortunately, this notion of sparsity is so powerful that there are a number of combinatorial problems that are believed to be intractable, which can be reduced to it. So this is just showing a kind of theoretical computer science flavor example of this, which sort of shows the computational hardness of L0 minimization by reducing from a combinatorial problem that's some kind of a set cover problem. Okay, and so this, here for our purposes, we're not so focused on the details of this, but just to say that it's not enough for us to have an effective regularizer, an effective low-dimensional model. We also need to be able to compute with it. And what this says is that we can't directly compute with the L0 norm, right? We need some kind of a tractable surrogate. And so, classically, one effective way to do this is basically to look at the class of functions that I believe that I can optimize, which is often taken to be the convex functions, and then look for one that's a good approximation to the number of non-zero entries. And so the number of non-zero entries here, this is plotted in red as a function of a scalar. So along the x-axis, you have t, and then the red thing is the number of non-zero entries in t. And if I imagine that t is bounded between -1 and 1, and I ask, okay, find me the tightest convex lower bound for that number of non-zero entries, it turns out that that tightest convex lower bound is actually the L1 norm, the sum of the magnitudes of the entries. We can also sort of see this in terms of this figure at right with the norm balls, where we said that as p goes from infinity down towards 0, we get a sequence of geometric objects which get closer and closer to the coordinate axes. And p equals 1 is this kind of nice sweet spot where I have a convex body. I have kind of an octahedron, or, here in 2 dimensions, a diamond shape. So we're convex. That's good for computation. On the other hand, we're as close as possible to those coordinate axes. So maybe we're good for finding the sparse things. And one of the big surprises in this area is that although we can't recover all of the sparse things, right? We argued a few slides ago that that problem is hard in general. Actually, there is a fairly well-structured subset of them that we can find. And it turns out that often they're the ones that we're looking for. And basically, the intuition is that for solving systems of equations y equals ax, if a is nice, generic in some sense, then this L1 minimization, the thing that I actually can compute with, is capable of finding sparse solutions to this system as long as my number of observations in y is a little bit bigger than the number of non-zero entries in x. Here, not as small as twice as large, we have to pay a little bit more, but say the number of non-zero entries times the logarithm of the length of the vector. So this plot here is just sort of showing this. Here we're varying the complexity of the signal that we're trying to recover. And what we can see is that actually there's this sharp transition between always succeed. We always succeed when the target is structured. We always fail when it's unstructured. And so in some sense, this is good news, maybe even better than we could hope for, that although the worst case is hard, if our model is well motivated, if the target signal is structured, then we can get at it with tractable methods. And, this is, again, very classical and pertaining to a relatively simple data model, right? Linear system of equations. But this is a theme that we're going to see again and again throughout the lecture, throughout the tutorials, that structure makes computation possible and efficient. So structure is good for us statistically, and it's good for us computationally. Okay, and so there's a sort of beautiful geometry associated with this that basically explains why this is working. I won't go into it in too much detail, just to say that the fact that the L1 ball is pointy makes the L1 norm good at picking out sparse things, right? And it actually is what makes L1 well motivated in this setting compared to something like L2. Okay, and as we go to quantify this, then a little bit heavier theoretical machinery is required. In particular, the notion that we should have in mind is kind of a notion of isometry. What that means is that our measurements are preserving the structure. So here we have the sparse things. Those are the structured vectors that we would like to recover. And what we need to be able to efficiently recover them is that our measurements actually preserve their geometry in a particular sense. And this, again, is a theme that we'll see throughout the sequence of tutorials. In fact, when we get to deep networks, we'll see that a lot of what makes deep learning sort of work at the optimization level and what we can try to design for at the sort of individual component level is really preserving the structure of signals, right? We want to sort of make sure that things stably propagate up and down our network. So, here in this simpler setting of sparse approximation, we're really trying to preserve the structure of the sparse signals. When our measurements do that, then we can do a good job of going from the measurements back to that structured signal. Okay, so we won't talk much about the theory here, but just to say that all of this can be quantified and the mathematics associated with it is actually really beautiful. I personally learned a lot by learning this area. So it's a lot of fun. But I think what I'd like to do with the remaining maybe 3 minutes of this introductory talk is just sketch one generalization from sparse to low rank. So we talked a lot about sparse models. We saw that these show up in a lot of different physical scenarios. But sometimes we need other things. And so what I'd like to show in the next few slides is how this notion of sparsity generalizes very naturally from a single signal, that's the single vector X or a single image, to a batch of signals. And that batch of signals we're going to kind of represent as a matrix. Okay, and so for low rank modeling, there are really nice motivations in imaging, in collaborative filtering, recommender systems, so on and so forth. I don't have time to sketch them in too much detail, but hopefully the slides will be available, and you're also welcome to check out the book. But the point is that this is a very fundamental class of low-dimensional models, right? Modeling a collection of images a collection of user preferences as lying on a low-dimensional subspace. And it turns out that this is actually a kind of sparse model as well. So when we talk about low-rank models are sparse, not in terms of the entries of the matrix, but rather in terms of its singular values. So if I think about a matrix X and I think about its singular value decomposition, the rank is the number of non-zero singular values. And so my matrix X is low rank if and only if its singular values are sparse. And so that means that all of the same intuitions and even computational tools that we've alluded to over the past few slides can also be deployed in this setting. We can talk about recovering low-rank matrices from a few observations. We can develop good computational approaches. Again, understanding when our observations interact nicely with that low-rank structure is important theoretically. And this actually leads to very practical and sort of scalable and statistically principled approaches to a lot of different applied problems. Okay, so there's a kind of high-level message here, which is a parallelism between rank and sparsity, right? The workshop title is sparse and, I guess, sparse and low-dimensional deep neural networks. And so what this slide is kind of arguing is that actually sparse and low rank or low dimensional are sort of two instances of the same thing. They're both a form of sparsity. And it turns out that there are a number of very powerful generalizations of this. If we have sparse and low rank, we can look at things that are both sparse and low rank, have superpositions of this. We can model structured batches of signals and errors. This is especially applicable in video analysis, community detection, so on and so forth. We can talk about structured forms of sparsity, incorporating more and more signal structure. This is especially important in imaging, where there's structure on those wavelength coefficients, there's structure on the occlusion. This can be modeled in a kind of sparse model. As we talked about earlier, we can learn models from data. And finally, as we move forward through the lectures, we'll talk more and more about deep models for nonlinear low-dimensional structure. We'll see that some of the same themes, modeling structure, isometry, understanding propagation of information, understanding how many measurements we need, come back again and again as we try to do this. Okay, so with that, thank you very much for your patience with the remote talk and also your attention and attendance. I'm going to stop here. This is actually something like a 500-page story. So if you want the full version, you can feel free to check out the high-dimensional data analysis book that was alluded to earlier. Our next lecture is going to go into computation and modeling with non-convexity. So, moving in the direction of non-convex and eventually deep. And so with that said, thank you very much. If time permits, I'm happy to take any questions if folks have questions. And yeah, thank you. Okay, so there is one question in the Q&A, which is about the video being available afterwards. So maybe Ching, who's been doing a heroic job of organizing this would be the right one to answer that. Okay, I'm sorry, I can't hear the room audio at all. Are there any other questions? Okay. Well, I'm going to assume no because I'm not seeing it in the chat. And
John, do you hear me?
Yeah. Yeah, I can hear you. Yes.
Yes, the
Wonderful.
video will be available online. It's already being streamed live and will be available on demand.
Okay, wonderful. Thank you so much for making that possible.
All right.
Okay, great.
Thanks, John, for the wonderful talk.
All right, thank you.
Okay. Okay.
Okay. Hi, Ron. The second talk will from Yuqian Zhang from Radford University, and she will talk more about low-dimensional models for non-convex approach for low-dimensional models, and then we will progress towards deeper models later on. Thanks.
Okay, thank you, Jin, for the introduction. So I will keep talking about how do we try to leverage the low dimensionality in data models, and especially we're talking about non-convex approaches. And probably like in later portion of the previous talk, John has tried to do a lot of things where we try to use this as an L1 penalty to impose like sparsity and something like that. So basically, we have tried a lot to have like a convex optimization approach to solve low dimensionality problems. And in this talk, I will show you that for certain low dimensionality problems, because of the nonlinearity in the data model, we actually cannot do convex procedures. But the surprising and maybe the fortunate thing is that even if you try to approach with a non-convex procedure, which is assumed to be hard and NP hard, and we actually have a good solution for those problems, and we can show those low dimensional, we can solve those problems like with rather efficient algorithms. Okay, so that's kind of like the outline of the talk. So next, I will just start with a few examples John kind of mentioned in his previous talk. So the first one is the problem of the low-rank matrix completion. And we see this problem in a lot of machine learning problems and in computer vision problems. So this is a case where we have a matrix X, and this X is usually very big. So if you think about the Netflix problem, so this X could be a recommendation system, and this X is of the size of the number of users times the number of like movies on Netflix. Okay, and our observation is like a subset of the X because you only see like a subset of the rating from some users for some movies. And what we want to do is like we want to recover this original X. And so the convex approach to do that is that, okay, we are just going to try to make the X matches the Y on this support omega. And at the same time, I want this X to be sparse. To be low rank, I'm sorry. Okay. And as I mentioned, so this X could be very big. So think about like how big the Netflix data set is. So in general, if you try to solve this problem from a convex procedure, that could be very heavy computation. And the more practical approach people do is like, we just try to approach it from a non-convex procedure. Here, because I assume like my X is low rank, so I can write that matrix as a product of some matrix and U and V. So here U is a tall matrix and V is a fat one. So once you have like this this like reformulation of the original problems, instead of working on this original X, I'll try to work on the factorization U and V. So we are working with much smaller data set. Okay, so that's something efficient for our computation. And if I try to write down what's the corresponding optimization problem I want to solve, so what I want to do is I want to find a UV such that the product of UV is going to match my observation Y, and at the same time, I want this UV to be regularized. Okay, so here this term is for some numerical issues. So basically, we want the UV to be of the same size. Okay. So you can see that here the optimization variable we have is this UV, and this process is non-convex. And because here we have the product of UV, so this is a non-linear term, so the whole thing is non-convex. And another example we have is this example of dictionary learning. So this is where we have we have an image, and what we want to do is we want to find a dictionary A, such that this dictionary is going to give me a sparse representation, and so I can write my data as a product of A and X. Okay, so here you can see that the only thing we know is this data Y, and we want to automatically find this dictionary A that's going to render the best possible sparse X. Okay, so what shall we do with this? And you can see that the natural formulation is nonlinear again. We have two variables, A and X, and their product is going to be my data. So if I try to write down another optimization problem for this problem, so the formulation of this one is going to be non-convex. So far we seem to have run into a couple of issues. Basically all the problems we mentioned, and those problems are structured. Those problems have low dimensionality innate, but somehow the natural formulation is non-convex. And this is probably why we're afraid of non-convex problems. And this is a benign picture we all hope we can do with our optimization problems, where you have this benign shape such that you can start from any initialization and run a gradient descent algorithm or some other algorithm, and you can recover the best solution. But here, that's what's happening in the non-convex setting. So basically, we can see that there are so many possible local solutions. So depending on your choice of different initialization, and you're going to run into different local solutions. And most of the time, those local solutions has nothing to do with your ground truth. Okay, it sounds pretty pessimistic, but we do know, like, at the same time, we have like this dictionary learning problem, we have like this low-rank matrix completion problem, and we use the non-convex formulation to solve these problems all the time. So what's happening over here is that, okay, even if you think about these non-convex formulations, and even if we start from different initialization, it seems that we always run into a local solution with the same objective over here. So here I show you the result of a dictionary learning problem. I have the different image, and here I plot you like what's my objective value when I run the algorithm from different initialization. Okay, so every time, because my initialization is different, I should expect to run into a different local solution. And the surprising thing is that all these local solutions seem to obtain the same objective function. So actually what's happening in this non-convex optimization problem we mentioned earlier is that instead of dealing with the general case, we actually run into this small structure case. So where we have this non-convex optimization problem, but the good thing is that, okay, if you check out all these local solutions, they seem to have the same objective value. So that basically suggests that, even if we start from different initialization, we are going to run into some solution that give you the same optimality. Okay, so here I'm going to show you another example. This is an example of the sparse blended convolution problem. So this is an example where John mentioned a little bit. And so here we kind of have the same issue here. We have the data Y, and then I want to recover what's my A and my X, and I want my X to be sparse. So here, Y is generated by the convolution of A and X, which is again a nonlinear structure. And if we look at the solution of this problem, actually it's pretty surprising that if you look at every local solution of the sparse blended convolution, you actually see this beautiful structure in these local solutions. So here I have like basically what's the object value of this of the sparse blended convolution. And so this one is the ground truth I have, and this is one local solution I have. So you can see that the local solution is basically a shifted copy of this one. Okay, so basically what I do is like, okay, that's a ground truth, and my local solution is going to shift my ground truth to some like offset, but in different directions. So actually this structure is it holds true for all the local solution you can find in this sparse different convolution problem. And if we do something crazier, so if we do this convolutional dictionary learning problem, where my observation data y is the summation of the convolution of several pairs, here I want like A to be the Shaw motif and X to be the sparse signal. Okay, so, and here that's the observation y. I guess you probably cannot see anything. And this is basically one local solution we can recover. And you can see that the local solution here, although we have like much more complicated problem, but the local solution here still carries a big portion of the ground truth. The local solution still serves as a shift truncation of the ground truth over here. Oops. Okay. So far we mentioned like a lot of examples where we see that we see some problem which are naturally non-convex. But the good news is that every solution in those non-convex problems are structured. And next, we'll try to go deeper and see what's a challenge for a general non-convex problem, and what's lucky here, and what's the special thing that makes these non-convex problems like benign. Okay, so let's look at what's hard about general non-convex optimization problem. So if we just look at these two pictures illustrate like the two main challenges for non-convex optimization problem from a geometric perspective. So the first issue is like we shown in the first picture, there are so many spurious local solutions. So basically, depending on your initialization, you're going to run into different local solutions. And the local solutions might have nothing to do with your ground truth. And another geometric obstacle is basically the flat saddle points. And you can see that in this picture, we have a big region where we don't have any gradient. So which basically says that if my algorithm is initialized in that flat region, or at some point my algorithm runs into that region, we cannot escape that region with some gradient descent algorithm or other local search algorithm. So that's where non-convex problem could be hard. And fortunately, in the problems we encounter, we don't run into issues like that. And in the problems we mentioned earlier, and a common hallmark is that they all have certain kind of a symmetry in the data generation process, which is something I'm going to talk about in more detail. And once you have this symmetry, we can see that we actually run into this benign optimization of landscape. So this is kind of picture how this optimization landscape look like for the previous two problems. And so you see that so there's no flat saddle, and basically the local solution always have the same objective value. Okay. So next we'll look at what's the symmetries I mentioned in this problem so far. So if we think about the low-rank matrix recovery problem we mentioned, so basically we have some X, we want to write down X as a product of UV, and you know that if you squeeze in another matrix gamma, and if this gamma is invertible, so we can always say that this U gamma and V gamma inverse is going to be the same as a product of UV. So basically say that, okay, if I have some ground truth UV, I can always apply some invertible matrix gamma, such their observation is going to be the same. And for the dictionary learning problem, you can do something similar. And what do I do here is that if I have some ground truth A and X, and I'm going to apply some like sign permutation of the different rows and column of UV. So basically that's corresponding to you're going to give like different numbering or different ordering of the entries of your dictionary. Okay. So you can see that in these problems, because like how the data is generated, and we kind of run into this kind of symmetry. And similarly, we can see that in the blended convolution problem. So we write down the matrix, the observation Y as a convolution of AX. And because it's convolution, so you can shift the two signals into opposite directions, and they're going to give the same observation. So because of this symmetry property, this basically says that even if I have a ground truth, I can always apply this symmetry such that that's going to generate another pair of the ground truths. And they're going to give me like the same kind of optimality. Okay, so next what we'll do is like we'll see this, we'll see what's the common structure of the optimization landscape when we look at these problems with this kind of symmetry. So basically we are going to show two things. The first one is that if we look at the problem with this kind of symmetry, basically the local minimizers are symmetric copy of the ground truth. So the local solutions is going to be some like certain operation of the original ground truth. So maybe for dictionary learning, so the local solution is going to be the different combination of the ground truth. And for the Flint convolution, the local solution is going to be the shift of the ground truth. Okay. And the second thing we are going to observe is that in this kind of non-convex problems, basically any any critical point is going to be have some negative curvature in a direction that breaks symmetry. So we don't run into issues where we have like this flat saddle. Okay, so question? Yes. So basically because of this, the symmetric issues over here, because the data is generated by this model, so you can apply the different operation on the ground truth. That's going to be as good as the ground truth. Okay, no problem, thank you. Any other questions? Okay. Where we were, okay, we were here. Okay, next we'll just go back to a little bit of basic calculus of non-convex and convex optimization and try to build things up a little bit. Okay. So here I have like a simple plot of the difference between convex and non-convex optimization problems. And for non-convex problems, we know that that's good. And whenever we see a critical point where the gradient vanishes, that's basically a minimizer. But if you look at the non-convex function, the critical point is much more complicated. So here we see we have local solution and saddle point and global mean. Okay, so they're all critical points. And if we want to talk about the geometry of non-convex optimization problem, say if we want to tell the difference between a local solution and saddle point, we need to look at what's the second order derivative, because for all of them, the first order derivative is the same, they're all 0. Okay. So next we'll try to distinguish like different kind of a critical point. So here we have a non-critical point where the gradient is just non-zero. And next we have like the critical point where the gradient vanishes. And if we just look at the hashing, and if we try to see what's the eigenvalue or singular value of the hashing matrix look like, we can try to characterize the critical point into 3 categories. So one is a local minimizer or global minimizer. So those points are where the critical points has like positive hashing. And we have a saddle point where the eigenvalue of the hashing is kind of a mixture of the positive ones and negative ones. And we have the local the maximizer where this hashing is always curving down. Okay, and next we'll try to see why the problems we mentioned earlier have this good geometry that the local minimizers are always a symmetric version of the ground truth, and there's no critical point. There's no flat critical point. Okay, so first we'll look at the problems with like the rotational symmetries. So here I mentioned I have like 3 examples. Those are like eigenspace computation problems, generalized phase retrieval problem, and matrix recovery problem, as we mentioned earlier. And in all those problems, the data generating model or the data observation model is nonlinear, and you can always apply certain operation to the ground truth and generate another solution, which is as good as the ground truth. And next, we'll just take the example of this low-rank matrix recovery problem. And we'll try to work out the mask really quickly. And once you work out the math really quickly, you can see that the property we mentioned already actually holds. Okay, so this is the low rank matrix recovery problem. And we know like the convex formulation is that we want to recover this low rank X such that the observation is going to match, the X is going to match my observation. And the non-convex procedure is that I have my UV over here. They are like much smaller data matrix. And I want their product to match my observation. And I'm going to have some regularizer for UV. So next, we'll just look at some simple illustration, and we'll work with like a toy example and see how things work. Okay, as I mentioned earlier, so in this low rank matrix inquiry problem, so the inherent symmetry is that basically we can always find in this invertible matrix gamma in it, and if I apply this gamma and gamma U inverse for UV, and that's going to be as good as my ground truth. So next, I will just try to show is this gamma, is this like U0, U gamma and V gamma inverse are the local solutions. And we also need to show that there does not exist a flat stationary saddle point. Okay, so next we'll just look at a one toy example, because if we want to do it really quick, that's the only way we can move forward. So here I will just introduce a few simplifications. The first one is that assume like my Y is just my X. So basically I have the full axis of the matrix. And my second simplification is that I assume my X is a symmetric matrix and it's also rank 1. So in that case, I have my X is basically UU transpose, and I can also introduce like a minus in it. So here we kind of reduce the rotational symmetry to a sign symmetry. Next, if we just squeeze in like the non-convex formulation we kind of listed earlier, so basically we have like this new objective where I try to match this X to my UU transpose. So here X is the observation, and U is something we want to optimize. And we have the regularizer, but here because like my U is my V, so that thing is just a constant. Okay, so with this, just by ignoring the earlier, like the constant term, so we have this thing. And what we're going to do is like, we're going to find out all the stationary point, because we mentioned like the stationary point could be either a local solution or a flat set point or a saddle point. And if we want to tell anything about the geometry of the non-convex problem, we need to start with the stationary point. So here what I do is I just calculate the gradient of this function, and the calculation is simple. And if you trust the calculation here, so basically we can see that the only critical points are these two kinds. The first one is that my U is either my U0, which is the ground truth, or the negative of that. Or another case is that my U is 0. So that's all the stationary points in this non-convex problem. And if we want to see something further, we need to look at the second order derivative of this function. So we need to look at the hashing of this function. So I just do some further derivation. So I have this hashing calculator here, and next I will see what's the hashing look like. Okay, if I squeeze in U is either U or minus U, I have like UU transpose is going to be an X, and here my hashing is always positive semi-definite. So this basically says that this is a local solution. And the other scenario is there where I have my UA to be 0. And in that case, this hashing is going to be minus X. And recall that this X is symmetric, and that's UU transpose. So this is always a negative hashing matrix. Okay, so basically that says that the geometry of this problem looks something like that. So we have all this, so if you check out this red dot over here, that's going to correspond to all these local solutions, all the like different permuted version of the ground truth. And the only other non-stationary point is going to be a maximizer, which is the point in the middle over here. Okay. Any questions so far for this example? we'll see the other category, which are problems with discrete symmetry. So this is where we kind of have the ground truth, and we can apply some discrete symmetry to this ground truth. And that's going to generate another copy of the ground truth. And you can see that the distinction between this version and the earlier problem is that the local solutions here are kind of disjoint from each other. And that basically says, okay, if you try to convexify the problem or something, that's basically impossible. Okay, so the problem with discrete symmetries include the eigenvector computation problem, dictionary learning, tensor decomposition, and this blending convolution problem we mentioned earlier. So next, we'll just look at the dictionary learning problem. And so, So dictionary learning problem, recall that that's a problem where we have the data set Y, and what we want to do is we want to recover this dictionary A and this X, such that the Y is going to be the product of our A and X, and you want to make sure that your X is sparse. So here, that's the objective we have, function we have. And if you have noise, you can use a lasso formulation of that one thing. And the inherent symmetry, as we mentioned, is basically that you can insert some sign permutation matrix for this A and X. So you can permute the rows and the column of A and X. And that's going to give you the same representation. Okay, so in order to, so for this problem, I'm not going to show you the math because that's a little bit complicated. So I will talk about the simplification of this problem a little bit, and I will just state like what's the final result. Oh, and if you're interested in details, you can check the book John mentioned earlier. Okay, so here the simplification I'm going to introduce is that I'm going to suppose that my matrix, my dictionary A it's not like a general matrix. I'm going to assume like it's an orthogonal matrix. So in that case, I have like my A0 transpose is going to be an identity matrix, and my X is going to be sparse. So the good thing about this simplification is that once you assume like this A is orthogonal, and you can basically write this original X as A transpose AX, because this is identity, and this AX simply gives you the observation Y. So with this simplification, you basically can change this optimization formulation into this one. So this is easier for you to work on to work on the optimization problem. Okay, and any questions? Okay, and another simplification is that, okay, recall that here what I'm going to do is like, I'm going to assume like the A is orthogonal. So I want to do my optimization problem over the orthogonal group. And still that's going to be complicated because so every time you try to take a gradient descent or something, if you want to do that on the orthogonal group, you basically need to do SVD, and that's really heavy. And another approach to do that is that I can try to solve like for different rows of columns of A. So every time I don't need to solve the whole A, I can just try to solve one column of it. So what I do instead is like, okay, I'm going to just optimize over a vector. So I assume like this vector has a unit norm, kind of translate from that the A is orthogonal. And I'm going to, the objective I'm going to have is basically A transpose Y. And here I have the L1 norm, which penalizes the sparsity of these coefficients, because this is going to correspond to one row of X. Okay, so now here we know that, okay, what the optimal A will be is so if A is basically one column of the ground truth A, so that's going to pick up the one column of Y and one column of X, that's going to give me maximum sparsity. And if you work on math a little bit, and because the math is a little bit complicated, I didn't show it here. So if you work on math a little bit, you can see that if I choose my A to be either the positive or negative version of AI, so AI is any column of the ground truth A matrix A. So in that case, the hashing is going to be positive semi-definite. So that's it. This is a local solution. And in other case, we can see that all the other stationary points is going to be the superposition of this A. So here we just have like A is just AI, and here we have like this is going to be a superposition of multiple of them. And once you check the hashing for those points, you can show that there actually exists a negative curvature that's going to break out like the evenness at a stationary point. So basically, that gives us such a geometry. So here we have this. All the local solutions shown up here, and that's going to correspond to 3 different AIs. And we also have the negative version of it. And here you can see that we have all these local solutions are plotted as these red dots. And the stationary point is somehow kind of like in the middle of them, because that's corresponding to the superposition of like, because the stationary point is going to be the superposition of like a few copies of them. So basically, you are going to find all the superposition like in the middle of this, the local solutions. And obviously, you can see that there is going to be a negative curvature that breaks the symmetry between them. Okay. So next, we'll look at the problem of the short and sparse blend deconvolution. And so the problem is going to get more and more complicated. So I'm going to show you less and less math, just show you more pictures. Okay, so this is a blend deconvolution problem we mentioned earlier. And we have the observation Y. We want to recover A and X. And because it's a convolution, so we know that we can shift the 2 signals into opposite directions for the same offset. And we know that this copy is as good as this copy because they have the same convolution. And the shifted signal, the shifted sparse signal is still sparse. So so apparently this is a non-convex problem. And if you think about like an intuitive objective function you want to write on, it's probably this last one. So what you want to do is you want to make sure that your A and X is going to match my Y. I'm going to penalize with the Frobenius norm. And at the same time, I want my X to be sparse. Okay, so that's what we look at over here. And basically, this is going to be what such geometry look like. So here, what I'm looking at is basically what happens around one shift of the ground truth. And you can see that we always have this bowl shift thing. So we have like around any shift, we have like this local geometry, which show that any one shift is going to be a local solution of this problem. And next, we'll look at what happens if we look at like the linear span between 2 shifts. So here I have one shift and that's another one. And we know that either one of them is going to be a local solution, like we see in this slide. And if you look at like the subspace between them, and we'll have this geometry which are kind of like that. Okay, so here what I'm plotting is the subspace connecting these 2 local shifts. And we'll see that each shift is going to be the local solution. And you can see that we kind of have like this thing on the span of them. And in the middle of them, that's going to be the saddle point. And you can see there is a negative curvature that's going to separate them apart. Okay, so that's what happens between like 2 shifts. And if you just try to fight with the math a little bit more, you can see that that's going to work on the subspace between multiple shifts. So here I have the 3 shifts, but so every shift is going to be a local solution. And if you look at what's happened over here, like over the connection between these 2 shifts, we see a saddle points over there, and we also see a saddle point over here. Okay. So basically with the problem so far, we can see that for those problems we mentioned earlier, we see that this inherent symmetry in the data generation model, such that even if you don't have the ground truth, you can always apply some operation on the ground truth. And you can generate another pair of ground truths, which is as good as your ground truth is. So this this is going to lead to the non-convexity of the problem. But the fortunate thing is like the local minimizers are actually the symmetrical version of the ground truth. So like in this example, okay, I have this non-convex problem, but the local solutions I care about are always a symmetric copy of the ground truth. And another property is that we can always find this negative curvatures that in direction that's going to break the symmetry. So like we see in this point over here, that's going to be a set of points, and you can move away to any local solution just by moving from this set of point a little bit. Okay, any questions so far? Okay, so last we'll talk about the computation a little bit. And so far we have seen that we do see a lot of like problems where we see this low dimensionality in the data generation process, or the low dimensionality in the data observation process. And the fortunate thing is that if you cook up like the natural non-convex optimization for these problems, they actually have a pretty benign shape, such that either the local solution are always a symmetric copy of the ground truth, and secondly, there's a negative curvature in direction that breaks the symmetry. So next we will see like what kind of algorithm do we need if we want to be guaranteed that we can run into one of these local solutions. So in general, if you want to find a problem if you find a local minimizer in this non-convex optimization problem, this is NP hard. And we'll see that because of the problem we mentioned earlier, they have this symmetry, and actually this problem will become much easier for us to solve. Okay. So basically, if you look at all the problems we mentioned so far, we call that in all the problems we mentioned so far, the critical points are always regular. So basically by regular, I mean that if I look at the hashing of them, I can pretty much tell what's happening over there. So if I run into a critical point, so all I need to do is I look at the hashing, and then I know where's the next direction to go. So you can imagine that if you have a flat saddle point, and even if I have like I can have the gradient to be 0, and I can also have the hashing to be 0. So in that case, you need to look at higher orders, and that's where the algorithm becomes less efficient. But in the problem we mentioned so far, so you don't need to look at higher orders. All you need to do is like you need to look at the hashing, and then you can look at what's the direction that's going to break the symmetry. Okay, so this also says like what kind of algorithm we want to deal with this issue. So basically the key issue is that in all the problems we mentioned, the set of points can be distinguished by looking at the hashes. So when we try to design an algorithm, we just need to find an algorithm that's going to find the negative curvature in the hashing, right? So we can run our gradient descent algorithm or whatever your favorite algorithm. So that's going to run into a set of points where the gradient vanishes. And now next you need to decide which direction I want to go to break the symmetry. And because of the properties we mentioned earlier, so next what we need to do is like we need to find the negative directions such that I can escape these saddles. So all we need to do is like we need to make use of the hashing in these saddle points. Okay, so here I'm going to mention like a few algorithms, and so we have some polynomial algorithms. So we have like this trust region algorithm, curved linear search algorithm. So what they do is like so when you design an algorithm, you not only take account of the gradient, you also consider the hashing to terminate. And it's kind of like you have the higher order approximation of the hash of the function based on the gradient and hashing, and then you try to decide what's the next step to move. And another way to escape the saddle is also kind of intuitive. So what you do is like you do this noisy or stochastic gradient descent. So just think about, because of like we are going to inject noise or inject some stochastic in our gradient search algorithm. So if you're stuck at a saddle point, so where the gradient vanishes, because you have some noise in all stochastic in this gradient estimation. You are going to choose some direction to go, right? Because, okay, if you are stuck at saddle, if you just look at a saddle, if you just look at the gradient is 0. But because you're adding some noise, so with high probability, you are going to choose a direction to move forward. Okay. And so that's the algorithm. We can show that they're polynomial, and they're actually pretty efficient. But there's actually another thing I do want to mention is that, so although there are so many algorithms which are guaranteed to escape the saddle points, but actually in practice, what we do for this dictionary learning problem or blended conclusion problem, we just use gradient descent. We don't even consider the hashing. And this picture basically says that why that's the case. So if you think about what's the worst case scenario for non-convex problem, so that's where you are going to have a different saddle points, and if you go from once you leave one saddle point, you are going to run into another saddle point. So if you are going to visit all the possible saddle points, so that's where the algorithm could be slow. However, that's not the case in the problem we encounter. So if you think the natural occurring problem is that, okay, it seems like there are not so many pessimistic situations where you have saddles lead into saddle. So what's happening over here is you just escape the saddle and you run into local solutions. And this can be explained in this picture. So here I have two non-convex problems. And you can see that this basically plot two saddle points. And I have the red dot, which basically represents a slow region. So this is where the gradient becomes small, and the gradient descent algorithm is going to be slow in that region. And you have this green line, which is stable manifold associated with the saddle point. So you can see that if my algorithm falls on this green line, if I follow the gradient descent algorithm, it's just going to it's going to move along this green line and fall into my red region, right? And what's the difference between these two pictures is that you can clearly see that we have okay, so how do I say? Okay, so if you look at this gradient along this green line, so the gradient is going to approximately orthogonal to this green line. So that basically means, okay, if I fall exactly on the green line, I'm going to be super slow and fall into my region. But with high probability, it's not going to be fall on exactly the green line. And once it's not on the green line, it's going to move orthogonal to the green line. So that's where you can get the efficient speed to escape the stable manifold. And the counterexample is this one. So you can see that, so if you just look at the point over here, the gradient of this picture is probably parallel to the green line. So that basically says that if my algorithm falls into this black region, so that's where all of them is going to collapse to this red dot. So that's where the gradient is going to vanish. Okay. So basically, this is a picture we can show that for dictionary learning problem. And so this is basically, I try to redraw this picture on the dictionary learning example. If you check out what's the geometry in dictionary learning example, you can see that they basically have the shape of this geometry over here. So basically, okay, you have the stable manifold, but the lucky thing is that most of them, the gradient along this stable manifold is going to be orthogonal to it, such that it's going to escape from the stable manifold efficiently. Okay, any questions? Okay, so basically that's, Okay, so basically that's the reason like why even if we have like all these saddle points, we are supposed to check the local. We are supposed to check the hashing. So actually, we don't need to do that. We can just run our gradient descent algorithm, and because of this dispersive structure, the algorithms can just escape from this stable manifold automatically. Okay, I think I kind of like went a little bit too fast. So basically, let's come to the conclusion. So far we can see that for the problem we mentioned, so the problems where we try to leverage this low dimensionality in our data recovery problem, we have like this natural symmetry such that because the data is constructed in a nonlinear way, you can always apply, sorry, this is some backup slides, I guess. You can always try to apply some operation on the ground truth and generate another equivalent good ground truth. And because of that symmetry, it makes your problem non-convex. But the thing is, like, if you look at this geometry a little bit, if you try to calculate the gradient hashing a little bit, you can see that those local solutions are just the ground truth, the perfect solution you want. And you can see the saddle points kind of in the middle of them. And if you trace where the hashing goes, it just leads you to the ground truth. Okay. And because of this issue we mentioned, we have like a very efficient algorithm. We can show that the gradient descent always work. And even for the worst case scenarios, we can find some polynomial time which leverages the second order information. So that's going to close my talk today. So I would welcome any questions if there are any. Question? Mm-hmm.
There's several examples of benign geometry, right, where you have this non-convex, sparse low-rank problems. But do you have a general statement, like if you have like something like a two-layer neural network with some structure, some symmetry, is this possible to say that that problem will have benign geometry, or is it just for specific examples?
So the problem is like if I have a more general non-convex problem, like the two-layer neural network, that's probably
you hear all those problems have like two linear layers and some structure, right? The L1 or some other type of convex regularization. So in general, can you say something those problems, or if you have some symmetry, this will have benign geometry, or just for those specific problems?
Okay, that's a pretty good problem. So actually, I do look at a few like matrix type of factorization problem, but I look at matrix factorization problem with different prayers, like the low rank or dictionary learning, but there are other prayers like clustering. You can also see that's a matrix factorization problem, or an NMF. And I can see that for the problem I have seen so far, that seems to be true. And I do see some work on one-layer neural network, and we probably talk about that in the last time. So one-layer neural network, and they show that basically all the local solution is going to capture a large portion of the ground truth. And this is probably something some personal perspective. I feel like in general, if you look at this non-convex problem, the local solution is not always the ground truth. But the fortunate thing is like they always carries a large portion of the ground truth, at least in some matrix factorization problems.
Okay, thank you.
Sure.
For the two-layer network, there's a lot of work. Actually, that's the case under very benign conditions that you can show the same thing and generalize. In fact, the matrix factorization you can think about is kind of like a two-layer network. And also, in fact, the neural networks with some structures, especially with your minimizing the cross-entropy object function, it's already shown. I think the work of Mert, Planchi, or Stanford, right? I mean, in fact, it's even easier. Each per layer-wise, you can reduce to convex optimization. Even the convex optimization gives you the globally optimal solution, right? So in fact, in many cases, depending on the object function, depending on the structure of your network, the problem is actually even simpler, to ensure in terms of ensuring optimality than the matrix factorization problems here.
But those are infinite dimensional spaces. But those are infinite dimensional spaces for neural networks.
No, finite. Everything's finite. Yeah. Like Meta Planch's work, right? They show, all the network can layer by layer. You can just relax to convex optimization, and that give you exactly the optimal solutions, right?
I can also add something to Daniel's and Yi's comments. So recently we started some like a neural collapse phenomenon. And I think in the afternoon, Zhihui will talk about this, and he will show that if you study neural network under unconstrained feature models, you can show this kind of benign global landscape, that the global solutions are the neural collapse solutions that don't know how to discover like 2 years ago. I think Zhihui will talk more on this in the first talk of this afternoon. So yeah, thanks.
Yeah, no, I feel like for neural network, it's something like people are still trying to develop the idea of what's a local solution or local global solution, or people don't care. Anyway, I feel like for different kind of constraint, you always find like different fundings for two-layer neural network. But I have definitely seen papers saying that if you have like a two-layer neural network with like one layer of non-linearity, the local solution always recovers a subset of the neural network. And so another guess I have, like, which is quite wild, is that we all know like this lottery ticket hypothesis, which says that if you have a highly over-parameterized neural network, you can always find a subset of it, which obtains a good result as the original one. I feel like that's like an empirical observation, like why local solution always makes sense. But this is just like intuition. No one knows what's going on.
So right now, yes, I mean, a lot of the existing theories about, Yu Chen has laid out all these important cases. They're already very important enough. And also, of course, cases about deep networks, layer-wise, and also specific object functions and so on. But John summarized this as two earlier slides. You had these two slogans, right? There's no general theory yet, right? Says what class of non-convex optimization that has all this. But there are two slogans are really saying that if your problem, if the object function is highly structured, for example, cross entropy, or I'll talk about some other object function, you have to seek low-dimensional structure, L0 norm, L1 norm, right? L4 norm, all those things. If the object function you look is for structure. Second is also your models are structured. Either the model is coming from the data or from the network you're building. Those actually needs to, the two slogans says that all the local minima actually are global. And also the greedy descent actually converge to that. So those are two slogans. You can think that they're sort of folklore theorem, but they're backed up by many, almost all the important cases so far. I think it is still, mathematics is still open to say more unifying framework that says what class of family of problems non-convex problem falls into. But so far we saw those two slogans has been held true for almost all the cases we have seen so far. Although they are non-convex, they're actually captured this optimistic picture rather than the most pessimistic picture, which is very surprising, very enlightening.
Yeah, but also that also says like why people do machine learning in a non-convex way. A lot of machine learning problems are non-convex, but we still use a solution. There must be a reason for that, right? Okay, and that's really good discussion. Any other questions I can? Okay, please.
Thank you. So I think there's one bullet point that you summarized that all local critical points has negative curvature in directions that break symmetry. I understood that as it might be a good thing because you can move along the negative curvature directions.
Yes.
Could you comment more on what's the implication of breaking symmetry?
Okay. So we mentioned like if we think about a generic non-convex problem. So one issue is a sparse local solution, and another issue is a flat saddle point. So if you're stuck at flat saddle point, so basically there's nothing you can do with a local search algorithm. And the good thing with the problem we mentioned is that even if you look at the saddle point, or flat saddle point, not flat, a saddle point over here, it's quite easy to figure out what's the next direction or what's the next progress you want to move, just by looking at the second order information. And that's could be quite efficient for computation. And in practice, you don't even to calculate hashing, you just have some random perturbation that's serve the goal as well.
So like breaking symmetry is like you would jump into like one of the attraction basin to a good solution?
Yes.
I see.
So as long as you don't stay in the flat region and you just follow the gradient descent, you run to your local solutions, which is a global solution.
I see. Thank you.
Yeah, that's a great. Yeah, Yu Chen also mentioned that this is actually very important because I mean the geometry here is that the negative curvature actually is really corresponding to what Yu Chen said is a dispersive, right? So they will steer you away from the stable manifold, which is actually zero measure set. Make it a low probability event, right? So you actually can just and so you can say that rigorously speaking, gradient descent may not do that. Gradient descent still allows you to stay on the grain curve, right? You might get stuck with there. But that's exactly the role of the noise diffusion process, right? So you can see computing the direction which orthogonal to the grain curve, still you need to compute in the second order, the negative curvature of the Hessian. It's still expensive. You need some iterations and so on. But turns out in practice, it's very easy to do that. You just add a little bit noise to it. If you add the noise to it, that will search direction orthogonal to the manifold with high probability, right? Which is exactly all the things you heard about all the diffusion model is precisely doing that, right? And the noise precisely behave the role of computing second order geometry for you automatically. So actually, by the way, that's also in the capture in the book, right? In the optimization algorithm chapter, we precisely talk about the role of noise gradient, how they deal with or help you implicitly computing the second order negative curvature, and which is equivalent to if you do computing it explicitly or implicitly, actually.
Yeah, so here I just want to give another quick comment. So basically, if you look at this geometry, one informal analog or picture you can have is basically like the champagne tower. So when you pull the champagne from the tower, it just goes up like smoothly. It doesn't do crazy things like that. That basically capture what's over here. But yeah, I want to add this story in it, but John complains all the time, so never mind. Okay, any other questions? Okay. I guess we can have the coffee break then. Oh, 15 minutes. We have 30 minutes left. We are 2 minutes ahead, behind. Yes. Thank you.
it's really my pleasure to give the lecture about
Hi everyone, welcome back to from the coffee break. So our last tutorial today, this morning, will from Sam, who is a citizen research assistant professor at TTIC, and he will talk more on understanding deep neural networks through low-dimensional models. Let's welcome Sam.
Thanks, Qing, and thanks everyone for coming to hear this next tutorial. There's a lot of more interesting stuff in store for the rest of the day, so I hope you'll continue to attend the sessions in the afternoon as well. Just a quick disclaimer that I hate to have to make. I'm nursing a bit of a cold these days, and so if I need to take a pause in the middle of the talk to drink some water, I apologize in advance and hope it's not too disruptive. So like Qing said, with this the next few lectures here, we're going to start talking about deeper models, still through the lens of low-dimensional structure. I just realized I think I don't have the clicker. Did I need a clicker? I'm a little bit stuck. Do I have that? Thanks, sorry. Thank you. Okay, so getting into deeper models, but first let's recap a little bit of what we heard about in the lectures this morning from John and Yuchen. So the first lecture where John introduced some of the canonical low-dimensional signal models and computational toolkits for working with those. In that case, maybe the most simple instantiation of those principles was the sparse recovery problem, where we have a low-dimensional signal, which is sort of sparse, but the structure here is all sort of linear or piecewise linear. We have linear measurements. The computational toolkit that we have for reconstructing or computing with these signals is that of convex optimization, efficient, scalable, all that good stuff. And we can even obtain, in many cases, provable guarantees for these algorithms, where the types of results that are representative of what we get, say when we have enough measurements of the low-dimensional signal, where enough here depends on intrinsic structural properties of the data, here measured through its sparsity, we can reconstruct efficiently using these convex optimization problems. Then going forward, where we wanted to be a little bit more flexible in the models that we have, in Yuchen's talk, we started to look at cases where we simultaneously learn the low-dimensional representation and the model itself. So in problems like dictionary learning, in order to have this flexibility, we needed to move away from the convex toolkit and start using non-convex optimization, which at first is scary, but as we learn in a lot of these very naturally occurring machine learning signal recovery problems, we can still have the same types of efficiency and recovery guarantees that we saw in the convex case, even using sort of local non-convex optimization algorithms as our computational toolkit, where the types of results we get again say that we can succeed when we have, in this dictionary learning case, measurements that depend on, again, intrinsic structural properties of the data. And so what I'm going to start talking about here, and what we're going to visit in the rest of the tutorials throughout the day, and indeed in the rest of the talks throughout the workshop itself, is where is the low-dimensional structure? How does this all play out in the more modern setting where we're now computing with deep learning models, going from where we had previously looked at linear measurements, bilinear measurements in dictionary learning. Now we have a sort of staggering degree of nonlinearity in these models. We're using, working with a variety of tasks here, but maybe in a very simple supervised case, just taking a network that has some parameters that we're trying to learn, using data sets, and so these networks will map data to outputs, maybe labels for classification. And this mapping now from parameters to the outputs of this network is sort of very highly non-convex, and it's not always the case that we have the same sort of structured, nice non-convexity that we saw in some of the previous models. So we want to understand here is, to what extent low-dimensional structure in the data and in the network itself, perhaps, is allowing us to understand, train these models, succeed on practical tasks. So where exactly and how exactly does low-dimensional structure play a role in the practice of deep learning, especially modern deep learning, where nowadays we have some pretty exciting, at least demonstration level sorts of AI tasks where we can see these models working. And so what we're going to see, and in my talk and the rest of the talks throughout the day, is that low-dimensional structure is still playing a massive role here once we sort of tease it out and identify exactly how it's playing a role here. And so I'll start off by doing a quick survey, just some sort of vignettes in the style of the talks previously, that are attempting to get at what exactly are the low-dimensional structures present in modern data sets that maybe demand or befit the use of these highly nonlinear deep learning models for computing with the data here. So I'll talk through a few simple examples there, and then once we have some idea of what the specific low-dimensional structures in data are, we'll try to tease out a mathematical model problem that we can study a bit, try to get some insights similar to what we had for the convex and non-convex case for sparse recovery and dictionary learning, where we can understand resource trade-offs in between properties of the network, the deep networks that we're training, and then structural properties of the data once we've suitably formalized things. After me, so when we come back in following lunch, Zhuhui will give us some discussion where we'll start to not only look at deep learning from sort of a data and model perspective, but begin to open the black box of this model a little bit, try to understand what is being learned in the weights or the features of these neural networks, and get a handle on that aspect of the problem. And then going forward later in the afternoon, Professor Yi Ma will be telling us about when we have specific low-dimensional structures present in data sets, maybe even how we can design end-to-end white box networks for computing with them under various notions of optimality. And of course, we'll see other talks as well, going more into applications in imaging, as well as a deep dive into sparsity in neural networks. So to start off, I'm going to talk through a few motivating examples of low-dimensional data that seems to demand the use of deep learning. And we're going to try to explore a few basic questions throughout these examples. So those two questions are, what will be an appropriate mathematical model for the types of low-dimensional structure that's present in these applications where we're using deep learning? And sort of how does a sort of reckoning and accounting of the low-dimensional structure that's present in these types of problems give us insights and even allow us to make practical improvements to sort of improve the deep learning approaches that we're using. So the first task I'll talk through at this point with some of the demonstrations that we see these days, text-to-image, photorealistic generation. Now we even have 3D scenes and videos being generated. So image classification, which I'm going to talk about here, can feel a little bit quaint. But in many ways, this is now perhaps a classical problem that has led to a lot of innovations in deep learning in terms of driving progress in architectures through optimization on benchmark data sets. So basic image classification task I'm showing here, we have a couple of non-orthogonal classes, which will appear a few times in this talk. We're trying to decide whether a given input pixel image contains as its content a hedgehog or a hairbrush. So the data space here is just the images. The outputs are going to be, for this binary case, maybe a +1 if we have a hedgehog and a -1 if we have a hairbrush. And we're interested in just training a deep neural network using some generic statistical learning loss in order to classify these data. And so the main question we want to have here is maybe why is it that we are often using deep models when we're computing with image data instead of more classical linear classifiers or kernel classifiers? And so if we think about the types of variabilities that are present in natural image data, we can get a little bit of an intuition for why we might need or why it might be most beneficial to use these very flexible deep models here. So natural image variability is sort of notoriously complex, and we can identify a few distinct different modes of it here. Deep learning sort of seems to give us a good tool for coping with all of these. So statistical variability, sometimes called that, can just be referred to variability, or can just refer to variability associated with different classes that is kind of a probabilistic type of variability. So something like the class of dogs being subdivided into several different dog breeds, and even different dogs themselves within the same breed having sort of variabilities in their appearance when we have images of them. This is pretty hard to cope with analytically, and this type of sort of a lot of the progress that we've seen in the last 10 years of deep learning has maybe been using these very flexible architectures and a very data-driven approach to training networks just to cope with these types of statistical variabilities in a data-driven way. On the other hand, there's also sort of much more geometric and well-structured types of variabilities that come up when you're thinking about invariant classification or invariant computing with image data. So one that I'm highlighting on the bottom left here is sort of geometric variability in the pose of an object, which is just arising because of the fact that natural images that you're maybe using or taking here of a subject sort of subjects move around in the scenes that we're sort of capturing in these 2D images. And so as a result of that continuous motion, you have sort of a continuous geometric structure associated to the different images shown here of the same face. So this is the type of geometric variability. Maybe pose variations are one of the most common, but there are also sort of other sorts of structured, well-structured variabilities, maybe associated with illumination as well. And all of these give rise to a concrete low-dimensional structure, maybe associated to families of images of a common subject or a common scene. So one maybe natural approach to, in deep learning practice, to working with these, or computing with these types of variabilities in order to have invariance, is still maybe a data-driven approach where we use something like data augmentation, taking known images in our training set and augmenting them with structured transformations, not always this complex in terms of pose changes, but maybe these sorts of contrast or illumination changes to the image, just enlarging the data set in order to encourage whatever models that we train on this data to be invariant to these types of variabilities. So this sort of low-dimensional reckoning is present in, even this very fundamental operation of data augmentation, but we can highlight some pitfalls associated with just this purely data-driven, perhaps reckoning with this type of low-dimensional structure. So probably most of you are familiar with adversarial examples in neural networks, where it's sort of there's this phenomenon that it's possible to make imperceptibly small perturbations to an input image for a deep neural network that's maybe been trained to do image classification, and due to the sensitivity of the network to the input, have the predictions change in a sort of wild way from the true class to the wrong class. So what I'm highlighting here is an even more fundamental issue than sort of these worst case adversarial perturbations, where commonly trained neural networks can be susceptible to maybe pixel level translations of images that are in the training set. So on the top row here, we're translating an image that the network classifies correctly by a few pixels in either direction, and seeing that the sort of probabilities associated with the correct class can plummet. And the same sort of thing is shown at the bottom, where we're having pixel level scale transformations of the input image. And nonetheless, although it's totally imperceptible to us, these simple geometric structured transformations that we encourage invariance to with data augmentation and things like that still end up in a lot of commonly trained neural networks having these sorts of stability issues. So robustness in neural networks, invariance as well, is very linked to, through this example and other similar ones, low dimensional structure that's present in the data. And it's important to keep that in account to have these types of desirable stability properties. So the next example I want to spend a little bit of time talking about is drawn from a slightly different application, but still very important, scientific discovery. And in particular, one application that I learned a little bit about during my PhD was this gravitational waves problem. So this is a case where we're trying to verify predictions of certain physical laws by taking some measurements of astrological phenomena, astrophysical, sorry, phenomena that are occurring in the universe. What's happening here is that there's an event, a black hole merger. When these two black holes merge, just based on sort of predictions of the laws of general relativity, there's a relatively small number of degrees of freedom associated with this system. And as a function of those degrees of freedom, certain gravitational waves are emitted, and those can be sensed with detectors on Earth that folks have constructed, at least in the USA. So the types of signals that you're getting in this application associated with an actual gravitational wave merger are shown at top left or top right here on the slide. It's kind of a chirp-like signal. And if you sense many different merger signals, just because of the fact that you have a relatively low number of degrees of freedom that parameterize the variability of these signals, what you end up getting is that the observations here follow the structure of a low-dimensional manifold, just parameterized by those degrees of freedom that are sort of characteristic to the physical signal. And so one very basic task that folks might want to solve in a problem like this is just detection. So trying to figure out whether an observation that we've obtained on some of these detectors that we've built contains a gravitational wave event. or not. So this is sort of a very simple classical statistical problem just associated with deciding between sort of signal plus noise or pure noise. If we can have these detection events, then we can sort of process this data, make sort of inferences, predictions on the underlying physical laws of the universe, and interesting questions like that. But there are already some sort of interesting issues that pop up, and even thinking about this type of a problem from the deep learning perspective. So one way you can perform detection here that's very classical is just to use kind of a template matching approach or a matched filtering. So because we have this sort of parametric flavor in the problem here, we have a small number of degrees of freedom that parameterize the variability of the signals that we're sensing. What we can do here is collect a lot of different templates associated with some physical model of the signal. That's the gamma parameter here, maybe capturing the masses in the previous slide. When we have some new data, we can filter that data against these templates. And if we sort of choose a threshold properly based on information theoretic criteria, we can decide that we have a detection or not when sort of a filtering exceeds a threshold. But issues that come up here, sort of things that you might like to do. So in the context of deep learning, there's a lot of unknowns in this system that you might want to compute or treat in a data-driven way. So for example, there are very complex noise processes that lead to corruptions in these observations. You might want to be able to use data-driven approaches using deep learning to cope with those. Even just talking about simple issues like optimality of this statistical test. In general, so I guess this is known in classical dating back to the 60s, but it's easy to forget in the modern deep learning era. This type of a simple parametric template matching test is not optimal. And to get a better test, you might want to be able, or working in sort of a data-driven way. This operation that we have here is the sort of template matching is very similar to one layer in a deep neural network, doing a lot of linear filtering operations and then taking a max, kind of like a pooling operation. It sort of stands to reason that with that similarity, maybe swapping out the detector here for a deeper network would allow you to do better in these issues of optimality, even efficiency as well. How many filters do I need in order to accurately detect? But the current practice here is very much on the science side, sticking with the sort of brute force template matching approach, just due to its simplicity and interpretability. If we can understand better the interactions between the deep models that we're sort of computing with on the internet scale and actual data that has concrete low-dimensional structures like we're seeing in this example, so we can potentially have a big impact in scientific discovery problems like this as well. So the third example that I'll talk a little bit about and that we'll see much more later in the afternoon is the issues of sort of computing good features from data in a self-supervised or unsupervised way when we're using deep learning and trying to understand how those features behave. So one workflow that's very common these days is to sort of do some kind of a self-supervised training, or maybe a training on a certain benchmark data set, maybe training a deep neural network on a large benchmark like ImageNet, and then taking the weights of that deep neural network. And when we want to solve a specific task downstream, maybe in computer vision doing some tracking or segmentation task, we'll take those pre-trained weights and then fine-tune them on data from our specific application in order to optimize performance for that specific task. And the idea here is that when we can pre-train on these very large internet-scale data sets of, say, images, we can extract good representations from our data, which are very useful for various downstream tasks that we might want to solve. And so issues that come up here, we might want to understand sort of in connection to the dictionary learning problem that Yuchen told us about in the previous talk. Can we actually get an understanding of what features are learned here, why they're good for these specific tasks, how they reflect structure, different types of structures in the data? And even more so when we have that specific knowledge, maybe like, for example, in the gravitational waves application where we know a little bit about the physical model that we think generated our signal, how can we incorporate that into the neural network that we're using to compute with these data, maybe to do a bit better performance-wise or efficiency-wise? So these are, I think, very active areas of research, and throughout the workshop we'll actually hear a lot of research talks around problems much like this in feature learning as well. This is sort of an area where understanding is evolving very quickly, but it's also one that's very intimately connected to low-dimensional structures. So what can we maybe pull out from these three vignettes as maybe a common thread to build off of? So the two things that I pull out here, the first is that nonlinearity in sort of the data that we're computing with in these deep learning applications is totally essential. So where deep learning is really maybe successful or needed, it's where we have complex nonlinear structures in data. And the flexibility of these nonlinear deep learning models is maybe in a large part useful for coping with these types of nonlinear structures in the data. That's one thing. And the other thing is that actually there are many important practical issues, especially robustness and invariance, but of course also efficiency and performance, maybe detection and things like that as well, that are linked to considerations about specific low-dimensional structures that are present in the data. So by getting a better understanding of interactions between deep networks and low-dimensional nonlinear data, we can get insights into these important practical issues. So in the next part of the talk, I want to say that maybe we've motivated enough, we have a good model here, and start to formalize a bit. So I'll talk a little bit about a specific mathematical formalization of a certain model for low-dimensional structure that's motivated in large part by the image classification task. And we'll try to do a little bit of analysis there. I'll give a high-level overview of some of the things that we can try to prove, understanding similar guarantees in terms of efficiency and resource trade-offs to what we talked about in the examples of sparse recovery. So before I do that, I want to just pause briefly and see if there are any questions about the motivation or the examples from the audience. If not, I'll just jump right into the next part. Okay, so especially inspired by the example in image classification, one thing that we saw there was that there's this very specific mode of variability of natural images associated with objects moving around, changes of pose, which are these sort of structured geometric transformations of an object in a scene. So these geometric transformations, because they have nonlinear low-dimensional geometric structure themselves, give rise, when we talk about maybe classifying between different images under these transformations, to problems where the main computational task is to classify between two nonlinear low-dimensional submanifolds of a high-dimensional ambient space. So the formalization we'll proceed with here is to say, okay, we have this geometric structure in practice. Why don't we model this as sort of a geometric manifold structure for our data? And so we'll try to understand what we call this multiple manifold problem, where you're solving a k-way classification problem of data where the classes are drawn from low-dimensional submanifolds of this high-dimensional ambient space. And we're trying to classify using a deep neural network. So more formally, here's some of the notation that we'll see throughout the rest of this part of the talk. We'll specialize to a simple case where we're looking at binary classification. And this gives us the two-manifold problem. So the task here is just the following. Given capital N IID labeled samples from some density that's supported on the union of two low-dimensional submanifolds of the unit sphere. Those submanifolds are going to be more or less arbitrary, subject to some constraints I'll talk about on the next slide. So those can be just very general geometric objects. Okay, so given those samples from this density, we're going to use gradient descent to train a deep neural network classifier, and we're going to try to obtain a guarantee that says that from gradient descent, we'll get parameters that give us a perfect separator for the manifolds. And so we want to understand conditions under which this is possible. So when I say perfect separator here, this is kind of asking for training on finite samples, generalization to unseen data in a pretty strong sense. So we perfectly classify all future data drawn from either of the two manifolds. So a few of the features here, again, just to highlight, this is just a binary classification task. So we're looking at sort of a simple ImageNet type inspired problem to get some insight here. We have sort of a latent or unknown low-dimensional structure that's present in this model. The data is high-dimensional. You can think of the ambient space here as kind of representing pixels in sort of an image. The low-dimensional structure is just the degrees of freedom parameterizing the intrinsic variability of the data. And we're sort of going to prove a generalization guarantee after training on finite samples here. And so the constraint that I'll look at here, or that I'll enforce, is rather than talking about general d-dimensional manifolds, We'll just look at one-dimensional submanifolds, and these will be asked to lie in the unit sphere. So one-dimensional submanifolds are just curves, like kind of is shown or sketched in the figure here. And so this is maybe the simplest possible example of a pretty general class of nonlinear, low-dimensional geometric structures for data distributions. And we're going to try to understand resource trade-offs here. So in analogy to what we obtained for the example of sparse recovery, we can try to set ourselves a goal here of what we want to understand and what types of guarantees are going to be appropriate, and maybe what are the central issues that we're playing with here. So in the case of compress-sensing sparse recovery, where we're doing reconstruction of a sparse signal from linear measurements, we had guarantees that told us when we collect a sufficiently large number of measurements here, where that sufficiently large is relative to the intrinsic structural properties, here the sparsity of the data, and we can efficiently reconstruct. So if we have enough sort of measurement resources relative to the intrinsic structural properties of the data, efficient reconstruction is possible. And so the questions we want to ask in this sort of mathematical model for deep learning are, what are the corresponding measurement resources? So presumably they're associated to the properties of the neural network architecture. And also, when we have this nonlinear low-dimensional geometric data, what are the intrinsic structural properties that are going to govern whether it's easy or hard to learn to classify data from the two manifolds? So we'll dig a little bit into first the issue of the intrinsic structural properties of data that are going to play a role in parameterizing difficulty of an instance of the two-curve problem here. And so we're going to see in the analysis that we look at here, just 3 parameters, more or less, can allow us to summarize difficulty. So we have kind of a separation parameter, a margin type parameter, a curvature parameter, which we're going to see is governing sort of regular or irregular each individually the two data manifolds are, and some kind of a complicated separation frequency parameter, which we'll talk a little bit about, and just is governing how many times the data can tend to loop back on itself. So first, just this separation parameter. Like I said, this is a lot like a margin parameter in classification problems, but in this geometric data model, the two-curve problem that we're looking at here, this is measuring sort of what's the minimum nonlinear distance measured through walking in the extrinsic space. So our curves lie in the sphere here. That's the extrinsic space. And what's the minimum nonlinear distance between a point that crosses the two curves. So in the figure here, kind of in the top right, there's a small deep purple line that marks the minimum distance in this sort of 2m's configuration between the two curves. So this is intuitively measuring how difficult it is to separate the two data distributions. And we're going to assume in the analysis that this is a positive number. So the separation is important. We also have sort of a curvature parameter. Because we have this nonlinear geometric structure, now we need to measure sort of what is the deviation of our data manifolds from being kind of the ideal not curved flat structure. And this curvature parameter that we define on the slide here is capturing that. So intuitively, for this sort of definition of the extrinsic spherical curvature of a curve, a one-dimensional manifold on the sphere, this quantity is going to be equal to 0 for the analog of a subspace or a flat data distribution. So that's just a subspace intersected with the sphere. And in the one-dimensional case, that'll be a great circle, just a sort of hemisphere of the sphere. In that case, we have 0 curvature, and we have maybe in the sense of curvature, a very benign data distribution. In general, though, when you have curvy data like these 2m's, the curvature can be quite large. In the figure here, we're marking the point of maximum sort of worst case curvature over either of the two data distributions with this little pink oscillating circle. So 1 over the curvature is equal to the radius of that circle. When the data tends to sort of, the data manifold moves quickly, loops quickly in that sense, you have a higher curvature measured through that radius being small. Question? Yes, good question. Exactly, yeah. So this X here is implicitly reflecting a parametrization of the data manifold. So we have like just a parametrization of the curve, and the double dot means the second derivative of that parametrization in, kind of the arc length sense, walking along in that parametrization. For curves, this is kind of canonical, so we can always have such a parametrization subject to some technical assumptions which are really quite general. But that's what the double dot means. And then the other things appearing here are just X. This first matrix is kind of a projection, so this specific quantity here on the sphere, I can't remember if we talked about it in the previous talk, but on the sphere, the tangent space to the sphere is kind of, it's going to be perpendicular to the radial component of a point on the sphere. So if this is the surface and this is 0, the tangent space will look like that. And this matrix here is projecting into that tangent space. So it kills any component of the curvature of either of the data manifolds that's going parallel to the current point. That's why I call it an extrinsic curvature in the sphere. Does that answer the question? Thanks. Okay, so curvature, separation, and the third parameter that we need in order to talk about complexity here is this Clover number parameter. So we'll call it the Clover number. This is capturing intuitively the tendency of either of the data manifolds to loop back on themselves or come close to a point on the other curve a large number of times. So while you're parsing maybe the formula here, I'll just talk intuitively about what this parameter, what we feel like it measures, maybe for practical data. So again, thinking about the example of very simple image transformation manifolds. At the top right here, I'm showing you some T-SNE embedding, so heuristic, but hopefully representative, of data that's obtained by taking an MNIST digit, so at the left a 4 and at the right a 1, and taking all possible rotations in the plane, so by angles from sort of 0 to 360 degrees of that digit. So that gives me a bunch of images, and then I T-SNE those to get a low-dimensional representation of the variability. So what we end up seeing with the 4 is that when we embed, this data tends not to intersect itself. Whereas for digits that are self-similar, like the 1, so it has a symmetry under, or an approximate symmetry under rotation by 180 degrees, we tend to see in the T-SNE embedding a self-intersection around halfway through the, along the way of the parameterization once we've sort of embedded in the low-dimensional space. So this Clover number parameter that we define here, which intuitively counts the number of times that the data can loop back on itself, is going to be higher in this example of image transformation manifolds for data that is self-similar, so data that has certain symmetries. Like in the digit case, we have this symmetry under reflection by 180 degrees. So intuitively, for practical data, data that is coming from image transformation manifolds or data coming from maybe physical systems, we probably don't expect this sort of a self-intersection parameter to be too large. But when we go through the math, it's important to have a precise accounting of what it is for the types of guarantees that we get. Again, this is just counting we have this separation parameter, which is determining the minimum distance between opposite curves. This is counting how many times we can actually come back to a neighborhood that's at that sort of resolution of that separation. So that gives us these three complexity parameters, intrinsic structural properties of nonlinear low-dimensional data, that in this two-curve problem that we're studying here are going to allow us to parameterize the difficulty of an instance of the problem. So it's interesting to note here, maybe there's an analog somewhat of the separation when we talk about sparse or other sorts of bilinear, et cetera, non-convex models. But a lot of these parameters here, especially the curvature, these are truly nonlinear that only sort of show up in problems when we actually go to model the sorts of nonlinear structures that we think are present in a lot of deep learning applications. So in that sense, they're capturing that unique aspect of the data in these types of problems. So next, let's talk about the neural network that we're going to use, the algorithm gradient descent that we're going to use to train, and get those details out of the way. So in this discussion, we're just going to consider a very simple, very generic neural network architecture that's nonetheless flexible enough to allow us to talk about some trade-offs. So we're going to work with a deep feed-forward ReLU neural network. The depth is going to be L. The width we're going to call N. All the layers have the same width. we're going to consider gradient descent training from a Gaussian random initialization done in kind of the standard fan-in or PyTorch format. All the weights of the intermediate hidden layers are going to have sort of 2 over width variance, and that 2 is just a parameter to guarantee stable propagation throughout the neural network. And the training that we're going to do is just very simple, sort of classification as regression, training on the empirical mean squared error, evaluated over these capital N IID labeled samples that we have from the unknown density, supported on the union of the 2 data manifolds. So this mu will be the sort of measure associated to that density rho. So just recapping or going back to this analogy between the example of sparse recovery, now in the sort of nonlinear deep learning setting that we're trying to model and study here, we have the sort of nonlinear structural properties of the data that are representing our intrinsic structural parameters, maybe a little bit analogous to sparsity in the familiar case. And we have these architectural resources associated with the neural network, sort of in analogy to our measurement resources in the sparse recovery case. So those architectural resources are going to be in our analysis the width of the network, its depth, and the number of samples that we get from the 2 densities. And we're going to try to understand this issue of resource trade-offs here. How do we need to set the resources of the neural network, the architectural resources, statistical and sort of architectural, relative to these structural properties of the data? How complex is an instance of the 2-curve problem, so that we can guarantee success with gradient descent training? This is the question we're going to try to study, answer at a high level in the rest of the talk. So let me talk a little bit here, going into some of the details of the analysis and how we can sort of maybe start to prove some types of guarantees for neural network training, even though the optimization problem is highly complex. So the square loss empirical objective, we can write it in this kind of arcane form, which is sort of useful for analysis. This is the objective we're minimizing as a function of the neural network parameters theta in our training. And we want to prove that gradient descent on this loss can give us parameters that are going to yield perfect separation of the 2 manifolds. So one approach we might try to take here, which is sort of analogous to what we were using for the convex and non-convex toolkit that we talked about in the first 2 lectures, is to understand the geometry of this objective phi, maybe using considerations about the symmetries associated to the neural network architecture that we've selected, this deep feed-forward network, in parameter space. So an explicit understanding of sort of the theta side geometry, like what we use to analyze problems like matrix factorization, deep learning, sparse blind deconvolution, in which we've gotten a lot of mileage out of in the last 5 years. So this, I think, is, although there's always new and interesting progress for neural networks, this is extremely hard just due to the level of sorts of complex, non-convex interactions between the parameters associated with different layers of the neural network. And so in this talk, we're going to use a kind of different approach to look at the analysis of the neural network, which is to consider simpler dynamics. What I mean, we're going to analyze this objective from kind of a different perspective, just considering dynamics in input-output space. That is to say, sort of a kind of aggregate evolution, not of the parameters themselves, but of the prediction function that's implemented by those parameters. So that's going to be the evolution of the neural network's output, f sub theta on an input x. And a quantity that's going to play a big role in the analysis, which very naturally governs this evolution of the prediction function, is the so-called neural tangent kernel, which we'll talk exactly on the next slide about how this arises. But intuitively, this kernel is just an inner product between gradients at some parameters of the neural network function, evaluated at 2 distinct data points. And in that sense, it's measuring intuitively how easy it is to adjust the neural network's output at one point x without changing it at x prime. And in that sense, we can have the intuition, which we'll talk much more about in detail later on, that we want this kernel to be very sharply sort of peaked around the diagonal where x is equal to x prime. If it's small, when those 2 inputs are distinct, we can make rapid sort of gradient updates to our parameters. We'll see that in detail on the next slide. So to do that, I need to introduce a little bit of a notation. Forgive me. So two things we'll see throughout the rest of the discussion here. We're going to call this signed error zeta. That's just the difference between the neural network at some parameters. And so in particular, for most of it, we'll be looking at the random initial parameters of the neural network. You can think of theta most of the time as just that. So the difference between that neural network at random initialization and the true label function for those two manifolds. And the algorithm will use a sort of idealization of the constant stepping gradient descent, which is just going to be a simple gradient flow, kind of just a continuous time analog, ignoring some technical issues, which we can always sweep under the rug and then resolve. This is kind of a continuous time analog of the constant stepping gradient algorithm on the parameters. So we see, kind of in the Slobin form, that this this error function, the learned predictor minus the labels, evolves according to this neural tangent kernel, and it just comes through, a very simple calculation here. So this first equation is just dotting with respect to t. This is sort of the directional derivative. If we plug in the definition of the gradient flow for this theta t dot, we get an equation like this. And if we manipulate it a little bit, we end up seeing a certain integral operator arises very naturally, which involves this neural tangent kernel, the inner product between gradients. So the integral operator here is associated to the empirical measure coming from our finite sample from the data distribution. And so if we write that compactly, what we have sort of as a bolded integral operator, kind of analogous to a matrix that collects our different neural tangent kernel evaluations at the different capital N sample points in our data set, we end up with this very simple integral equation, or you can think of it as a matrix equation, that describes the evolution of the error throughout gradient descent training of this neural network at all points across the two manifolds. So this becomes significant because of this very interesting observation, to my knowledge originally from these folks, Jacot et al., which is that you can actually analyze, so this, this complex dynamics that really governs the error evolution here. It's complex because this integral operator, bold theta, has a time component. So it actually changes with time. It changes in a complicated way that reflects both the random sample from the data distributions, this mu sub n, and also the specific evolution of the parameters of the neural network theta t, because this neural tangent kernel operator here that arises is evaluated at the iteration t parameters of gradient descent. So that sort of hasn't solved our problem of needing to analyze complex aspects of the landscape, the geometry of this objective as a function of parameter space. But what's interesting is that when you over-parameterize the neural network enough, when its width is very large relative to various architectural aspects of the network, and you have a large number of samples, so it turns out that this complex integral operator theta t is very close in a very strong sense, kind of an operator norm sense, to its random, its time zero, so at random initialization, expected value, so averaged over the weights value. So this is now a deterministic kernel, this theta, that doesn't depend on time. And once we actually perform this swapping out, we get a much simpler dynamics, which still implies guarantees for the original one, which is just a linear time invariant system. So this error in this auxiliary, maybe nominal dynamics, is just evolving according to a fixed matrix or a fixed integral operator, theta. And now we can actually prove guarantees about the norm, say, of the error, which is going to allow us to control the generalization error in this problem, just using sort of reasoning about aspects of linear systems. So relationships between the initial error and the eigenfunctions and the eigenvalues of this integral operator theta. We'll get rapid decay, fast generalization error from gradient descent when we have a good alignment there. So the challenge here technically is just that in order to prove that we have alignment, when we have sort of nonlinear low-dimensional models for the data, it's very hard to argue that explicitly because there aren't any closed form expressions available for the eigenfunctions of this integral operator for general nonlinear low-dimensional geometries. And even if we do have those expressions, it's sort of a massive lift in terms of calculation in order to prove something. So the approach that we use in our analysis is to be a little bit more implicit, and so we didn't get to go into all the details, but I'm sure most of the audience is familiar here with maybe the dual certificate construction of optimality in sparse recovery and compressed sensing. So in a sort of homage to that theory, we're going to, in this nonlinear case, call a function g defined on the manifolds a certificate if it satisfies two conditions. One of them, and this is kind of capturing implicit alignment with good sort of low, large eigenvalue eigenfunctions of this integral operator. So if we can integrate g against this neural tangent kernel theta operator and approximately in a mean squared error sense reproduce the initial random error, and we can do that with a function g, a certificate g, which has small norm. So then if that's the case, then g will be called a certificate. Let me just say intuitively what is going on here. You can think of this g, since it's a function defined on the two manifolds, and what I'm actually plotting here is a numerical rendering of a certificate for this running example of two m's that we've been looking at in the talk so far. So the certificate here, it's actually a function on the two manifolds, and it sort of encodes through its sort of local global properties, kind of local variations, global things like like its height, the complexity of classifying the geometry. So I'll talk a little bit more about that later on, but you can see here that the certificate shown in purple is kind of larger in magnitude at points where the manifolds are closer. We saw the purple line earlier in the talk, and also a bit larger at points where the curvature is high. So in that sense, it encodes difficulty of the classification problem. And maybe in sort of a familiar way from the compressed sensing perspective, we can talk about in kind of an algebraic way, this certificate is guaranteeing that the initial error, the zeta, I didn't write it, but zeta is on the left-hand side of this mean square relation up above. This zeta is going to be close to the stable range of this random initial integral operator theta if a certificate exists. This is sort of implicitly guaranteeing that most of the energy of zeta is concentrated in the high eigenvalue eigenspaces of this integral operator. And that's what I mean by the stable range. So two perspectives through which this certificate is helping us to implicitly reason about the difficulty of the classification problem and to be able to prove generalization. And I won't talk about any technical details, but just a small lemma and a little bit of scaffolding allows us to conclude that if a certificate exists, so satisfying the conditions up above, suitably made quantitative, then we're able to decrease sort of this L2 error, this generalization error of the predictor fairly rapidly as a function of different architectural properties of the data. So a certificate existing is going to be sufficient for us to guarantee that we generalize and that we get a result for the two manifold problem. So in the rest of the talk, I want to dig a little bit into, now that we're sort of armed with that understanding of how we can get a theoretical result here, what are some of the main resource trade-offs that play a role in whether or not we succeed in this classification problem? And specifically, so how do the architectural and statistical resources in the problem, the network's width, depth, and samples, play a role in governing properties of theta, ensuring that a certificate exists? And also, how do we have sort of an interaction between this operator theta and the geometry of the data? And so two sort of foreshadowings, what we'll see here is that the depth of the neural network is going to play the role of a fitting resource. So we'll see that when we have a deep enough network relative to the geometry, we'll guarantee the certificate of small norm exists, satisfying the conditions that we need. And the width is going to play the role of a statistical resource. When the width is sufficiently large, the network is sufficiently over-parametrized, we're going to tamp out statistical fluctuations associated with the random initialization and to some extent the gradient descent dynamics. And that's going to allow us to have sort of good control of all this random operator theta around its expectation and allow us to replace the complicated random process with a more simple deterministic one. So first, let me talk about just the key insight that comes from depth here. So if we talk a little bit, we haven't looked into it yet, but if we actually do some plotting of this neural tangent kernel theta that's associated to our Rayleigh network, we see something that's pretty striking. So this kernel, just by virtue of the Gaussian initialization, theta is a rotation invariant kernel on the sphere. So I can get its value evaluated in any xx prime just by picking one reference point and looking at how it looks there. So that's what I'm showing in the plot at the right here. This is a profile around the North Pole of a suitably scaled version of the expected infinite width neural tangent kernel theta at a fixed depth 5, sort of suspended over the sphere. And what you see is that sort of in a way that's desirable for the types of guarantees we want to establish, this kernel is localized around 0, and it kind of decays as we move away. So that's good because, as a reminder, this neural tangent kernel is governing our ability to adjust the network's output at distinct input points. If it decays fast, that's a good indicator that we can do what we need there. Then the interesting effect that we see is that when we increase the depth of the neural network, this kernel gets sort of more sharper and more localized around its value at 0. So this is stepping up now to a depth of 625, where the kernel, at least at this resolution, kind of looks like a very sharp point just around the initial value. So what that means is that by increasing the neural network's depth, we can make this kernel sharper and sharper. We can give since this kernel is connected to the dynamics of gradient descent, that gives us a better ability to fit complicated functions. And in particular, when we make the sharpness, the level of sharpness of this kernel sufficiently large relative to the geometric complexity parameters of the data distribution in the problem, so things like the curvature and the minimum separation between curves, we can guarantee that a certificate will exist for the specific instance that we're studying. In a SOLGAN, we have deeper networks fit more complicated geometries. And just to show you a little bit maybe of a simple illustration of the last claim, that we can decrease the size of the certificate by increasing the depth, this is just a very simple numerical experiment following along from the example shown previously of the certificate for the 2m's geometry. So what I'm showing it right here are two traces, unrolled, or kind of, I guess, unwrapped versions of the certificate's sort of trace on both the plus curve and the minus curve. So left is going to be plus and right is going to be minus. And the different warmths of green coloration of these different traces shown in each plot are representing sort of the magnitude of the certificate for different depths of a kernel. So what we see here is that actually the magnitude is decreasing in a pretty strong sense as we increase the depth of the neural network from 1 or 2 to 10 to 100. It's going down kind of an octave for each increase in depth. And something that doesn't, you may see if you squint at it a little bit, is that there's a fairly pronounced improvement in the size of the certificate when we go from a very small depth, like 2, to a larger, depth around 100. So we have some kind of diminishing returns with respect to depth as it gets larger and larger and larger. There's something, but it's a little bit diminishing. But the fact is that for small improvements, once we pass that threshold where the depth is set appropriately relative to things like the separation between the curves, their curvature, we actually get a fairly significant improvement. So that's the main effect in the analysis that is allowing us to guarantee the certificate of small norm exists by increasing the depth. And again, this is just a simple numerical illustration that this really does play out in, at least a simple example of a geometry here. Next, I want to talk briefly about the role of width in the analysis, tamping out those statistical fluctuations. So what we're illustrating here is just, so the main role of width in our analysis is to control the fact that when we randomly initialize the neural network parameters to theta 0, these Gaussian initialization, they induce a very complicated process, random process, but still quite complex, associated to the gradients of the network that defines this neural tangent kernel operator theta. So the main task that we have for the width here is to understand, so how does adjusting the width control the statistical fluctuations of that random process around its sort of expectation? So what we're showing at the right here is kind of a trace of just a single sort of sample trajectory of this random process for some fixed x and the x primes that kind of move along a great circle going away from them, of this expected neural tangent kernel and various random instances of it at finite widths. And so what we see from this intuition is that as the width is increasing, we get more and more bounded fluctuations around this infinite width value, kind of shown as the nominal sharp curve in green in the middle. So as the width is larger, we get better concentration around the infinite width expectation of the neural network. Another role that the width is playing in the analysis that we won't touch into here because it's more technical is that neural tangent kernel aspect of things, which is guaranteeing that the actual integral operator theta t that governs the evolution of the error throughout training is actually changing with time. So in practice, we also need to make the width pretty large relative to other polynomials in sort of the network architectural parameters in order to guarantee that that change is small. That ends up setting a lot of the very messy rates in the analysis and rates that are associated in general with this type of neural tangent kernel approach to analyzing neural networks. And there's going to be a lot of research talks, I think, throughout the week about approaches that in maybe simpler cases can get around those sorts of unsavory dependencies, give you better efficiencies, provable efficiencies for neural network training. But with the neural tangent kernel approach here, and again, I'm not going to go into too much more details on that, but we also need to have overparameterization in order to guarantee that lack of changes to the neural tangent kernel throughout training. So the type of result that we can prove for the concentration of the initial random neural tangent kernel around its expectation is something like shown here. So when the width of the neural network is growing like a sort of linearly with the depth of the neural network, plus polylog factors in the depth, the ambient dimension, as well as maybe the sort of dimensionality of the manifolds, then we have sort of uniform concentration, kind of a strong subnorm concentration of this random process around its expectation. And so that allows us to effectively replace the initial random neural tangent kernel with its expectation and analyze that when we do the certificate construction part of the analysis of the dynamics. So what we end up getting here through this guarantee, through this linear dependence of the width on the depth, is that we're going to make our network wide relative to how deep it is, and that depth, again, is reflecting how complex the data is. So this is how the resources of the neural network need to be set relative to the structural properties of the data in order to guarantee success here. So the last aspect that we'll talk about briefly is the statistical resource of the number of samples we need to guarantee success in the problem. So here I'm just showing a simple case for that illustrates kind of the basic trade-off that we have here. So intuitively, we're minimizing the empirical mean squared error on our n sample points from the data distribution. So these two traces here are kind of illustrating what we expect to get here from this analysis I've described earlier in the talk around sort of the linear time invariant system governing the evolution of the error, is that at all the sample points, so since those are part of the training objective, we're going to get a small error, sort of in squared magnitude. And we're going to, in order to argue that we generalize, we're going to need to guarantee that this error is not getting too large when we move away from those sample points. So generalization is asking us to have a small error everywhere on the two manifolds, in particular in order to guarantee that we have this sign threshold consistency of the classifier. The error needs to be less than 1 in magnitude. So just guaranteeing that we have minimization at these finite sample points is also implying the error is not too large away from them, is going to allow us to generalize. And the way we end up doing that in the analysis is just using the fact that, again, when we're training in this neural tangent kernel regime, the dynamics of the evolution of the predictor, the zeta function, kind of evolves according to a kernel dynamics. So what that means is that there's a very characteristic shape that you can associate in a worst case sense to the deviations of this error function as we move away from the sample points, as we train for long enough times. And that characteristic function is really governed by just the shape of the neural tangent kernel. We were talking before about how the shape is governed by the depth, and deeper networks lead to a sharper, more localized kernel. The flip side of that is that when we localize more and more the kernel, now our error can grow more and more as we move away from our sample points. So what that means is that in order to guarantee generalization here, we just need to have a sufficiently large number of samples relative to this kernel aperture parameter, this sharpness localization aspect of the kernel. So functionally what that means is that the number of samples needs to be set according to the depth, since we talked about how the depth is what determines the sharpness of this kernel. So eventually, in the result that we're going to establish, we'll have a dependence of the number of samples for success on the depth of the neural network, just governed by this aperture of the kernel. And so the type of result that we can end up getting is going to look something like this. So for sufficiently regular one-dimensional manifolds and ReLU neural networks, when we set the depth of the neural network relative to intrinsic structural properties of the data, when we set the width to grow as a sufficiently large polynomial in the depth, and when we have a number of data samples that grows like a sufficiently large polynomial in the depth, then after not too many iterations of constant stepping gradient descent, we'll obtain parameters that give us a perfect classifier for the two manifolds. So that gives us, although the rates here are not going to be totally sharp, a somewhat satisfying resolution to the issue of resource trade-offs in this two-manifold problem. So we've understood the role that each of the architectural and statistical resources in the problem plays in allowing us to succeed here, how they need to be set relative to structural properties of the data. And that's given us sort of an end-to-end analysis here where we can prove a result for neural network training that just can be stated in maybe half of a slide, subject to technical restrictions. So that's all for this part of the talk. Let me very briefly summarize the conclusions again and try to interest you in some of the coming attractions for this afternoon as well. So what we've seen here is that maybe one of the essential features of low-dimensional structure and deep learning in modern applications is that nonlinear low-dimensional variabilities in modern data sets demand the use of these flexible nonlinear deep models. And we can have some understanding using generic neural networks and a simple data model of what types of resource trade-offs play a role in guaranteeing success in certain model classification tasks between these structural properties of the nonlinear data and the deep neural networks themselves. So we're going to start to, as I alluded to before, later in the afternoon, open the black box a bit here. We're going to talk more about features that are learned in the weights of these neural networks during training on certain classification type tasks. And then we'll talk even more about design of deep neural network layers for seeking good representations of low-dimensional structured data and motivated by certain structures that you may know are present in some tasks. So that's all to come in this afternoon. I hope to see you guys back later on for that. And thanks for listening to my talk. I'll take any questions if you have them.
So this is very high level. Can I think of your results as sort of analyzing the NTK kernel under these manifold assumptions a little bit, or no?
Yes. Yeah. So I haven't gone too much into other aspects, but there's also kind of an optimization side of things. So the analysis is going to be specific to the case of using a deep neural network, because for us, we needed to use depth large to prove these types of guarantees that you described. So can we get some new guarantees as well for the optimization side of the neural network, or the neural tangent curve training? So it'll have those two components, if that makes sense.
Thank you.
A couple of questions. The first one is, what is the connection between the manifold separation problem and, say, the first vignette?
Yeah, that's good. I think if there is any connection, it's highly stylized. And maybe so, in that sense, the connection is one of motivation. So we were maybe motivated to consider this manifold separation problem by considering some very simple model problem for separation of image templates that are induced by certain types of geometric structures. Of course, when you get down into the details, this type of Riemannian manifold structure is not the correct one for working with image transformation manifolds. There are a lot of other issues, different variabilities, like we alluded to in the first vignette, illumination changes, things like that, that will make this task of separation of positive delta manifolds not the one that you really run into when you talk about classification of distinct image templates. But if that makes sense, it's kind of one of inspiration, drawing the inspiration from that first vignette for the manifold separation problem.
The second question is about the significance of the problem. Do we really want to, I mean, in most statistical learning problems,
yes,
there are errors in classification.
Yes.
And what we want simply is a small generalization error.
Yes.
While here, the task is really to achieve perfect separation.
Yes.
And therefore, by definition, you need to have a margin before you start. And also the y was a deterministic function of x.
Yes.
as opposed to x comma y being drawn from a joint distribution. So
Yes.
what is the significance of the problem?
Yeah, that's a good question. I think it's, for this work I've talked about here, it's extremely important to extend it to this case of noisy observations, a general distribution rather than just y of x, as you said. I think because, although I'm not getting into a lot of the technicality in this talk, I think the technical kind of scaffolding framework that we introduce in order to prove this manifold separation result can be useful for the general case as well. Although much more needs to be done to cope with noise, I think the basic analogy is that you can imagine replacing this function y of x that I've talked about here with the regression function in a more general classification problem, the conditional expectation of y given x. This is maybe not the most general noise model that you can consider, but I think it's a good step towards more realistic classification problems that you described. And when we think about it through that analogy, then the same type of formulation that I've presented here, this L infinity guarantee for generalization, it's not going to connect to generalization perfectly per se, but I think it does have an interesting statistical interpretation, maybe getting whether or not you can learn a well-calibrated predictor, a predictor that is getting close in L infinity to the regression function. It's not immediately clear here. I'm thinking through some of the connections these days, whether with this, this approach that's described here, the neural tangent kernel approach, just the kernel approach in general, whether you actually have this type of a consistency property or a close enough to consistency property. But this is an interesting question that I agree should be explored in follow-up work. But I do think the framework is going in that direction, although I haven't presented with you sufficient details for you to make that judgment here.
And my last question is, in the vignette, it was sort of clear how there was a low-dimensional manifold.
Yes.
But in the theoretical results, what was the dimension and what was the role that that dimension plays on the result was not entirely clear.
Yes. So in what I've presented here in the analysis that we've done for this problem, we've only looked at the case of dimension 1. That's why we fixated on this figure with two curves that we're separating between. So in general, I think for the type of approach we have presented here, the kernel-based classification and things like that, we can expect some exponential unsavory dependencies on whatever dimension of the manifold we have, if we model that aspect of the problem as well. Maybe in practice we expect this dimension to be constant or something like that, but exponential is still going to be pretty unsavory. So it's interesting to think about whether other types of techniques or whether other types of data structures, say not just an arbitrary d-dimensional Riemannian manifold, but a data manifold that has some structure, factorized, hierarchical. There are some analogs in maybe subspace arrangements. Whether then we can have better efficiency guarantees using the same type of framework. That becomes an interesting question that could be more connected to practice. But the short answer is that, yeah, we've just fixated on the d equals 1 case here. Although in general, we do want to be extending to that setting. Thank you. Yeah. I think we're reconvening at 1:30. Is that correct?
All right, thanks. That concludes our morning session, and we have about 1 hour for lunch, right? Lunch will be at the, which restaurant? Garage restaurant, okay, in the hotel, right? I'll see you guys, we can reconvene around the 1:30 for the afternoon sessions. Yeah, see you there, bye.
നോയ്സ് ഉണ്ടോ? ഏയ് ഏയ് ടെസ്റ്റ് മ്യൂട്ടാണ്. ടെസ്റ്റ് एक डेट डालकर नहीं आ रहा है. ടെസ്റ്റ് 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 എല്ലാം പോയോ? ഒന്നുമില്ലല്ലോ. ഓക്കെ അല്ലേ? അറ്റൻഡ് അറ്റൻഡ്. ടെസ്റ്റ് 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 ചെക്ക് 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 ടെസ്റ്റ് ടെസ്റ്റ് ചെക്ക് 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 ടെസ്റ്റ് 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 ടെസ്റ്റ്
पावर चेंज कर लो क्योंकि अभी इससे वीडियो है 58 मिनट्स का वीडियो है.
with this setup now, our goal is to study the properties of the learned features and classifiers. We assume the network is well trained. Probably you would imagine there should be like different ways actually to characterize the properties. And in this lecture, we will take two perspectives. The first one is that we take one input and then we look at its features. We try to say what's the properties, the features we have. Okay, so we call this one as the individual property. The second one is that we put all the samples into the network and we take out all the features. And then we look together what's the features, what's the properties among all these features. We want to study these collective behaviors. It turns out that low-dimensional structures will emerge actually in both perspectives. Okay, so let me be clear what we mean by these individual perspectives. So here we use the AlexNet as an example, which is proposed 10 years ago and which is one of the pioneering architectures. So this AlexNet, it contains 5 convolutional layers, and on top of this one, we have 2 fully connected layers. So now that network is fully trained, and on the left, I plug into an image. So for example, here is a boy image.
This. This.
check.
Thanks, everyone. Welcome back to the afternoon session of the educational tutorials. We're going to first hear a talk from Zhuhui Zhu from the Ohio State University about representation learning in deep neural networks and low-dimensional structure. So thanks.
Hello, everyone. Welcome back to the tutorial sections. So this is Zhihui from the Ohio State University. It's a pity that I can't join in person, but it's really my pleasure to give the lecture about learned low-dimensional structures by deep networks. In the last lecture, Sam has talked about resources needed to ensure classify two manifolds. Now we will focus on the general classification of K-manifolds. And moreover, we will look inside the like deep networks. We will focus more on the learned features and classifiers. So let's first give the terminology we will use during the lecture. So we will use capital K to denote the number of classes. So capital K could equal to 10 for MNIST. Capital K could equal to 1,000 for ImageNet. For each class, we assume we have a bunch of training samples. So for example, we could have n different cat images. We could have n different dog images. So during the lecture, we will assume the dataset are balanced in the sense that each class has the equal number of training samples. They all have n training samples. Well, if not, we can easily use tools like data augmentation to make them balanced. Then for each training samples, we will label it. A common choice is so-called one hot labeling vector, which is a length K vector. It only has one non-zero element at the corresponding locations indicating its class membership, and the zeros at the side. We will have different deep neural network architectures, but most of them contains two parts. The first one is called feature mapping, that we map an input image X to say a wrong vector in a high dimensional space. And then on top of the feature vector, we have a linear classifiers. There exist different architectures for these feature mappings. They share kind of like similar structures in the sense that they are layer-wise structures, and each layer contains an affine transformation, and then we have another layer on top of the previous layers. So each layer could be like fully connected layers, as in Sam talk, could be convolution layers, or could be like a transformer. So with this setup, the network output will simply be W multiplied by the features for each input X plus the bias factor. And then the training problem boils down to find the optimal parameters, which is the theta prime in the feature mapping, the linear classifiers W and B, by minimizing the difference between the network output and the one hot labeling vectors for all the training samples. And we usually a common choice is by the so-called cross entropy loss, which we will talk in the next slides if you are not familiar with this one. And then we usually add a regularizer, for example, the weighted decay, which is a common choice, which is simply the L2 regularizers on the network parameters. If you are not familiar with cross-entropy loss, so here is a simple formulation of how we calculate the cross-entropy loss between the network output and the one hot labeling vectors. So for example, if the network output is so-called 1, 0, -1, we first apply the so-called softmax function to transfer this to a distribution, which basically that the first element will map to 60%, which says, well, this input has 60% being to cat, and 13% being to dog, and 10% being to panda. Now we can view the one hot labeling vector as also a distribution. Then we can say we just need to capture the difference between these two distribution probabilities. And this can be used as, so this can be captured by the so-called cross entropy loss, which in this case equals to a negative log the network output of the corresponding probability. So here, the network output of the probability cat class, which is 60%. So therefore, the cross entropy loss for this case is negative log 60%. In this case, so from this, we can say that cross entropy loss achieves its minimum when the network output probability is equal to the one-hot label vectors, which means it will give us the correct prediction. With this setup now, our goal is to study the properties of the learned features and classifiers. We assume the network is well trained. Probably you would imagine it actually be like different ways actually to characterize the properties. And in this lecture, we will take two perspectives. The first one is that we take one input and then we look at its features. We try to say what's the properties, the features we have. Okay, so we consider one as the individual property. The second one is that we put all the samples into the network and we take out all the features. And then we look together what's the features, what's the properties among all these features. We want to study these collective behaviors. It turns out that low-dimensional structures will emerge actually in both perspectives. Okay, so let me be clear what we mean by these individual perspectives. So here we use the AlexNet as an example, which is proposed 10 years ago and which is one of the pioneering architectures. So this AlexNet, it contains 5 convolutional layers, and on top of this one, we have 2 fully connected layers. So now that network is fully trained, and on the left, I plug into an image. So for example, here is a boy image. And then we look at the features in each layer. Okay, due to the limited space, we plot the features only on the first convolutional layers, the third one, the fifth one, and the last layer. So we can say that the last layer feature, which is a length slightly more than 4,000. Well, so here each feature mapping, they have different shapes. What we do is we reshape it to a 2-dimensional space, to a 2-dimensional image, so that we can plot them. Even so, we can't say so we can kind of like get much insight from these feature mappings, but there is a surprising phenomenon that in this feature plot, black means the pixel equal to, so black pixel means it has 0 value. So what we can observe is that if we look at the last 2, say, feature mappings, so I mean like in the like bottom plot, what we can observe is that most of the pixels actually say are 0, which means we have like sparse activations or we have sparse features. So okay, so this figure is actually obtained from the work by Mason and the collaborators. They actually, they also plot the average activation densities of each layer over like training. So for each layer, you can say from left to right or from the dark to light blue. It means from the initialization to end of training. What we can observe is that after training, actually, the features tend to be sparse, in particular in the deep layers. So for example, if we look at the last layer, the last feature layer actually, at the beginning, the features actually they tend to be very dense. They are not sparse, but after the training, actually, they become sparse. Here we can say only maybe slightly more than 35% are non-zero elements. The rest of, are non-zero elements, and the rest of them actually are 0. These sparse features also appear in other architectures like in VGG, Google Net, and SpaceNet, and many other architectures. These sparse activations also appear actually in like larger models, in the recent large models, and in particular, actually, the model become larger. That tends to be more sparser. That tends to be sparser. So let's look at a particular example of the transformers, which is one of the most widely large models. So a transformer, again, it contains a lot of layers, and each layer is corresponding to a transformer block. So within a transformer block, actually, it contains 2 components. The first component is called the self-attention layer, and on top of this one we have the MLP layer. So in this figure, we plot the features inside this MLP layer. Say right after so inside there's 2 layer MLP layers, and right after there's a relu unit. What we can observe is that, from the right figure is that most of them actually are sparse. So here, blue means non-zero elements and white means zero elements. So we can observe actually they tend to be quite sparse. Actually, only 1% non-zero elements in this feature mapping. This sparse activation emerges in different transformers and data sets. So as shown in the left top figure, which appear in from sufficient transformers to T5 encoders and T5 decoders, and also for both natural language processing and vision tasks. Also, it also appears not only on the training data points, but also on the testing data points as shown in the top middle figures. It also, appears in different data sets as shown in the top right figures. Also, if we increase the network depth, say if we enlarge the networks, then it tends to be sparser as shown in the bottom left figures. And also, there's sparse features not only on the well-labeled data points, but also on mislabeled data points as in the top, so as in the bottom middle figures, and also on random images as shown on the bottom right figure. This sparsity can be exploited to improve, say, the training efficiency, to reduce the computation times, and also to improve the robustness and calibrations. So in particular, so for example, so in the work by Zhongli and Tong, which is the previous figures are from these figures. So previous figures are from these papers on these transformers. So what they did is that they simply, keep the top K largest values in each layer. For example, we just keep the top 128 largest values in each layer, which is quite sparse compared to the size of each mapping. But if we look at the first column in the table, we can see actually there's no hurt to this natural accuracy. And by forcing the sparsities in each layer, the exact sparsity in each layer, actually we could improve the training, the accuracy or the robustness to the label noise, and also to the input perturbations as shown in the tables and also shown on the right figure. Okay, so which also plots the different choices of K and the different different level of corruptions. What we can observe basically is that by enforcing exact sparsity, actually we could have better performance. While this phenomenon emerges, but there is a lack of mathematical justification for the emergence of why this happens or why the feature turns out to be sparse. Well, I think the Professor Thomas Project's talk on the compositional sparsity may provide answers to this question. Okay, so far we have talked about the sparse features for each input. We look at the features, then we say, okay, they have a nice actual properties, like the sparsity. Now we try to characterize the features, or in particular, we want to say how the features learned in each layer will facilitate actually our decision tasks. So for classification problems, we want to know how the features actually are separated or discriminative across different classes. So in that sense, we will study the collective behaviors of the last layer features of all the samples and classifiers. So we will first focus on the features just in the last layer in the last layer features, and then during the end of the talk, we will briefly talk about the features in the shallow layers. So just to be clear, what do we mean by collective behaviors? So say we just input n cat images and dog images and other images from other classes into that network, and we look we take out all the features. Okay, so we have a bunch of feature vectors. Then we try to look at their properties. Then we try to capture lies their statistical properties or their distribution of these features in this feature space. Okay, so for like this goal, the recent work by Papier, Han, and Dorner, they conduct a lot of like experiments, and they reveal common outcomes of the learned features and classifies across a variety of architecture and data set. And indeed, there is a precise mathematical structure within the learned feature and classifies. And we call this properties as the neural collapse property. So this neural collapse refers to the following three properties. First, it's called the within class variability collapse, which means the features of each class will collapse to class mean with zero variability. Or in other words, if we look at the features for each class, say all the features corresponding to cat, they actually tend to be very close to each other. They will converge actually to its class mean features. Likewise, if we look at all the features for the dogs, they also corresponding to a single point. So now, if you think away, like all the features, actually we turns out to have k different features. So therefore, all the features they live on a low dimensional space. They actually live on a k dimensional subspace. The second property concerns the distribution of these k class mean features. Actually, this says they will converge to the so-called simplex equal angular time frame, which means that the class mean features are linearly separable. They have the same length, and they have equal angle between each other, and the angle is achieved as the maximum possible in the sense that the cosine of the angle actually equal to -1 over k minus 1, which means the angle is slightly larger than 90 degrees. Well, why you may imagine why this cosine angle is the largest possible, why we can't achieve each pair has larger angle, which is say 180 degrees. Well, it can't. So this is actually captured by this result, which says that if we have, imagine we have k unit length vectors u1 to uk in the dimension in a d-dimensional space, we assume the dimensionality d is relatively large, which means d is at least equal to k minus 1. Then actually, if we look at the angles between each other, which is captured by the correlations between each pair of the vectors, then the largest these correlations will be at least larger than or equal to -1 over k minus 1, which means we can make them smaller than this value. This problem is also related to the or known as the optimal packings on spheres, or the or like the tennis problem, which basically you can think of like we want to uniformly put like a k points like on the sphere. And okay, and here, because we assume the dimensionality d is is large enough, then this corresponds to the simplest case of these problems, which we have closed form solutions. Well, so to show that result, we can simply use the following argument. We look at the sum of these k vectors, and we look at its energies, so like in terms of the square of the L2 norm, which we can expand it as k, as k squared in the product between each pairs. By like this simple argument, we can show that the maximum correlations between any pair will be at least larger than or equal to -1 over k minus 1. And we can show that this equality can be achieved only when first say the mean of this k vectors equal to 0. Second one is that each pair has the same angle and the cosine angle equal to this value. The third neural class properties refers to the distribution of the class weight vectors. So the classifiers in particular, actually, there is a well alignment between the classifiers and the class mean like feature vectors, in the sense that if we look at each row of the class, so I mean of the classifier with the metric W, then it points to the same direction as the corresponding class mean feature vectors. So, so this well alignment means that there is a self-dualities between this class means and this classifier with metric W. So this neural collapse property is preferred among every successful exercise in feature learning from the following two perspectives. From the information theory perspective, if we think of these features as the codings for the input, then this simplex ETF features actually is optimal sharing code because they have the largest possible distance between each other. From the classification perspective, the simplex ETF features actually will lead to the simplex ETF maximum margin classifiers. Okay, so because each class has the largest margin to the decision boundary. Well, even though this neural class property is preferred, a natural question is that we always train the network by iterative algorithm like by gradient descent. Then why these iterative algorithms will learn these low-dimensional neural collapse features and classifiers? So to answer these questions, we will use tools developed in the non-convex analysis presented by Yuqian to understand these neural collapse properties. Now let's come back to our training problems. And we mentioned before that the network is contains two parts: a feature mapping and a linear classifiers. And we learn both feature mapping and the linear classifiers by minimizing cross entropy loss. However, this problem is usually highly non-convex and it is hard to analyze and even to prove its convergence to global minimum. Well, the neural kernel analysis can guarantee that if we minimize the training error, if we minimize the training loss, the training error will converge to 0. However, we know that the neural kernel corresponding to the lazy training, which is different to what neural collapse will like predict actually. So here we will exploit another perspective and we will use another way to study these problems by studying a simpler, like a simplified problem. So motivation is that recall that this neural collapse is only about the learned classifiers W and the features. Therefore, let's feel these features as free optimization variables, which is called the unconstrained feature model, which means that let's assume the features can move anywhere in the feature space. Then if we minimize this cross entropy loss, what are the features and classifiers we will get? Well, aside from simplifying the analysis, the rationality behind this unconstrained feature model is that modern networks are highly over-parameterized, that we can approximate actually any point in the feature space, which means that the features actually can move anywhere for any input. So this is also called the layer field model. So we will use this simplified model and we will show that this simplification actually will preserve the core properties of the last layer classifiers and features, which in particular, we will show that we observe as neural collapse phenomenon. So in the recent years, this neural so these unconstrained feature models have been used to understand that. To understand that neural collapse properties. Based on different setups. So for example, the work shows studies the one example per class, which means that we assume each class has a single training sample, and there is no weight effect, and we only assume the features live on the unit sphere, and then we look at what features we will learn by minimizing this cross entropy loss. Or other works will study this constraint formulations where we like restrict the classifiers and the features within a certain region, say within a unit of ball, something like this. Well, for all such works shows that any global solutions actually has nucleus properties. But what about the local minimum or saddle point in particular? This problem actually is a non-convex problem due to the bilinear structures within the weight. Within the weight metric W, and the classifier is H. And also the constraint formulations actually are not aligned with practice. To address this issue, so we will study this cross-entry loss under this uncontrolled feature models with this weight decay regularizers on both the features and the classifiers. This problem actually is closely related to the metric factorization problems presented in the previous lectures. So we will use the tools there and to study its global and local minimums and saddle points for overtraining problems. Let's first look at the global optimality solutions in particular. So our first result says that if the feature dimension is relatively large, and again, D is larger than or equal to now the number of classes K minus 1, then any global solutions to such training problems must satisfy nucleus properties. So in particular, the bias will equal to 0, and the features will collapse to a single point for each class. The features between each, the class mean features between each pair has largest possible angles, where the cosine angle equal to negative 1 over K minus 1. And the class, and then the classifiers are well aligned with this class mean feature vectors. So again, here D equal to larger than or equal to K minus 1 is required to ensure the simplex ETF solutions, actually, as we mentioned before. So we know in the previous lecture said for a general non-convex problem, which is the case here, we not only have global solutions, we could also have local solutions. And we could also have a very flat saddle point, which means if we run gradient descent, we may easily get stuck at this point. Fortunately, for overtraining problems, actually we can show that the problem has a very benign landscape. In particular, it has that any local solutions actually say are global solutions, they have such nucleus properties. And any critical point that is not a local minimum, indeed it is a straight saddle with negative curvature, or if you remember, it means that if we look at the Hessians of this overtraining like functions at this point, it actually has negative eigenvalues. So that means that if we run gradient descent, you will easily avoid those points. All right, so now let's briefly talk about how we establish our global landscape analysis. So the proof idea is that, as we mentioned before, this non-convex problem actually is related to the metric factorization problems, and we can further relate one to convex problems. In particular, if we let W multiplied by H as a new variable which is called Z, then we can show you that this non-convex problem actually will be related to the following convex problem in terms of Z and bias vector V. And then the weight decay in terms of features and classifiers becomes the nuclear norm, or in terms of Z. So here the nuclear norm means the sum of singular values. So the first step we will show is that these two formulations, the original non-convex one and the convex ones, actually they have the same global solutions, in the sense that if say HWB is a global solution of the original problem, then W multiplied by H and B turns out to be a global solution of the convex problem, and vice versa. So the main idea is that if we look at the nuclear norm, which is the sum of the singular values of Z, actually this can be related to the weight decay of the factors W and H, Well, for any Z, we know we could have infinite many possible choices of W and H, such that CR multiplication equal to Z. But if we found the one which has the smallest energies for W and H, then its energy actually turns out to be the nuclear norms of Z, which is a very original form. So using this result, it's clear that if we minimize the non-convex problems, which kind of like minimize the weight decay in terms of W and H, it seems we are minimizing the nuclear norm for the convex problems in terms of Z. So second step is to prove the benign global landscape. So for this one, we will look at a critical point, which is not a global minimum of the original non-convex problems. Then, because it is not a global minimum, then Z, which equal to W and H, then ZB turns out to be not a critical point to the convex problem, because it is not a global solutions of the convex one and the convex one. If any point is not a global solution, it must not be a critical point, which means that this point actually does not satisfy the first order optimality conditions for the convex problems. Then by exploiting these properties, we can show that the hashing of the original non-convex problems at this point indeed has a negative eigenvalue. So therefore, this point is a strict saddle. Since the second step holds for any non-global critical point of the original non-convex problems, which basically says that the original problem has a benign global landscape, which means any critical point is a global solution or a suicidal with like a negative curvature direction. Therefore, if we combine these two results together, the global optimality and the global landscape, and then global landscape, then basically like following the like results we learned in the previous lectures, we know that because of this benign global landscape, if we run iterative algorithms like the gradient descent, you will almost surely actually you will converge into a local solutions, which turns out to be a global solution, and which turns out to have the neural collapse properties and classifies. Well, now we will conduct experiments with the practical networks, not on this uncontrolled feature models, to verify our findings on the later model. So we will use residual networks on CFR10 dataset, so which has 10 classes, and each class has 5,000 training images and have 1,000 testing images. Since we have shown benign landscapes on our simplified training problems, which means that if we run any local search algorithm, you will almost surely find neural collapse solutions. So now let's verify this one on predict networks. So in particular, we will train the ResNet 18 by different training algorithms, including the first order algorithms, SGD and ADAM, and Quasi-Newton algorithms, LBFGS. So here we plot the learning curves in terms of 3 neural collapse measures. The first, the left one plots in terms of the within class variabilities. The second one plots in terms of the between class separations, or how they close to the simplex ETF. The third one captures how like alignment between the classifiers and the class mean features. The smaller of these quantities means the severe neural collapse. Since we will use the first measure very often in the rest of the talk, let's give the formal definitions of the first measure. So this first measure, it captures the trace of the covariance matrix, the within class covariance matrix multiplied by the inverse of the between class covariance matrix. Well, so the within class covariance matrix, it basically captures the variance between each class features, actually how like each class are aware from the class mean features. So this you can think of as a noise term. So between class covariance matrices, it kind of like captures how separated the class mean features. If they are well separated, then this between class covariance tends to be large or somehow to be large, even though it is a metric. So therefore, this NC1, it captures actually how the features are collapsed and separated. If they are small, means the features are well collapsed and well separated. So with this, so here's the three learning curves which we showed before. Basically, I mean, like indicates that for all these three training algorithms, we always observe this neural collapse properties. So which means this neural collapse will across different training algorithms. Now let's see how this neural collapse depends on the training samples. So here we use the same CFR10, but we use a random labels, which means the labels are totally wrong or like not correct. Actually, we kind of like do a random shuffling for all the labels. And so here in the first in the left figure and in the middle figure, we plot the learning curves in terms of the within class variabilities and the self-duality collapse. So in each figure, we have different plots which correspond to different network widers. So from the top to the bottom, we increase the network widers actually from 8 to more than 2,000. So from these two figures, we can observe that as long as the network is wide enough, actually we will always observe neural collapse properties because they converge to zero. And well, so this is result on the random labelings. We also observe similar results actually on random inputs, which means each pixels are random. So on the right figures, we plot the learning curves in terms of training error. So we also say that we will achieve zero training errors. So which, as we know, that the network will memorize training data, but it actually tells us it will memorize in a very special way, which means we have neural collapse properties. Well, so these neural collapse are so common, and the previous work by Papi and Donald actually shows that this property actually will lead to better generalization performance and robustness. We can also exploit this neural collapse actually for many other purposes. For example, to improve the training efficiency and memory cost, to understand the effect of loss functions, or to understand the transferabilities across different tasks. Okay, so we have seen that we always observe neural collapse across different training algorithms, different data sets. Then you may wonder why we need to learn like a linear classifier, because it will always convert to a simplex ETF. Well, actually, we don't need to learn the linear classifiers. We can just fix it as a simplex ETF. It could save us a lot of parameters, actually range from 8% to more than 15% for different architectures. The second one is that what about the feature dimensionalities? In practice, we usually use a very large dimensionalities, say feature D equal to more than 2,000. But here, our results actually shows that we can just use feature dimension D actually equal to the number of classes K, say K equal to 10 for CFR10. Actually, we will obtain the neural collapse properties. So this actually could first save a lot of parameters, because the last layer is, because the linear classifier is a fully connected layer. So here we conduct experiments on less than 15 on CFR10 with different setups. So in the plots, if we look at the left figures and from the top to bottom, the first case is corresponding to the standard one or the default one, where we learn the classifiers together with like the feature mappings, and we use the feature dimension D, which equal to more than 2,000. And then the blue curve where we fix the classifiers, and the green curve is that we reduce the dimensionality to 10, and the red one is that we both fix the classifiers as a simplex ETF, and we reduce its dimensionality to 10. And the left figure plots the learning curves in terms of the neural collapse. What we can observe is that from the blue curves and the red curves, which correspond to the fixed classifiers, actually we have, we have a severe neural collapse. Well, which is not surprising because we already fixed them as a simplex ETF. What's interesting is that if we look at the middle curves and the right plots, which is the learning curves in terms of the training accuracy and the testing accuracy. So if we look at them, we can observe actually at the beginning, the red curves actually were converging factor, which corresponded to fixed classifiers and small dimensional features. And eventually we can say after training, actually they have identical performance. They have same training accuracy and same testing accuracy. So this actually tells us that the training with small dimensional features and fixed classifiers actually achieve on par performance with the large dimensional features and the learned classifiers. This is in contrast to the NTK theorem, which will require the feature dimensionality relatively large enough. So far, we have talked about the learned networks, based on the cross-entropy loss. So is this essential to the neural collapse? Or in other words, what about we use different loss functions to capture the network output and the one-hot labels? And indeed, there are various losses and tricks that have been proposed in the literature to improve network training and performance, and we will give several examples of them. So here is the so-called focal loss, which will put more focus on the hard examples by reweighting the cross-entropy loss. So here PT is network output probabilities for data class. So if PT is small, which means the sample is misclassified, then we add a relatively large weight. On the other hand, if PT is close to 1, which means the sample is well classified, then we add a small weight. So by doing this one, we will put more focus actually on the misclassified samples. So, or if we look at these figures, if we look at the left-hand side, that's 2 points. So there's the light one and there's blue one. So if the probability is small, which means it is misclassified, then there's a green point, which has a much larger gradient than the blue curve, than the blue point. Okay, so another one is another common loss is so-called label smoothing. So the idea is that label smoothing, in label smoothing, we use a soft label, which probably we can say that, well, previous one we say we label the samples by 100, which means 100% is equal to a cat. Label smoothing says that, okay, let's not be so sure. Let's give some uncertainties for the label for the samples. So we will say, okay, now we will label these samples by 90% as cat, 5% by dog, and 5% by these pandas. Okay, so here says alpha, which captures the uncertainty you can think of. So this is called the soft label. Then the label smoothing, then we use the cross-entropy loss to capture the difference between the network output probabilities and this soft label. Another loss, perhaps the simplest loss you would imagine is the mean squared error loss, right? We don't involve any, say, soft max functions. The network output is 1, 0, -1. I just compare this to the one-hot label vectors, and then we look at the difference for each output, and then we sum them, and then we just use this as the loss functions. It's interesting that compared to cross-entropy loss, this mean squared error loss or its variant actually produce on-par performance on various computer vision tasks and the natural language processing tasks. So now a natural question is, which loss is better to use? If we look at the literature, we will find we may even get like opposite like conclusions in different papers. Some papers may claim that level smoothing is better. Some papers may claim that cross entropy has better performance. So here in this table, we train the network with different training losses. So the 4 training losses we mentioned before, and the 2 different setups. So first, the law corresponds that we reduce the network width by 1/4, and we change the network by 200 epochs, which is a common choice. And in the second law, if we have enough resources, then we use a large network. We double the network width, and we change the network longer by using 800 epochs. So what we can observe is that if we look at the first law, we can say that, well, cross entropy loss is better, and it has better than MSE, and with 2 points better, actually, two points better. Well, if we look at the second law, by increasing the network width, actually they achieve all the performance increases, and they achieve similar performance. Actually, the gap become much smaller among different loss functions. So this actually implies somehow that all these losses will lead to largely identical performance when the network is larger and the chain longer enough. So to study this, so we will look at the uncontrolled feature models for different loss functions L. So we will study the loss functions under the so-called constructive properties. So it says that it basically refers to the following 2 properties. The first one is that if we look at the loss functions in terms of the case classes, it can be lower bounded by a new scalar function per se in terms of the difference between the case output and all the rest of the, and all the rest of the output. And it achieves the equalities when the rest of the outputs they are equal. The second one is that if we try to minimize these scalar functions, then its minimizer is unique and its minimizer is like negative. So the intuition behind these 2 properties is that for the first one, we want to contrast, the case output simultaneous to all the other outputs. And the second one is that we want that the minimizer has the case output being its largest entry. So therefore, we have, a correct prediction. And okay, so under these properties, so for like these properties, we can show is that the loss function we mentioned before, cross entropy loss, focal loss, and the level smoothness all are satisfied. Then we can show that with the feature dimension D is larger than or equal to K minus 1, then all the losses with these constructive properties will lead to the same global solutions. In other sense, they have the new collapse features and classifies. So this, together with the previous result on the mean squared error loss, will tell us that all the one-hot labeling-based losses we mentioned before, indeed, they will lead to the same neural collapse features and classifies. Well, even though this result is established under the uncontrolled feature models, it somehow implies that if the network is larger enough and the chain longer enough, then we may get largely identical features on the training side, on the training data points, the neural collapse the neural collapse phenomenon. And moreover, we will use experiments to verify that actually all these losses will lead to largely identical performance on the testing samples. Now we conduct the experiments with less than 15 and using different training losses. So the most left figure plots the learning curves in terms of the within class variabilities for these 4 different training losses. And we can observe is that if we train longer enough, they all converge to the neural collapse features. The middle one and the right one plots the learning curves in terms of the training accuracy and the testing accuracy for these 4 losses. And we can also observe that actually they lead to largely identical performance. now we study the performance and I mean like different setups with different network widers and training epochs to say the performance of different loss functions. In each table from the bottom to the top, we increase the training iterations from 100 iterations to 800 iterations. And from left to right, each time we double the network widers. Now, if we look at the left bottom like cells for in like each table, we can say that we do see some variabilities among each like loss functions. However, if we train longer, then the performance will become better. And if we increase the network widers, all the performance will be increased. Moreover, if we just look at the right top corners in like say 4 tables, actually, first we can observe they are much better than the left bottom corner. Second, these 4 values actually they have very small values, which means that by increasing the network widers and chain longer enough, all these 4 loss functions actually they lead to largely identical performance on the test samples. Okay, so far we have talked about the learned features and classified. I mean, for the features, we mean the last layer features. And we have shown that there is a neural class properties, which means that the features, they are well separated and they are well concentrated. Now, a natural question is like that, if for the input, they are not well separated, they are not concentrated, how does these features are like this separated or like collapsed across each layers from the shallow layer to the deep layers? We can capture these progressive separations by the same neural collapse properties or by the neural collapse measures, which we mentioned before, which captures the like ratio between this within class covariance and the between class covariance, and the smaller, the more collapse. Here we plot a well-trained network and we plot its I mean like neural collapse across the layers. So from left to right, it means from shallow layer to the deep layer. Actually, it means each, I mean like residual block. So what we can observe is that from left to right, actually the layer-wise training curve, it has a very surprising phenomenon. It kind of like has a geometric decay, which means that there is a progressive separation and concentration among these features across the layers. So Professor Wei-Jisu's talk I think will talk more on like these aspects. Now, now a question is that how this well separated or how this progressive separation and collapsing will be transferred across different tasks or across different data domains. So here we try to numerically verify that this progressive separation is actually robust to the distribution shift. So here we pre-trained a ResNet on CEFA 10, and then we fix it, and then we evaluate this layer-wise neural collapse on the original CEFA 10 training samples, testing samples, and the CEFA 10.2 testing samples. So this CEFA 10.2, it has the same 10 classes as CEFA 10, but it has different actually training samples. So in the right figures, so here there's solid curves corresponding to the residual 18, and the dotted curves corresponding to the residual 34. And this, if we look at say if we look at it, so if we look at the solid curves from the bottom to top, it corresponds to the CEFA 10 training samples, the CEFA 10 testing ones, and the CEFA 10.1, CEFA 10.2 testings. So we can observe is that all these 3 curves, they have similar trend of progressive separation and collapse. Okay, and the second one is that the red curves actually say are slightly larger than the blue curve, and also the green curves, which means that distribution actually will, so that distribution shift actually will cause slightly less collapse, and which will turn out to give, like slightly worse performance. Now, okay, so let's briefly talk about how this progress separation actually is transferred among different tasks. Again, we will use one example to illustrate this point. So we take a ResNet 13.4 pre-trained on ImageNet, which has 1,000 classes, and then we evaluate its its layer-wise neural collapse on CFR10, which is plotted by these blue curves. So remember that this model is fixed without fine-tuning. And then we will train a linear classifier on top of the features to look at its transfer accuracies, which is shown by these red curves. We can observe is that actually there are two phases in this layer-wise neural collapse on these downstream tasks. The first phase, which is from the first layers to the 11th block. Actually, we do observe this progressive decreasing actually on these neural collapse measures, which means that the first 11 blocks kind of like as a universal feature mapping, which can be used to progressive separation and collapsing. And then the second phase, after the 11th block, the neural collapse actually becomes increasing, which means that the pre-trained network actually, this part actually is specific to the particular data set, the ImageNet. So, okay, so this actually tells, implies, why projection height is widely used. It can actually help improve this transferabilities. And this result can also help us to develop efficient fine-tuning to improve transferabilities, and the team will talk more along these directions. So to summarize, so in these lectures, we have talked about two perspectives, that either from the individual perspectives or from the collective perspectives, where the low-dimensional structures will emerge in the learned features. So to summarize, in both, in the same lecture and in these lectures, we have talked about learning the common deep networks for the low-dimensional structures, either for low-dimensional data points or for low-dimensional features in several aspects. So in the next lecture, E will talk about a new approach actually for learning discriminative but diverse neural collapse features. And based on this, E will talk about designing deep networks architectures for low-dimensional structures. Okay, so thank you very much for your time, and I will be happy to take any questions you may have. Enjoy the workshop.
We'll hear from, thank you. Next up, we'll hear from Professor Yi Ma, telling us about designing deep neural networks for low-dimensional structures.
Hello, can you hear me? Good. All right, I'm gonna try to. Oh, I need the. Yeah. Sure. All right. I hope everybody's enjoying the. I know it's. Shoot. Should I stay away from there? So as I think just while things are setting up, just trying to remind you, right? We have to go from the morning that John has done a very good job motivating in many of the from scientific engineering or the natural high-dimensional data has a very, very important things are very low-dimensional structures. And it connects to some classical theory, right? How do we, in a very, very, in a nutshell, in a very idealistic model, try to solve inverse problem from the measurements to recover those low-dimensional structures, right? The classical theory from compressive sensing, from signal processing, and actually capture the essence of that. But those theory has been very much at the very foundation, the core of all the problem we're dealing with. But it is making, because of that, but actually making it very simplified. Idealistic assumption is that the structure of the data is already linear, right? Either it's k-sparse, piecewise linear, or is low rank, right? And also that even in those cases, the problem, the structure of the data is linear, but the meaning of this problem, try to solve those inverse problem, the formulation could still be non-convex. That's Yu Qian in the second lecture has talked about it. Progressively, like in the case of Sam and also in the case of Zihui, we just heard, is that the first fundamental role, right? Why this empirical success of deep neural networks in the past 10 years, right? In many of the practical data, like images, natural languages, or speech, and so on, it's actually precisely one of the messages we're trying to convey is that still, very importantly, they try to capture the low-dimensional structure of the data. Nevertheless, the data may have nonlinearity, right? They're no longer as simple, as idealistic as piecewise linear or piecewise or like a low rank or sparse signals. So this is something that we try to put together, right? In the past 10 years, we've seen tremendous empirical and inductive approach to practice gazillions of variants of neural networks. Many, many tricks, many, many phenomena, many, many understanding, right? Including the, Sam's work, and also Zihui has talked about different aspects of either the network architecture from statistics point of view, from optimization point of view. I've seen those. So the question is, maybe it's time, right, after 10 years, after we have seen all these pieces, maybe it's time we probably have to do a little bit of integration, try to understand things from more deductive perspective, right? Can we have a sort of framework, try to unify all this, integrate all the observations, provide a unified assumption, a unified explanation to all this. So this is kind of the effort with, my research group and also with the colleagues, John, and also many colleagues here have been embarking on in the past few years, right? Today we're trying to present some of our discoveries, try to connect again some of the historical pieces, views, and also try to integrate under a more unified framework. So, how do I go back? Sorry. Yeah, this is kind of, we're trying to give a little bit of precursor, some of the motivations. I think one of the things this tutorial, probably different from others, we try to really try to understand what is the right problem we're trying to study, right? I know it's a mouthful, it's actually mindful, right? There's a very intense messages. It actually connects to many, many subfields. And also there's like hundreds of pages of books, probably have to digest. But hopefully, we try to give you the right motivation so that you know what is the right question to ask, what the problems were, right way to think about those problems, right? Then you know the doors to the right approach to this problem. So I'll give a little bit of precursor, I'll give you a little bit of examples of why motivate us, and maybe it's useful for you to understand, right? And then we'll try to make an attempt, can we actually unify things from a very deductive point of view, right? Making very simple assumptions, very unifying assumptions, so that we can maybe we can derive everything from scratch, right? Show the power of deduction. And not only just make the objective clear, but also make the network architecture clear, right? Everything become transparent. Is that possible? I mean, not just object function, the architecture, each layer, even every single parameter. Right? Leave no stone unturned, right? So that's actually, can we do that? And also the most important thing, right? Many, many things, were frustrating with theory the past 10 years. Yeah, maybe you can explain a little bit of things, right? Chasing practitioners' tales, I would call that, right? I mean, we can explain, this is what they do, maybe this trick's the reason why it works. but somehow can we impact practice? Can we say what they have done not good enough, right? Go way beyond what they can even imagine with the practice. So that's where we're going with a good. If we have a good theory, we should be able to do that. So let's just start with some motivating examples, right? What motivated me to connect, to look into, like John and we started looking at why there's a connection between neural networks and sparsity or low dimensionality, right? We didn't start it. Actually, Yang Kuhn started it, right? Before the neural network, deep network was even popular at all, right? So we all know, right, that this algorithm, John has talked about a lot, right? We try to solve a sparse solving of y equal to ax. This is a very simple problem. X is sparse. I mean, the algorithm to solve this is a classical algorithm, right? Solving the lasso problem. And the algorithm solving this is actually very simple, right? Take the gradient descent and take the iteration. This is gradient, and then we do soft thresholding to find a sparse solution. And this is algorithm. This is a way predate neural network, right? But if you look at what this algorithm is doing, each step take a gradient, which is a linear operator, right? And then do a soft thresholding. And look at the function, right? The soft function. And now if you compare this to modern neural network, this is exactly the kind of meta structure neural network has. Linear operator plus some nonlinear thresholding. It even looks like, right? And there's no surprise. This is the work around 2010, before neural networks, right? This Yang Kuhn already recognized there's a similarity to the algorithm to pursue sparse solution. Just looks just like a neural network, right? Then, of course, the algorithm actually unrolls it to just do the gradient descent, right? It said that if I just fix number of iterations, maybe the gradient descent may be not good enough. What I can do is that I can actually change the parameter per layer, making those here, sorry, oh shoot, I'm just clicking in the wrong direction, right? So here the linear operator, each layer is already fixed by the known dictionary. But what if it's not good enough? I can fine tune it. Nobody can stop me from doing it using backpropagation, right? I just fine tune them with a little bit. That makes the algorithm solving the sparse solution much, much better, it turns out, right? So in fact, he actually interpreted this, the algorithm, classical algorithm to solve sparse solution as a neural network. Right? We're going to do the opposite. Right? Another example actually motivated me is that, remember, this has been a recurring problem, right? We try to find a transformation. This is the holy grail for signal processing problem, right? We have some many data. Why? We try to write down a transformation equal to AX. Here, I consider A is the orthogonal transformation. I ignore the A transpose just to be consistent with my notation, right? So basically, A is a square matrix, and the Y is equal to A transpose X. It's similar to the problem we're dealing with in the morning, just notation-wise. So the point is that the whole holy grail of signal processing is always trying to find a transformation such that the structure in the data, observed the data Y, revealed itself, right? It become very sparse, become very low dimensional. So you can think about this classic example. A is just a Fourier transform. If I have a, audios, low bandwidth, right? The band limited signal to a Fourier transform. Wavelets, A could be wavelets, right? So now the question is about, of course, in the data-driven approach is what if I don't know the analytic transformation? I wanted to learn from the data. I just want to find among all transformations, all orthogonal transformations, which one gave me the most sparsest solution, right? This is. Now, interesting thing is that, right, today, the Yu Qian and also that Zihui has talked about this. There's a nonlinear formulation for this problem. And turns out there's actually a very interesting dual problem, right? We were trying to make the x zero, the zero norm of x small possible. Of course, you can replace zero norm with a one norm. Right? But regardless, it's still a binary problem. It's still a non-convex problem. Even you replace this, convexify this object function. Turns out, since you are dealing with a non-convex problem anyway, you don't have to, solve on just using one norm. Turns out, if you restrict all the features on the sphere, right? So minimize the zero norm is actually equivalent to maximize the four norm. Right? So you can think about the for norm is kind of dual to, but it's maximizing the for norm, minimizing zero norm. So it's kind of interesting with geometry. Now, so if you do that, if you just say try to maximize the for norm on the sphere to look for the optimal the diction transformation, that also will sparsify this. So if you do this, if you take the gradient descent, just do very simple gradient descent on this, right? I hope we sold you the idea, right? If you have a long convex optimization, don't be afraid of just using gradient descent. Actually, some magics will happen. In these cases, it actually works very, very well. This gives you some of the most effective, still probably by far the most effective. Just do the gradient descent on this, right? And yet, this simple gradient descent algorithm actually has a very interesting interpretation, right? It's actually trying to apply, every iteration is just to apply the orthogonal transformation on the data, remember, just computing. If you're computing that increment, every gradient descent, you just apply the little bit of rotating your data, so to find and make the data more and more sparse, right? So you naturally get a deep network. It's actually concatenation. Each operator, each layer, each iteration only depends on the feature already transformed. Has nothing to do with the original data, right? It already gave you from the original observed Y. You just apply a sequence of orthogonal transformation. Eventually, it will give you the optimal transformation, optimal representation. Right? And if you look at the way to compute each layer, each delta R, it's exactly a linear transformation plus a nonlinear threshold, right? And in fact, this is not unique. This is not the special. Turns out this is exactly corresponds to how people computing using power iteration to computing eigenvalues, eigenvectors. And also how people use this to compute ICA, right? This is a fast ICA is proposed by the guy called Abel Havanari. The guy actually proposed the score function for diffusion models. Right, it's the same guy. Actually, he did the score matching function precisely to compute ICA and for dictionary, not for denoising, because that's too simple. Right? This is actually a much more important problem to do. What I'm trying to say is that this is a sort of give you a little idea, right? Seeking the sparse representation is exactly the idea, the reason why we see deep networks, why we see the kind of structures. This is another work we did a long time ago, right? We call it PCA net, right? So there's a lot of learning we try to do. We build a neural network, we do backpropagation to tune it, right? Fine, if you have a lot of GPUs, but turns out we should understand what really each layer is doing. Can we ask that question? What each layer is making things better or worse, right? This is my first attempt to neural networks, right? At that time, everybody is saying, oh, we want deeper, bigger, wider, right? So at that time we asked the question, then can we justify that? Right? Can we do a simplest deep learning baseline for image classification? Right? And we build, but what about we just do the simple PCA? Each layer just do patch, image patch, do a PCA. Learn the filter, convolution filter. Build this in the most simple way. Everything's feed forward, absolutely no back propagation. The network doesn't even know what the task is, okay? Just do PCA for the inputs. Build the filter, right? And each layer is actually the nonlinear threshold in just the binary. This is the simplest network you can imagine, right? 2 layers, 3 layers. By the way, you can even replace each layer, the PCA filter, with a random filter. We call it a random network. This is 2013 or 14. And the surprise thing is that this actually gave you a state of art at that time on all the face image data sets. Of course, we couldn't publish this paper for 2 years, right? It gets rejected because people think deep network is everything, right? The simple network like this, why should it work? No. So eventually we published it in the journal. And we'll loop back to this, right? So this is actually ancestor to something quite remarkable. Right? By the way, you can actually replace all the filter with completely random filters. You only draw percentage by 1 or 2%. There's something very, very interesting going on. Now, transformers, right? As Sam Zihui also mentioned, right? Transformer. What transformer is doing? Very simple. Some attention head, and then with some, residual block, and this attention head. It's computing the autocorrelation, right? You can see that if you see the layers from early layers, the representation is kind of dense, but eventually actually becomes very column sparse. That's another feature. It sort out the features, try to make it linearize those features. Right? This is empirical observations. Right? It does something very interesting. Try to organize the data in some way. Right? We'll see why this shows up in a second. So all these pieces, different things, like you are solving a big jigsaw puzzle. So what they're really trying to do, right? You see, right? So then can we just do things from a very deductive way, right? If we do that, right, those are the two pillars of modern science. One is inductive, one is deductive, right? We've been doing that for thousands of years, but they actually help each other, right? So for example, we want to derive everything from scratch. So let's just can we just agree on the minimal set of assumption, right? We're dealing with many, many classes of data. Let's imagine ImageNet, right? Thousands of classes, objects. Then each class may have some structure, right? Apple, orange, the set of images, you can have gazillions of images of an apple, but they must be similar to each other, right? They lie on some very low dimensional structures. Right? Imagine each image is a million pixel, but the set of apples maybe lies on some, in that million dimension space, this is just some 5 or 6 dimension manifold, nonlinear manifolds, like maybe not a 1 dimension, but maybe some fixed number of dimensions. And also, we are making assumption that the apple and orange can be separated, just like Sam also illustrated with the model problem with 2 curves, right? They should be separable, right? But of course, in the real data, maybe the dimension is not a 1, but a multiple, and then but they are separable, most of them, right? You may not know how, but they are separable, right? That's why we can tell apple from oranges. Now the question is, what do we try to learn? Ask you, it's a very simple question. Fit the label, do the things, generate a model. To think about it, right? So our memory is trying to remember, right? What do we try to learn? Doesn't matter a machine or an animal or a human, right? Maybe we can agree on is that maybe we try to sort things out, right? Doesn't matter we do this for classification, for generation. Our memory we try to find some kind of very compact and structured representation of the data. Right? In fact, that's what the deep network started with, right? We try to map all the blue curve, for example, right? All the points on the blue curve to something like one hot, like we just talked about, right? This collapse into this one singleton neural collapse, right? And also, how do we do this? You try to optimize the cross-entropy measure, right? Make sure the output of some network, of course, this is a very complicated map. We already know for many, many years, people don't know how to build this map. But of course, neural network says, well, let's try some neural networks, right? Then we can train this, make sure, enforce the network output match with the one hot label, right? Again, this is a way to seek to transform the data so that the data has structure, right? Force the data to fit this kind of structure, simple structures, compact, very simple structures. Of course, Zihui has illustrated this very well, but this, eventually leads to neural collapse with good or bad things. We'll see that. But there's some elephant in the room, right? As Zihui says that if we choose a network too complicated, this guy can't fit anything. You can, randomly shuffle the data, randomly shuffle the label, you can fit everything, right? And it's actually not, just as Sam also mentioned, it's not actually even guaranteed to be robust or even invariant to transformation or deformations. There's a lot of things we strap under the rug, right? For 10 years, we have headlines, how wonderful they are, but there's a lot of bad things gets, ignored, acknowledged, especially for understanding, right? We sort of cherry-pick the results without guarantee that. The question is, I probably couldn't care less. Is actually, I care more is about what the network what the machine has really learned, right? Can we explain that? Just be able to fit the label. It doesn't say anything about the data, right? Because the label can be arbitrarily assigned. The network still can fit it. So what the network is trying to do? So there has been some existing theory trying to explain, right? So maybe, and this is the information bottleneck came out early on, is trying to say, but maybe what the feature mapping F is trying to do is try to extract some features that really match the label you care about. Well, if the label is what you care about, this may be the right thing to do, right? You wanted to find out the feature that is in terms of information, right? The mutual information between the feature and the label are maximized. And you throw away in the data whichever is irrelevant to the label, right? You minimize the mutual information between minus the mutual information to XMC. Right. This actually was celebrated as one of the ways to explain deep network, what the deep network is doing. But in my view, this is exactly the wrong way. Why? Do we care about the label or do we care about data? If you care about label, great, that's what you care. We care about data. What we learn is X, right? We want to understand what the X is, right? So this may be able to explain a little bit about what classification is doing, but it's definitely not helping me to understand what I have learned from the data, okay? The label can be arbitrary. But actually, there's a bigger elephant in the room. It's not just a formulation, not just what you want to do. What is the question? What can you do, right? It's a computation. You can, of course, you can write down, oh, this may be something I'm optimizing, the mutual information and between labels and this. The question is, can I compute this? If this is something I'm doing, must be able to evaluate it in terms of those things, right? Turns out that when you're dealing with data in a very high dimensional spaces, especially those distributions are degenerate, those almost all the entity, right? You saw very popularly, almost every NIRPS paper start with, let's talk about entropy, let's talk about mutual information, let's talk about Kell divergence, Jensen-Shannon distances, right? And the maximal likelihood even. None of them is even well defined. Let alone, even they are well defined, most of the quantities are intractable to compute. Right? Then you should ask yourself what the heck you're doing. All right, computationally. If you cannot evaluate those things. Of course, why there are 10,000 papers? Everybody approximate. Propose different way to approximate. Sample, lower bounds, different surrogates, right? Everybody claiming my approximation is better than yours. See, it works better on those examples, right? Keep doing that, right? We're just pretending we're making progresses, right? We're not. Not conceptually, not computationally, right? So this is actually questions that if you write down all those comparative concepts, you cannot even evaluate them, right? It's hopeless to compute them accurately. Then can you guarantee anything at all? Especially computationally, you cannot. By the way, this is not an old problem. This is not a new problem. This is exactly the problem. Renee, he's not here, probably jet-lagged. Right? Renee and we went through about 15 years ago when we were doing image segmentation classification. Right? Because even you assume your data lies on the subspace, even it's linear, that is non-linear, right? Even on linear subspaces, right? You cannot avoid those problems. Almost all the classical information theoretical statistics formulation, they become degenerate or ill-posed. Then computationally, none of them work, right? So we actually struggle with, we actually wrote a book about the generalized PCA on the whole subject. It took us about 10 years to sort things out a little bit, right? We tried everything, right? Fine, for example, how to do clustering. For example, we assume our data lies on multiple classes, right? Each one on some subspace. I'm not even talking about manifolds. Think about even simple case, subspaces, right? Well, everybody's very, very, arrogant. It's very simple. How do we do clustering? How do we classification? How do we do clustering? Well, you model your data. This is a multi-class. You model as a mixture of some mixture of distributions. Write this down. You run EM algorithm, right? By the way, in 1990s, that's what the Hinton works on. Okay. Everybody write that. This is statistical 101, right? If you take a statistical courses, the people teach you how to do this, right? But if you're dealing with high dimensional data, like images or text, speech, right? This is not defined, okay? If the support of the distribution is singular. And why are you doing this then? If it's not even ill-defined, you cannot even evaluate. Even this is defined, even if it's Gaussian. Evaluating this, sampling high-dimensional Gaussian is a nightmare, by the way, right? So why are we doing this? So at that time, we actually really struggle with this. We cannot even segment images, right? We cannot do the empirical. Of course, you can approximate. Of course, you can do empirical things. You can hack, right? That's what people do. But then the question is, can we do this in a slightly more formulated way, right? More formal way. So that's one thing we actually realize that maybe you have to deal with this degeneracy of the distribution in a more principled way. Let's actually come up with ideas that maybe why do we cluster data? We start asking ourselves some very annoying questions. Why the heck do you want to cluster your data? You must gain something, right? So, and one thing, how do you measure that gain? Right? Turns out this actually traces back to the very fundamental problem question that Shannon has asked, right? In the information theory, how do you measure information? How do you evaluate things, right? So this is something we actually realize that. So if data has this kind of no-dimensional structure, has this kind of structures, right? So something you gain something by looking at if there are two components, x and y, right? By looking at this, if you can separate them correctly, you must gain something. How do you measure that gain? Hence, one way to do that is very, very simple. If I don't separate them, to code them as one distribution, I find out how many bits I need to do that, to specify the location of each point in that space, in the whole space, right? Then I need to code the whole volume of that space. If I can separate them properly, then each one, I only can code those with different set of volume. The volume becomes small. So the notion of compression is behind everything, right? The reason I separate things because they compress, I get a much more compact representation. Very simple like that. Hence, the difference between the whole and the parts, the volume of the whole and the volume of the parts, that's exactly called the information gain, right? And so then this will become very simple, right? I only have to evaluate the volume of the whole minus the parts, right? If the parts volume is less than the whole, I'm done. I separate them. If smaller, I don't do anything. Right? Now the question becomes, how do you evaluate the volume of a distribution of some data in high-dimensional spaces, right? Turns out that's a very hard problem, right? Although you can write down rate distortion and so on and so forth, but it turns out that computing those things is NP hard in general. But we're lucky only in one very special case, is when your data lies on the distribution, if your data are Gaussians or subspaces, turns out there's closed form formula to compute the volume, right? So how do you, the basic idea, actually this is from Shannon, right? How do you evaluate the volume of some spaces? Then you just give me let's say a size of the ball, beans, or just pour that into that volume. Then you count how many beans in there, right? That's almost a universal way to evaluate the volumes, right? Of course, you have to specify more accurately, you give a smaller bean, right? If you don't care, you get a bigger ball, right? So you pour into that space, so you count how many balls there. The sphere packing, basically, right? And turns out in the case of Gaussian and subspaces, magically, it's the same formula, right? And so you can derive this formula purely algebraically or purely statistically. It's the same formula, which is very, very accurate, right? We'll see. I mean, this is something, right? So this is just a log determinant. It's actually the volume, how many balls you pack there. A very interesting log determinant of this regularized covariance matrix, right? Turns out everything comes from here. Residual network, transformer, all comes from here. Okay? We'll see that in a second. Right, so now, once you can measure the volume, the whole and parts, then it's easy, right? All I do is just compare, right? So if I have the data like this, if I split them in this way, proper way, the parts, sum of the parts is smaller than the whole. Of course, there's some overhead to code the membership if you want to do the Huffman code, right? And then how do you do this? This actually turns out to be a very interesting algorithm. And once this just tells you, once you split the data, it can tell us if you should split it or not split it. But how to split still doesn't solve that problem, right? There's combinatorial many ways to split the data, right? You have to try all of them. Turns out that this measure is very accurate. It's a log determinant measuring the volume. And actually, you can start from the bottom, right? You don't have to tell where to split the data. You actually just at any 2 points, you merge them if they can save bits. You start from grassroots, right? So it actually gives a very simple merge data. You merge data until any merging will not result in reduced number of bits, right? So this actually works magically. right? It's still the best, probably arguably the best clustering algorithm. Far better than k-mean, far better than any other factor method, right? In our book, we can characterize. It actually has a very interesting phase transition behaviors, right? I'll skip that. But before deep network, this gives the state of art unsupervised image segmentation algorithm. Everybody know what happened to deep networks, right? Everybody started to do supervised image segmentation, right? But this is still the state of art with unsupervised. It's completely unsupervised. Don't need any training data. Just merge similar data points together, right? Then this is purely unsupervised. We actually started with unsupervised problem. Then of course you think about what do I do supervised? If I do have data, right? Apple, orange, there's a new data comes in. Is this apple or orange? Right? It's a classification problem. Now how do we do that? Again, very simple idea is that ask yourself, then you must gain something by assigning the image looks like apple to apple, right? Then this is actually, again, is a compression problem that you can actually say that whichever cluster takes minimal number of bits, extra bits to put that points into it, the minimal incremental volume to claim that points becomes the assigned, right? So that actually turns out very interesting. That we call this minimal incrementation. Just measure the volume together and the subtract. Whichever one the delta increase of the volume is smallest, you assign to that, right? And it's all really has a minimalistic flavor to this, right? Everything about thing is about compression. Everything is about the most compact representation, right? Measured by bits, measured by the number of balls, right? Nothing else. Everything is a counting game. Turns out this simple counting bits assignment actually converge to, if you have data size goes to asymptotically goes to infinity, this give you precisely map estimation. Actually does exactly theoretically the right thing, right? It's very simple bin counting bits. This is our, and it has some very interesting behavior. This is our NIPS paper around 2009, I believe, right? So you can see this is the first paper, very first classifier actually extrapolate structures, right? This is what the nearest neighbor will do. This is what the nearest neighbor will do. This is what the SVM will do, right? This one you can see never has seen any sample on the left, but you will see this. I see a line. This actually can extend to the other side of the data. Completely give you a classifier actually respect the low dimensional structures, right? It does that automatically. At that time, we were pretty happy, right? We actually see this actually does the right thing theoretically, and also really unifying the notion of compression seems to unify in a supervised, unsupervised fashion, right? Everything's reduced to data compression. Of course, although we only was able to work for the case of linear substructure and the Gaussians, mixture of Gaussians, right? But we were happy. But there's one thing problem with this is that we'll see that this is actually only dealing with Gaussian or subspaces, right? But we just said the data could be nonlinear, right? Then the measure is off, right? If my distribution is curved, right? It's not a subspace, what do I do? So we stop there, but then neural network become very popular. Then we start to re-examine neural network. We started, this is our method of compression, only the measure. Remember, we can measure those rate distortion or coding length only when the distribution is linear or Gaussian. Right? Other distribution is very hard to compute. Okay? You can write down IXY, mutual information. You can write down rate distortion function, but you can never evaluate it. Okay? You can talk about them, but you can never get access of them. Okay? Stop talking about them. Okay? If you cannot compute. Everything you put on the paper, there's a price tag. Right? Well, so the question, then we would start to realize that since Gaussians or subspaces are only ones, the distribution we can measure, maybe we can make them. Maybe that's exactly the role of deep network. Right? Our original data distribution may be nonlinear or arbitrary, but the process of learning is precise to make your distribution to some standard structure. Right? So if X could be multiple manifolds, then we can learn the mapping F to make them linear. If this is a 5-dimensional, make this 5-dimensional. If this is 6-dimensional, make this 6-dimensional. And we sort them out. And if those two manifolds are barely separable, we make them orthogonal, just like the neural collapse. Different cluster means are orthogonal. Right? Hence, we call this So hence, the mapping has to do multiple things, right? We try to represent the data, right? Linearize if each manifold is nonlinear. We compress, right, from a high-dimensional sample space to compress. If this is a million subspace, but the minimum of dimension, this could be just a few hundred. Sparsity from separable. But if once this are orthogonal, the representation automatically becomes sparse, right? That's the emergence of sparsity, right? And also, we want one problem I'll talk about on Thursday morning, right? We want this mapping not just reduce dimension, or we don't want this 5-dimensional apples all collapse to 1 dimension. Why? I want to know why apple is different from orange. All the characteristics. All right? I just don't give me a label. This is an apple. Don't tell me why. Right? It's collapsed to the one label. That's very bad. Right? Tell me the color, the shape, the texture. Right? Don't forget that some apple are called computers. Okay? Or what if I want to regenerate the data? So I want this mapping to be almost 1-1 so that I can go back, right, for generative purposes. We want to unify everything, right? So the question is, that's something I'll talk about on Thursday. But today I'll focus on the one direction, right? So we try to learn a mapping such that make the data one-dimensional linear and also different classes incoherent, orthogonal, and also that hopefully that each class we want to preserve as information as possible, preserving the dimension. Can we do that? No collapse. Again, how do we do this, right? Remember that how do we measure to make this more compact? Oh, I have to measure how good the features are, right? You have to put the goodness of the feature. Again, we know when the feature, if they're linear, we know how to measure them. The volume and the dimension, right? This is the formula, we know that. This is for the whole data sets, right? That's why this depends on the number of samples, but if you only care about the rates per sample, you divide it by m, and also if d is fixed, m goes large, the rate is exactly this, right? You give it a rate function. It's average number of bits per sample, per vector you assign to your data, right? Give you a very intrinsic measure for the volume of the feature expanding in that space. It's computable for subspace of Gaussian, for mixture of Gaussian, right? Of course, your data could be multiple subspaces, right? Multiple mixture of Gaussian, and fine. If you know the cluster properly, especially in the supervised setting, right? You have samples; they're separated, right? You can compute for each class, fit with a subspace of Gaussian, right? That's a feature. X is not, right? This is only on Z, right? After the mapping is done. Now, what makes feature a good feature, right? Again, the information gain. Why do we want to separate all the image to 10 classes or 1,000 classes? Because I gain something, right? If I put them as a whole, I have to cover that entire space spanned together, right? To label them. But if I can split them, each one becomes a smaller volume. Hence, the difference between the whole bits, I encode the data, treat them as a whole, minus I code the data separately with k classes. That difference is exactly we call the rate reduction. The reduction in the rate distortion for the whole to the parts. Okay? I mean, in fact, it's actually measuring how much gain of information I'm getting. That's it. By counting balls, evaluating volumes. Very basic, very universal. Right? And you can see the first term is actually says measure the volume of the whole data sets. Right? The second thing is the different classes. It's a compression. So then, if I have freedom to map my data to such a Z representation, which one do we prefer? Right? Obviously, we prefer, you can see that if my data lies on two lines, right? Two subspaces, we cannot prefer the one on the left, right? You remember the Euler collapse, right? We wanted the subspace to be orthogonal to each other. Why? From the information gain point of view, you gain the most, right? Because the whole minus parts here, all the blue spheres are the largest on the left. Although intrinsically, the data has the same distribution, lies on two lines of the same length, right? But the information gain, the left one is larger. Hence, if you really wanted to look at the volume here, you want to find the Z such that this difference gets maximized. Right. Actually, this is exactly the similar idea, right? People have practiced this contrastive learning. Right? I want my different different data that's kind of different, right? Likely the data points from the different classes gets contrasted, right? They use a very heuristic measure to do that. It turns out using the redistortion, using the information gain, you can measure contrasting data with arbitrary classes, subsets. You can contrast them, you can compress. And hence, this is sort of we try to find a mapping such that the data rate reduction gets maximized, right? Now, then you try to, then you ask yourself the question, if I wanted the blue balls, right, the whole minus the parts, the largest, right? You say, well, what about I scale the one on the left, right, twice, 3 times? Then the space of blue balls gets larger, right? Then everybody can start to cry and fall, right? Why? The scale is not normalized, right? If you want to compare these two representations fairly, better they are on the same scale, right? That's exactly the notion of normalization, right? So you make sure the feature you got is normalized. That's exactly the notion of normalization. When you compare 2 representations, they better have the same scale, okay, on the same sphere. Hence, in the neural networks literature, people are doing the batch norm, layer norm, instance norm, group norm. They're exactly doing the same thing. Okay, there's no difference. Just like Zihui says, right? There's a different loss function. They're absolutely mathematically equivalent. Okay, it just matters how you optimize them, right? They make a huge fuss about every paper is about them, right? Just basically, I compare representation across different layers or across different neural networks. They need to be on the same scale. Hence, normalize them every time you are done, right? So once you do this, the question is, if we do this, if I maximize this rate reduction, do I get the kind of desired configuration? Turns out that is the case, right? Just very similar to what Zihui just said, right? Here that he's also, each class he assigned 1 dimension, right? Here each class will actually assign the dimension exactly the same as the class with intrinsic dimension, right? As long as the ambient space is larger than the sum of all the intrinsic dimensions, then you can prove those features gets pushed to orthogonal subspaces. And the rate reduction, if you optimize them, you'll get the right representations. Right? Does this work? Actually, that works pretty well, right? I mean, you can see that. And the good thing about this, you can see that this is on CIFAR. We can just use let's say we just choose there's the only thing that we can use to learn the mapping, we can still use the ResNet. We'll talk about how to replace that with a white box network just in a second. For now, we just choose neural networks. But the only applies the only difference between these 2 experiments is that everything is the same training, the same network, but the only thing difference is that one uses cross entropy, one uses the rate reduction, right? You can see that per class on CIFAR, each class actually is no longer collapsing, right? It actually converges to about 10 dimensions, about a dozen dimensions, right? And then the features of each class is absolutely orthogonal to each other. And here, even if it converge, right, the cross entropy is still, across different classes, still high correlation there. Maybe you train long enough, you get an orthogonal. But this is actually, you can see that this is actually saying that since each class is a 10-dimensional subspaces, right? I can compute the principal components. I can plot which image is close to those principal components. You can see that it sort out those different classes very nicely. And also, what does this work better? Actually, yes, even on CIFAR turn, right? You can see that in terms. Also, one of the things is that we're not just learning one feature, right? We're actually learning all the features separate apple to oranges. Actually makes, at least empirically, make the process much more robust to label crosses, right? Collectively, we're using a set of samples to estimate that subspace. Even some are mislabeled. The subspace is still the same, right? So actually you can see that if the 10% all the way to 50% of labels are randomly corrupted, but they still learn very well classifiers, unlike cross entropy. It's affected by that. Right? So of course the remaining question is, for the remaining of time, I'll just quickly, right? So the remaining questions, we're at that time we're a little bit happy, right? This actually reveals what the neural network is trying to do, right? I mean, this is the kind of features. We learn much more diverse features. We sort of explain what maybe each layer, we can evaluate the features, how good they are, But what's really depressing is that, well, there's still a black box, right? How do you learn this mapping from X to Z? Right, black box, right? How deep, why is deep necessary? What is doing? How wide, how deep, right? And what is this linear and nonlinear operators doing anyway, right? Why multi-channel convolution, right? Especially in images, right? We do convolution, but not in the tradition, not in the deep network type, right? The 3D convolution type. Why, right? None of them is because some of them tried and tested, right? But one good thing about knowing the objective, that you couldn't care less, right? If you were clear about the objective, then just achieve that objective, right? I couldn't care less. So remember, our job is to maximize this object function, find a mapping, continuous mapping X to Z to maximize this, right? If I can guess it, I'm the god, right? I couldn't care less. I use deep networks or shallow networks, right? Or guess a kernel to do this, as long as this mapping is mapped. So one thing we think about is that since this is the object function we do, we just optimize. Can we just optimize it? In fact, the recent paper from Hinton precisely said this, right? Nature doesn't do backpropagation, right? If you know the object function, if you know how to value the goodness of your feature, you should do things in a forward fashion. That's exactly what we should do, right? So this looks complicated, log determined and everything, right? Long convex optimization, but everything we told you guys this earlier is that don't be afraid of nonlinear optimization. If we see a nonlinear optimization, just to do a greedy descent. The least you can do is to do greedy descent, right? Let's just do greedy descent. If you do greedy descent, something magical happens, right, on this quantity. Remember, this is the volume of the whole, this is the parts, right? They're all log determined. Once you take the gradient of this quantity, something magical happens, right? The first term becomes this. The second term becomes this. The other terms become this. Everybody good at statistics should recognize immediately what they are, right? This is exactly the residual of doing data autoregression, doing ridge regression, using data points to regress each other data points. Okay, nothing else, right? And of course, you can see this is a complicated inverse. Doesn't really matter. Some function, some matrix hitting this feature, right? Hitting the iterate. And this is another matrix hitting the iterate, right? So we write down this delta R. It's actually one matrix multiply the data, another matrix multiply the data. Of course, for each class, apply a different linear transformation, right? It's a piecewise linear transformation on your feature. Right? This is, as I said, this can be exactly interpolating as EZ is exactly the residual doing the autoregression of all the data representing each other. This will show up, right? Autoregression, self-attention, guys, right? There's exactly the same thing. We'll see that immediately. Right? So this is actually just a residual. Depends on the residual. This is very simple, guys, right? I'm trying to compress the data, a whole, right? I want to maximize the first term. I compute the residual. Every point gets represented by other data points. If I want to maximize the volume, what I do, I make the residual larger. If for each class of data, right, I represent each point with other data points. If there's a residual, if I want to compress, I reduce that residual. Very, very basic, right? And turns out that's exactly what the maybe neural network is doing, right? So if the original data is nonlinear, curved, manifolds, then I want to linearize, map to those linearized. I want to compress each class and expand all the classes. I compute a residual. For expansion, I put a positive sign. For compression, I put a negative sign. I reduce the residual. That's it, right? Each layer is just doing that. And of course, here is one thing where the nonlinearity shows up, because for each class data, I need to know which class it belongs to. Which class that particular data feature point needs to compress to against which class, right? Then since if I don't know that class, I just do a soft class. I just do the soft mask, assign that to each class. Right? Hence, you get this. So this actually exactly applying the feature to the corresponding class, right? Doing a soft class. You get it actually the soft max. By the way, one way to approximate these things is exactly using ReLU. I mean, I'll skip that. So we are all engineers, right? If you write down the optimal function, unroll the optimization algorithm, then of course we can do diagrams, right? From the previous iteration to the next iteration. You get a diagram, this feature gets a hit, those linear transformations. By the way, this is doing the greedy descent. There's the residual part. This goes through the nonlinear soft mask, doing the normalization, and go to the next layer. Nothing else. So everything here is completely derived from scratch, from the data itself, right? And we call it the residual network. So everyone, does this recognize this looks like? Right? This is exactly the residual network looks like. In fact, later on people find the res next works better than residual network, right? Parallel channels. That's exactly the parallel channels. In fact, in the transformers, why there are multiple heads? Because for different classes, different substructures, you need to assign them properly. The data goes to different channels, right? Gets processed differently, and you need to have parallel channels. They're actually just doing optimization, doing compression correspondingly, right? So, but very different from all this architecture, right? It gets trusted. You need to randomly initialize carefully, and you do backward propagation training. Everything here is completely computed from the data itself, forward fashion. No training whatsoever. Right? Just like a PCA network. And look at even this transformer, right? Has exactly the same mixture of experts. Transformers has this Google's one training has exactly the same meta structures. They're all trying to emulating the same thing. Right? Does this work? Actually, it does, right? So actually, in the purely forward constructed networks, actually my students have some fun, right? They actually construct Tosan layers. If you want the deep layer networks, of course, just like a running deep neural net, just running optimization algorithms, right? You can do the iteration forever if you want, right? If you don't care about computing, but that's the wrong thing to do, right? It's not efficient. But you actually can think, as also for group invariance, you can actually try and train this. So this is actually just for grouping data already have subspace structures. What about Sam also talked about many more problems, right? We actually have data, maybe want to group all the transform cluster, right? Samples all as one classes. Don't worry. I mean, just treat all the transform sample as one class and push them into one subspaces, right? Map them into one subspaces. What about we compress all the translated or transformed sample together? What will happen? Shift transformation, right? Let's consider shift transformation. If you compress all the data, think about a one-dimensional signal where I shifted one by one, right? Do a rotation translation and rotated cyclic translation. I compress all the data together into one subspace. What will happen, right? Computed rate distortion, remember, right? Everybody can become a cyclic matrix. If this is the measure, right? Turns out the E channel or C channel, if you compress all this translated signal together, you automatically, the E channel, C channel, the operator acting on the feature becomes a convolution. They actually become multi-channel convolution. Precisely the structure of the modern deep neural network, right? Even with crosstalks, I'll skip this for the interest of time, right? The E channel, C channel actually precisely become cross. That's just a matter of, actually they become automatically multi-channel convolutions, right? And it turns out very interesting, right? This E channel, C channel turns out they need to take an inverse of a homologous matrix. Turns out this matrix has block diagonal structures. It's much more efficient to compute in the frequency domain, not in the original space-time domain, okay? Don't forget our brain computing in frequency. Right? This is at least one piece of mathematically, proof, right? Evidence, right? Computing in frequency domain is much more efficient, right? Computing in time domain is the n to the cubic, but in the frequency domain is linear in the number of pixels. Probably nature already figured out. It's much more efficient to do translational invariance in the frequency domain. Right? And now you actually can derive, right, the whole neural network. Write down the neural network, every operator, every parameter in a pure white box, right? And in frequency domain. And so this turns out this just gives us a little bit of a very interesting way, right? You have multi-class signals, you lift it to multiple channels, do a sparse coding. I'll skip that. But then what really the neural network is trying to do is try to do a map different classes, compress each classes into a subspaces and separate them. And everything, you don't decide anything here. As long as the object function, your object function is maximize the information gain. Human, you don't get choose almost nothing. You just try to gain that, maximize the information gain. Every part, linear, nonlinear normalization, everything gets explained. Right. Actually works pretty well. You can see. And by the way, nobody is stopping you from fine-tuning this. Okay, just like we have the algorithm to solve sparse representation, right? Remember the Lista algorithm, right? Yang-Kuhn test. Oh, I can, if those iteration, each iteration is not effective enough, I can fine-tune those parameters. Nobody can stop you from doing that. That's exactly what backpropagation is doing, right? If the output is not good enough, I backpropagate error. I can fine-tune the parameter. I get a higher text accuracy, right? If the number of iterations is fixed, I can make each iteration more effective if I have enough training data. That's exactly backward. But that's not a natural way, okay? Nature never do that. Nature cannot do that, right? We cannot do things end to end, okay? Well, on Thursday, I'll introduce another thing. Actually, that's exactly what the Quinton's latest paper was talking about, right? Nature correct error not through backpropagation, through loops, feedback loops. Right? We'll talk about it. So this is actually to try to conclude a little bit for the interest of time. Right. So basically, we saw a few examples, right? If I have data, I want to cluster them. You have to tell me why you gain. Why do you do that? The only measure is that it's compression. Because I separate, I gain information. Okay? There's a very fundamental basic measure there. Right? Bin counting, counting balls, packing spheres. Right? And it actually works in both classification. But this works, the difficult part, guys, if you put expression R there, you better know how to evaluate it. You can compute it. The only case we know how to evaluate it efficiently are the Gaussians or subspaces, not arbitrary distributions. Stop talking about those quantities that you cannot compute for arbitrary distributions, okay? Yes, admit if you are approximating them, you are sampling them, right? But don't claim you have a better solution. Well, I'll talk about on Thursday, especially about GAN, right? About the learning the generative model. That's even more worse, the situation, right? So, and now the question is, then maybe we can make, if the Gaussian or subspace are the standard structure we want to learn, then we want to learn mapping to make the data that way, right? The natural distribution might be very complicated, but we make them linear, make them separated. Right? That's exactly the role of neural network. Try to achieve this in an incremental, iterative fashion. Right? And of course, the rest of the job is just how to find the right optimization strategy to do it. Right? That's still open, by the way. Right? So basically, deep networks just try to do this. Right? The objective function of neural learning, any learning, I argue, is try to gain information. Any part of our brain is actually trying to gain information. A principal approach to interpret the deep network is just optimization. Could be gradient descent, could be a power iteration. We'll find out, right? So once you do realize this turns it's about the 70 years, right, since the inception of deep networks, 1940s, right? For 70 years, the practice of deep network has always been on the left column, right? We fit input-output labels. We fit input-output. Right? And the architecture, we try and error. We try, test it, right? The convergent, we'll see. Layers operation empirically. Well, what they do, softmax, ReNU, you try. Which one works better, right? For shifting variance, we do CM plus some augmentation, but we cannot guarantee anything. The university has to carefully randomly, or pre-trained. And we do backpropagation. Even after we did the backpropagation, the network still black box. Oh, you can argue it's a gray box, but still, you don't know quite, right? But the worst thing, right? Google, Facebook pays $1 billion to train those big models. Actually, they call the representation latent or hidden, right? That's very depressing, right? If I pay something for $1 billion, it's hidden to me, right? Now everything is turning upside down now, right? So if you have a more principled way of looking at it, if you know maybe the network is actually trying to gain the information, if the object function is clear, what I want to optimize is clear, everything becomes clear, right? Then maybe I'm just to optimize that objective. The network is precisely trying to achieve that, right? And each layer is just do gradient descent or maybe more effective operation, We can find out later. And then you can just do this, we compress all the invariants together. You'll get an invariant, the structure will pop up. And the network is actually formally computed. Right? It's very natural. And of course, you can do forward or backward or fine tuning. Nobody can stop you from doing that if you have a 5,000 GPUs, right? A lot of input of data. And the point is that you actually end up with a white box architecture. You know what each layer is doing. And also, the most importantly, after you're done, right, you know this is what you're getting. The features are linear, become structured, compact. And we'll see on Thursday, we can go back, right? How do we make sure what we learned that structure is exactly correct, right? So there's actually a lot of things, right? So of course, today I talk about the case you already know different classes, the samples for different classes are already labeled, right? What if you don't know that? Some of the students here are already working on that, right? How do you jointly optimize the representation and the clustering if I don't know the label? Again, but the principle never changed. Right? Having the label, without the label, it's just different variable in this object function, right? With the correct label, this difference gets maximized. That's it. It's the same quantity. Remember, we're doing the clustering. I can do pairwise, for God's sake, right? Merging them. I only compress what's similar and separate what's dissimilar. That's all this object function is doing, right? And once you realize network layer by layer is doing optimizing this object function. 300 years of studying optimization helps you to find a better optimization algorithm, design architecture, right? Here, the Redu network is just doing the gradient descent, which is the simplest, most naive gradient descent, right? You can do much better with accelerated gradient descent, other structure in your operator, right? Most importantly, remember this gradient of the rate distortion, right? Looks like this, right? Who says this is the only way to approximate it? Who says I have to approximate this inverse with the E matrix? Do von Neumann expansion, right? You can do the von Neumann expansion of the inverse. What do you get? Keep the first few terms. Expanding this, take this. This is exactly the terms that you saw in self-attention transformer. Nothing more, nothing less. Okay? It's the first order approximation of that. Right? So you can see that. Remember, guys, right? When neural network come out, everything is very mysterious, right? Or resident trial error. I mean, there's something. Of course, the theory fall back. People cannot explain. People think there's something very mysterious. Hence, for long years, many years, there was all this work about the AutoML. We do random search. We search all the different architecture. We believe there's something magical out there, right? But after how many years now? Only two networks sort of survived. ResNet, transformer, right? They're exactly approximating the gradient of the compression or expansion. This is the only thing you can compute. By the way, the score matching function behind this so popular diffusion model are exactly computing the same quantity, okay? The gradient of how data volume change. Nothing more, nothing less. This is the only thing you can compute reliably, accurately in high-dimensional spaces up to first order, okay? You can approximate more accurately, nothing more, nothing less. Everybody is doing the same thing. Right? So that actually turns out that this is actually another interesting thing, right? Through this approach, you actually can see not only this is a sort of engineering information theoretical driven, but actually you start to see a lot of things you derive from, deduce from this approach, resemble a lot of things that people already observed in nature, right? The sparse coding, spectral computing, subspace embedding, and we'll talk about on Thursday, the feedback loops to ensure, right? That is exactly what we saw in nature, in the primate's brain. Right? Those mechanisms actually that precisely, as I said, maybe our brain or memory is precisely trying to gain information. And that measure is very basic, very computable, very tractable. Right? And we'll see that. See, today we talk about how to learn this mapping x and y, what is the object function of delta y, but how can we guarantee? Remember, guys, the optimal solution may not be the correct solution, right? Very huge difference, okay? Optimal solution may not be the correct solution. Do you get it? Right. If you still think these two are the same, check your mathematics, right? So how can you make sure I optimize this thing, I get some z that's actually precisely the correct for the x? I'm not, if the oranges are 5 dimension manifold, how can I make sure the z is also 5 dimension, not a 6, not a 4, not overfitting, underfitting? How can you guarantee that? How can you guarantee your solution is consistent, is correct? So we have to be able to go back. How do we do that? How nature does. Of course, you can say, oh, well, let's do backpropagation, right? Have a lot of billions of pairs. That's what exactly they train all this chat box, right? Reinforced learning, if I have lots of pairs between x and z, label data, fine, do that. Nature never do this. Nature cannot do this, right? Cannot afford to do this. Then what they do? How can they still learn solution probably much more elegantly, much more efficiently than what we do now, right? So what are the other mechanisms? We'll talk about on Thursday, right? So how do we go back, close this loop, right? So anyway, let's sort of conclude, and also we'll start to see this one framework actually works in all settings, start to. Supervised, incremental, unsupervised, right? And all approaching the state of art. Things gets much easier and better. So this is the main reference for today is actually this paper. As I said, it's the JMR paper. It's really about this one direction, right? How do we build deep networks in a white box from forward fashion? But that's give you the optimal solution, likely, but not the necessarily correct solution. So we need some additional thing to make sure it's correct, right? Again, as John mentioned earlier, right, this whole tutorial based on some of the mathematics based on the high-dimensional data analysis, statistics, and geometry, right? This book gave you some of the introductory material, but many of the things we can talk about today or maybe on Thursday, we'll talk about some latest development in this direction, following this direction. Yeah, that's all. Thanks. Sorry, take a few more minutes. Can take a couple quick questions, and we can go through. Yeah, some of you can ask questions. If there's some question online, I'll answer first. Some of you guys, I can maybe take a couple of light questions, and we can, chat over the coffee. Okay, anyone have any question? Yeah, we're running a little bit late down for a coffee. Quick question.
If apples are aligned in 2 axes, like red apple and green apple, and we have label of only apples, and we align them in the simple space in one plane. So that would be wrong in some sense, right?
No, so here's quick question for your question is that even each class may have a substructure within the subspace itself. Okay, if it's sort of uniform distributed, and the object function will push them into more like a Gaussian within that subspaces. And the different characteristic attributes, in the Thursday you'll talk about, I'll show you more example. Different attributes may show up at different principal components. So maybe green apple, the different color may become different principal component. Color becomes one principal component, shape becomes another one, or different characteristics. Or the side apple, upside top view, side view apple will show us different principal components. So there's a finer structure within each subspace. But this is just a push different classes into one subspace, including potentially even the rotation, the transformations. You can even imagine, right, in the subspace, if you group all the apples, including the rotated one, so even the rotation will embed it in somewhere as a curve in that subspace. So similar to what Sam has, right? Discovered. But that transformation will not be one-dimensional, right? Because all the poles could be multiple-dimensional, but they will be embedded into that subspaces. Yeah. So that's what you want. The question, of course, what exactly they are? How can you further disentangle them? And then how do you sample them, right? The whole point is that we want. See, this is the point. We want our representation Z, whatever distribution in that hidden space, is not hidden for God's sake, right? That's why the GAN or after diffusion model, you still have to sample it. You have to guide where to sample, right? You cannot arbitrarily sample and generate something that will generate mostly gibberish, right? So this is the question: is that we want our structure Z map different classes in just like in our brain. We imagine an apple, we see an apple, right? we don't, it's not randomly sampled, then we diffuse the model to try to draw sample. That does not kind of work, right? Our memory has to be highly organized, highly compact. We know exactly which part of, actually that's how some of the scientific experiments showing, like monkeys' brains, they actually organize different classes of objects precisely in different regions of the brain, right? They're highly, like there's one region just encode all faces, human faces, right? Just a few hundred neurons, that's it. Encode all the faces as bases, coordinates, right? Representing all the faces that the monkey has seen in his whole life, right? So it's highly compact, highly organized. We want to understand what that process is, right? Hopefully, likely the whole neural network where layers are precisely doing that to maximize that information gain based on the separability and the compress of each class. Right. Good. Yeah, we can probably move on to, oh, you have one, yeah.
Sorry. Just one last question. This is probably dumb, but you talked about supervised and unsupervised for classification tasks.
Mm-hmm.
Does this information gain also extend to regression tasks, or
to which task?
Kind of a regression task instead of like a classification task?
So in fact, you can think about this object function is already doing implicit regression, right? You can see it's just like PCA. PCA doesn't, PCA just find a correlation among all the variables, right? You can think about it's doing joint regression. Of course, it doesn't specify which variable you regress against other variables. It's finding all the correlations, right? Then depends on future tasks. Once you find that subspace, then in the future you can find out which features are predicting which labels. You have a new variable, so you can decide which those subspace variables predict that variable is best, right? So you can think about this. In fact, the whole process, even using labels, we're learning the structure of the data, not the task. It's actually pre-trained, right? We try to build a memory based on what's similar, what's dissimilar. Very opposite almost to the information bottleneck. It's trying to distract, give me a label set, right? Label the data, I try to find from the data which one maximize the correlation to the label, as if the label is ground truth. That's why you learn the label. You learn the neural claps. Everything converts to that label. Here's completely opposite. You pay attention to X. I wanted to learn a Z, which is a mirrored image of X, but organized image, right? Beautified image of the data, and make sure it's consistent. It contains everything predictable about the data, right? Compress it, and then the neural network just play the role to optimize the measure, your beauty measure. Of course, this principle is not limited to subspace, right? Subspace is the case we can evaluate efficiently, Gaussian in the Z case. Of course, for other class of data, other distribution, if you know the rate distortion, you can measure the distribution very well. The same principle applies, right? You have a measure of information gain. The only thing we use subspace is because we know how to, the log determinant are the closed form for measure that log, the rate distortion. For any other distribution, Laplacian or whatever, good distribution you like to, maybe genetic data has a different binary discrete distribution. The same principle applies, right? In fact, the information gain originally was used for discrete variables, not for continuous. But it turns out it's easily generalizable if you use the rate distortion to generalize it, right? But the principle stays. It's the same. I believe it's very universal. Yeah.
Thank you.
Sure. All right. More? We can chat. Oh, yeah. Go ahead. Just last one.
Actually going to a quick one. So what if you actually use some of those discrete optimization techniques instead? Would you get new networks?
No, well, there's some still didn't remember. I think I mentioned briefly. We didn't get time, but you have a poster, do you? Yeah, about the clustering, right? Yes. So we didn't today. We didn't talk about how to optimize the pi, right? Right. See, for example, pi depends on how do you. Pi is actually the clustering, right? Which point belongs to which group? You can, of course, you can approximate it. Parameterize with the membership, right? With a continuous variable to optimize to do gradient descent. I don't know. I mean, we never do this. What is the architecture you get from there? You can do that. You still can do gradient descent against the continuous membership, right? You get some operator, but of course, you can depends on how you parameterize pi. If it's a discrete variable, then you have a compilatory optimization. That's actually something we got stuck when we do clustering, remember. The clustering, you don't know how many partition. We actually do merging. We do pairwise merging. In clustering, you can still do that. I think, until some of the students already try. Renee's have tried this as well. But regardless, you have this thing as a measure. The correct pi and z give you the best delta r. If you are God, you can guess it, right? You don't care what the network is. Network is just a means to the end. Whatever you can get that optimal solution for your data, you're done. Right? You learn the best you can, right? You get the best memory. Your brain already memorized the structure and the samples perfectly, right? So that's the common game there. Now, the rest is just optimization strategy to me. Also, the starting point is different. If I know the pi or some initial z, the optimization gets easier. If I don't know the pi, I just have to find it. Which one is the best? The optimization becomes harder. Right? Good. And because of that, I'm pretty sure in the future, in unsupervised learning cases, maybe there's a different architecture, right, than the ones works in a supervised setting. ResNet transformer, they are sort of customized to the supervised setting. We don't know, to take into account the unsupervised clustering together, what additional structure, what additional operator should be there. Right?
Thank you.
Sure. Thanks. I think that's it. Thank you, everyone.
Thanks, everyone. We'll be back here at 4 p.m. Maybe we'll extend the coffee break a bit. We'll see. For the next talk from Professor Atlas Wang. And after that, Professor Sai Ravi Shankar to wrap up the day. So hope to see you back 10 minutes or so.
15 minutes.
15 minutes. Thanks.
test or it,
Welcome back, everyone. We'll have now the last two tutorials for the day, taking some deep dives into specific aspects of deep learning low-dimensional structure. First, we'll hear from Professor Atlas Wang from UT Austin. He'll be telling us about sparse neural networks theory and practice.
Thanks, Sam. All right, thanks, everybody. Welcome back. And for this talk, I plan to talk about a bit different gear from most of the previous talks, I would say. I would apparently still talk about the sparsity neural network. I guess everybody is talking about. But my point would mostly be talking about how to exploit, how to leverage, and how to understand the sparsity that are naturally emerging in current practical deep networking use. So that will be a little different flavor, hopefully similar spirit, but different flavor as it seems, from many talks given by Sam, by Yi, by Qing, by Qing, and a bit similar to the flavor of Zhihui, which is to observe the training behavior of the deep network that could be interpreted as a terminal sparsity. So for this talk, I will talk about the sparsity in deep networks weight. Well, to me, sparsity in current deep networking use in particular has three aspects. The weight sparsity, which is sometimes known as pruning, sometimes as a sparse training, many other different names, we'll see some of them. The second aspect is activation of neuron. So that if it equals a channel, that leads as channel pruning that practitioners usually love the most. And many other things, remove activations. And the third part is the data. So weight, activation, and the data are three aspects of sparsity I usually look at. And in this talk, I will just focus on the first category, the weight sparsity. And for the most time, I will talk about the element of sparsity and all for practitioners known as unstructured sparsity. So without further ado, let's begin. A bit of the background, sparsity, everybody in this audience shouldn't need too much more introduction after today. Well, it's a well-known concept starting from philosophers and artists, and talking about myself, my personal research journey started from reading this famous book, The Classical Sparsity in the Lots of Context. And nowadays, if I ask my students, especially the new student coming to my group, what is sparsity, their by default answer is pruning. Yeah, at least you should know pruning. And so sparsity still thrives in our practice under a different name. So with so many years, so many effort, and so many nicknames being given to sparsity, people may start to wonder what else can still be done in sparsity, especially the weight pruning literature, since if you count, thousands of papers have been published in this field. Can we still publish some new papers in this field? I'm trying to convince you, yes, and there are more interesting questions that current literature doesn't suffice to reveal. So in this talk, I will discuss three aspects. First, I'm trying to convince you that if you are a practitioner, you should love a sparse neural network, and that means way beyond pruning, means pruning or model compression. There are way more than that. And second, I will talk briefly, hopefully I have time to scratch the surface. What are new theoretical problems that one could motivate from study neural network on the weight sparsity constraint? Just like from least square to lasso to L0 regularized least regression, those motivate many, many new interesting algorithms and theories like comparison. I will try to justify that a sparse neural network would have the same magic that can be played. And for the future, I will mainly talk about a few application perspectives that a new sparsity could be leveraged. Some may be under the buzzword trend now, so hopefully. Let's now start from the first aspect. Practically, what you could expect. All right, so start from some stories. Again, everybody should already be familiar with it. Sorry, that's how I prepare my slides. So one thing you should know that everybody now, okay, machine learning researchers like go big. Like we just listened to Yi complaining for an hour that we are using thousands of TPUs, big models, 2,000 layers, and build models no one other than Google Meta that are able to train. So starting from a BERT and the Sinclair, well, every model when they come out, we thought the BERT is large enough. So the Sinclair is more than large enough. And when GPT comes from, we all understand that we are underestimating what is called big enough. And GPT-4, who knows what will happen, right? So one arguable trend in deep network is a big network just seem to be more capable at everything. No matter why it happens, a big network seem to be generalized better, seem to be better at reasoning, seem to be better at future learning, seem to be better at auto distribution, uncertainty quantification, blah, blah, blah. Just don't know why, but seem to work, okay? So good, but that performance magic is just one aspect of what we look at. And on the other hand, the market always look at the solutions that go against the big trend. That is arguably for AI to be more persuasive and penetrating to different application frontiers. You want AI to be affordable. You want it to be tiny. You want it to put into all the devices like you wear or you carry in your pocket. So that leads to a contradiction and has naturally motivated the now called classical research field of deep learning model compression. I can see many people here have done influential work in the field. And in that field, I think arguably model pruning is one of the most popular and practically most adopted method. So now let's again give ABC level review, how people usually do model pruning, I call the old-fashioned sparsity for neural networks. Let's start from a random network, okay? And do some training. You get a trained network. Good. Now make it small. Then based on some criterion, I would remove some element that I believe to be unimportant from the model, put them as 0, and keep them as important element. Very nature, right? And such criterion of important versus unimportant criterion has been developed past for 4 decades, starting from element, from optimal brain damages, Hazen criterion, influence function, blah, blah, blah. Every year, CVPR can publish 100 paper on that. So from this pruned topology, usually size-wise you get satisfied, but you see you get satisfied, but you also sacrifice a bit in the accuracy. And people's typical trick is get that pruned network, put it back in the original data set, train a bit to restore the accuracy. And usually, in order to make it really match the optimal trade-off you can achieve, you want to do this multiple times, prune and retrain, prune and retrain, prune and retrain until you're happy with that, called iterative training. All right, so far so good. But one thing I think many of you have already realized that is this pruning method is getting the economic benefit of inference saving at the cost of paying extra training costs. So usually if you just want a dense network, if you just want a dense network, this is the endpoint. And if you want a sparse network, you need to go beyond, and that usually including loops, iterative loops between pruning, training. Roughly that means in this iterative training regime, if you want to get a compact network, you're going to train that for multiple times. Instead of dense network, you just train more one time. So think about, well, that is fine if you are playing network, train on MNIST or CIFAR. But talk about one day, I want to do this on GPT. Come on. What does it mean by saying I want to train GPT 5 times? OpenAI knew GPT-3 has a training bug. And they even don't have the budget to fix that by training it again. So you say you're going to publish a paper training GPT by iterative training. I wish you good luck. So a more pleasant method is, what if, I'm just saying what if, starting from the random beginning, I could directly get a sparse topology, directly identify what connection, what weight are more promising to train. And therefore, I start from point 0 with a sparse network. Sparse network here, I'll clarify again, means most of the network connection weights being 0. It's a weight sparse network. Starting from the weight sparse network, and directly stick to that sparse topology, keep training. Guess what will happen in the general case? The common wisdom before 2019 would tell you this will not work easily. And I guess the reason isn't hard to guess, right? We all complain about the deep network and how difficult they are to train. And with all those difficulties, that killing gradient here and there in your information flow, now you get one more difficulty that is many of your weights are being nothing but 0, how it will affect your backpropagation. So sparsity is a natural killer and similarly enemy for deeper network training. That's why starting from the scratch sparsity training wasn't getting popular and people doesn't deem it as promising. That's also why people have to tolerate this. Start from the full training and then pruning and gradually probe, where is my good sparsity subset? Okay, so that common wisdom also convinced me until 3.5 years ago in New Orleans, I clear. Well, how many people were in that iClear 2019? Okay, how many people attended that best paper ceremony? Jonathan Frankel. All right, so I was there, and I was seeing this best paper award, and was totally blown away by this concept. I'm honestly saying that. As someone has working in sparsity for a while, this result really gave me a refreshing new horizon. Lottery ticket hypothesis. iClear 19 best paper. I was trying to make a summary, and I eventually find I cannot do a better job than Jonathan. So this is a paper done by Jonathan and Michael Cabin, both are good friends now. And this summary, I still think Jonathan did an unbeatable job. So lottery ticket hypothesis stated as a random initialized dense network empirically should contain at least one subnetwork that is initialized in that way such that when it is trained separately in isolation from scratch, this subnetwork, randomly initialized, could be trained to match the accuracy of the original dense network by using no more than the training budget or the training length of the dense network. So roughly, it's telling you such a surprising truth. Instead of playing with this big fat guy, you could find there exists such a lucky slim guy, a subnetwork within the dense network, such that if you could get it extracted, this one alone could be trained to achieve better or same result, same or shorter training time, and from scratch, compare the dense network. And as this network is trained in the sparse format, naturally, you get efficient training and efficient inference. There is nothing called post-training compression because the compression is done at step 1. So all appealing, right? All those appeals were true if and only if assumption. If you know who is this sparse subnetwork. To select a subnetwork from this dense network itself is a combinatorial optimization and therefore NP hard. So it's not something that can easily formulated as an analytical optimization. So how Jonathan justified this could be right? A very interesting method he introduced. Actually, it may not be easy to understand at first glance, though, called iterative magnitude pruning. It's a very straightforward algorithm running the following steps. Let's first randomly initialize a dense network, okay? No surprise. Second step, training at normal, okay? Get the trend weight and remove the unimportant ones, okay? So far we have done nothing but a common training. Next, keep the current sparse topology and only the topology, and discard all those trend weight you have just harvested from current random training. You need nothing but the sparse topology. What you do instead is to replace those trend weight in the sparse surviving topology with their original random initialization, where they started from, and repeat this step again and again and again until you're happy. So I'm not sure, and after you have done that, so the key difference between this iterative magnitude pruning and the previous classical pruning steps is this resetting weight step. I'm not sure how many people, I'm not sure how many people find this makes sense, and I can offer one of my perspective in understanding this. Essentially, this lottery ticket hypothesis is trying to find a subnetwork with 2 critical conditions. Number 1, it has to be sparse. Number 2, this sparse one has to be trainable from scratch. Finding a sparse network is easy. Finding trainable from scratch is not, because sparsity you can enforce L0, L1 as you like. What does it mean by trainable from scratch? Harder to quantify nor regularize, right? So Jonathan's method, to me, is essentially an ad hoc greedy purse weight method, trying to find this constraint set. Every time, I first try to find a sparse subnetwork, sparser from that one. And then, when I rewind it back, I'm going back to the original initialization that could lead to this sparse subnetwork. And by keeping doing that, I'm identifying a growingly compact subset of initialization that sparsity is naturally satisfied. And meanwhile, this compact subset of random initialization can also be mapped to the most prominent weights after training, iteration after iteration, after rounds after rounds after rounds. So we gradually contract the subset while the weight consistently lead to the most promising trend weight. So I consider this as a heuristic to imply what does it mean by trainable weight from scratch. So this is my version of understanding. You could, well, there may be many different versions of understanding. Okay, but that invites another question. So is anyone so far feeling I'm talking about something stupid? If you feel so, please be honest and raise your hands. Because I can find obvious reasons this looks stupid to you. Well, I have been all bragging about deep network is too big to retrain by iterations. And I want a sparse network to be trainable from scratch. And now I'm telling you lottery tickets is the solution to that. And then I tell you how to find the lottery tickets. You need to retrain the network multiple times in order to find the good sparse topology. So I'm doing that classical chicken and egg game. I'm giving you nothing, right? So how to understand this second question for lottery ticket hypothesis? I think I need to also make, oh, sorry, I'm not familiar with this remote. Okay, so how to understand this dilemma in lottery tickets? Well, what Jonathan, indeed, I think the confusion I just stated is totally legitimate. Because what Jonathan offered in this original paper is not towards a practical goal. I would rather call it an empirical proof of concept that lottery tickets exist. Because finding such a good subnetwork is NP hard. Jonathan is essentially give you some polynomial time solvable ad hoc heuristics that would empirically lead you in a network that behave like this hypothesis predict you. However, so this show you there exists a solution. But the original lottery ticket hypothesis indeed tell you nothing about how this subnetwork could be practical. And please don't make a mistake in that. The original lottery ticket hypothesis is not practical and does not contribute to the goal of sparse training from end to end. That's the context. So I feel those are the two important facts I need to state about lottery tickets. Why it works and what are its limitations. Terminology-wise, after we have repeated this lottery tickets pruning, we get a sparse mask. And that can survive after multiple rounds of training, pruning, resetting, training, pruning, resetting. Resetting is the only extra step here. And we get the sparse mask, and we get its original initialization. They together are called, by convention, winning tickets. And this winning ticket is what we promise to be sparse and training from scratch. Okay, so now we have solved all other questions except the last big, quoting E, big elephant in the room. As long as we have this good sparse network without so much expensive investment. So now, from this point, I'll tell you several things done by my group with our extensive file since I saw that paper. So in the past 3 years, this is one of our research topic, core topic, how to make a lottery ticket practical and how to push sparse training towards the beginning. Let me tell you a few things from this point. First thing, well, sparse mask. If a mask is expensive, I guess everyone sitting here has already experienced at least 3 years in COVID. And I hope you still remember in the early years in COVID, it's quite difficult to get a mask, especially the N95 mask to get. So if you do not have enough masks stored at home, what would you do? Option 1, let's reuse the mask. Okay, we use for day 1, day 2, day 3. Let me quote the same for getting this for how to make a sparse mask affordable. So we have tried. So the same time lottery ticket came out, the other concept also gained popularity called self-supervised pre-training. That's roughly the time when Moko and Sinclair started to gain attention. And when I compare those two concepts together, self-supervised pre-training and the lottery ticket mask fighting, I can see some stunning similarity between the two. What? When you train a pre-trained model, you spend a lot of effort to get that pre-trained model. And then people could use that pre-trained model with ease. People can just fine-tune that with less resource and less data. In comparison, lottery tickets would also need an expensive ticket sparse mask fighting process. But once you have fight that sparse mask, if the next people want to use this mask to train on the dataset, regardless why would anyone want to do that, but if anyone want to retrain again with this mask, then the sparse mask could give efficiency from user 2, user 3. It only make user 1's life a bit heavier. So that stunning similarity between pre-training and lottery ticket fighting have inspired us to do a very natural merge between the two. What if I do lottery ticket hypothesis on pre-trained models? So the idea is, if the pre-trained model is meant to be reusable, sparse mask is also meant to be reusable. How about I put a sparse mask on the pre-trained model to create a sparse pre-trained model? Then everybody, when they fine-tune this pre-trained model, they could just use fine-tune transfer with this sparse version instead of dense version. And then if the pre-trained model could be reused by different downstream data and different tasks, however expensive I have paid towards finding the sparse mask and finding the pre-trained weight would be amortized by the reusability. This is a key insight why we do this. And does it work? Fortunately, yes. We spent a few papers to test this concept in NLP, computer vision, and multimodality pre-training. You don't need to read any of those papers, though. There's only one single take-home message you could remember. Lottery tickets could be seamlessly extended to self-supervised pre-training goals. Actually, supervised pre-training goals as well, for example, ImageNet pre-training, to create sparse pre-trained models. And the sparse pre-trained models could be transferred to different downstream tasks. For example, on computer vision, small code synclair or ImageNet classification pre-trained model, after sparsified, could be transferred to object detection instance segmentation for the same. On NLP, BERT mask language modeling pre-trained lottery tickets could be transferred to all the downstream tasks in Squad, Glue, and even recently we show common sense reasoning. So the transferability of the pre-trained weight with sparse mask is very high. And I would also like to draw a link to what Yi just said. So this sparse structure thing, from our observation, is also way more data dependent than task dependent. It seems to depend heavily on data distribution, but quite reusable on one task to another task defined on the same data distribution. This is our observation. And this also gets some good visibility and including a headline from MIT News. So that's the first thing, reuse. The second one, assume that, okay, all right, I admittedly have a bigger face than my wife. So if my wife wants to use a mask customized for my face, then probably this mask will need to be reshaped, stretched, squeezed a bit. So this is the second opinion I want to offer you. And what is my research question here? The first one, in pre-trained model, we show that sparse mask is potentially transferable, quite transferable, across the data set, across models, across even downstream data set. Basically, the same pre-trained model could be transferred as well when adding a purple lottery ticket sparse mask. But there remains another aspect of transferability. What if I have found a lottery ticket on a small model? How it will help me find another lottery ticket on a bigger model? For example, if my lab's GPU can only afford training a ResNet 18, is there a chance I could use it to smartly find some good ticket for ResNet 152? This is the second question. This is what we call elastic mask, or stretching, squeezing the mask. This started from an empirical study, but end up with some interesting theoretical links, though. So we have studied the question like, okay, so assume I start from ResNet on the top left. Sorry, because this point, well, this laser point wasn't very friendly to me. Okay, So the source ticket, assume I'm starting from a source ResNet. For example, on the top left, the source ticket, consider this to be residue blocks, res block 1, 2, 3, 4 in a ResNet 18 or something, okay? So we have studied, after we have find a lottery tickets in this single network, and assume I have a target network that has twice the depth. For example, from ResNet 18 to ResNet 34. How the two networks' lottery tickets resembles each other? Is there any structural similarity between lottery tickets on a shorter network and a taller network, assuming those two networks come from the same design family? Of course, I'm not going to claim ResNet lottery tickets has similarity with VGG or transformer. That doesn't seem to happen. But if the network has a certain structural similarity, we should expect something. And indeed, we have found that the lottery ticket itself, when the network depths change in the same family, seem to be quite structured and self-repetitive. An example I could give is, if you first find a sparse network, let's say, let's call it mask 1, 2, 3, 4 from this source network. And if you just do a simple, stupid thing, extend this mask from 1, 2, 3, 4 to 1, 1, 2, 2, 3, 3, 4, 4. So you get 8 masks by in situ duplicating them. And this in situ duplicating mask actually have a very strong graph measure similarity. With the lottery ticket mask, you really use IMP to have found in a double depth network. And a direct implication of this finding is you could practically use a small lottery network to find a lottery ticket, and then reuse this found lottery tickets by mindfully transforming them. And the transforming here could be as simple as duplicating, local duplicating. And that local duplicated mask, as we compare extensively on computer vision and NLP task, is performed slightly inferior to the real lottery tickets. I'm going to admit that. For example, on all those figures, the gray line is the real lottery tickets, and this blue line is our transformed lottery tickets, but perform better than all other cheap alternatives that we're aware of in finding lottery tickets, which are those colorful guys below here, okay? So that tells us this lottery ticket transformation indeed find meaningful structures. And if you think about that, think about especially many literatures explain ResNet and many networks as iterative on-roll estimation, which E just told us another one, the iterative estimation. All those layers, if you view them just to be unrolled estimation from solving an optimization problem, then you shouldn't get surprised if those unrolled iterations have a similar learned a similar projection, similar incremental structures. And we feel that's one reason why their sparse structures also tend to be similar. They essentially converge to similar projections and therefore similar sparse masks. So that's our feeling. And we have verified this to even work, which I don't fully understand, on non-ResNet. For example, on VGG, it still works. And in transformer family, sometimes it still works. So that tells us there is perhaps a nested structure in neural networks. Means the sparsity structure itself have low dimensionality as well. The sparsity repeats itself across layers. Sparsity or sparsity, if you call it that way. That's okay. So that's the second answer I could offer you. What if a sparse mask is too expensive? So we could reuse the sparse mask across the dataset and task by putting them into pre-training. We could transform by mask by our model architectures. Okay, and question, please. Mm-hmm.
So how is that? Yeah. So I'll repeat the question. So you said that the lottery ticket hypothesis, it depends on the initialization, and one of the you also have to, once you have a mask, you have to keep the same initialization in order for that to work.
Yeah.
So, and here something that I'm missing is you do not talk at all about initialization when you're extending the mask.
Well, great question. When I extend the mask, when I copy mask, I copy the initialization too.
Okay.
Yeah. So the initialization is often a hidden gem in lottery tickets, indeed. So, and yet I didn't scratch every detail as I want, but indeed, for example, in the pre-trained model, everybody gets the same initialization because they all start from the given pre-trained weight. In the second work, when we copy mask, we always copy the initialization. So yes, when I talk about mask, I almost always use it together with its pair initialization. Otherwise, there will be issue. Yes. Okay. But I also want to make an additional comment. From our observation too, the initialization, and although one initialization would lead to a different initialization would lead to a different sparse mask, but if you use some graph theory measure to look at those masks, they are actually quite similar if you use Laplacian representation. Okay? All right, but that's not in today's slides. All right. So far I have been telling you how to bootstrap ourselves from some smaller models or the pre-trained models, and now let's look at an even bigger elephant in this room. Assume I have nothing. I have to start from the bare ground. I have to do training from scratch. Nothing to borrow. How can sparsity still help? That's a bigger question than transfer, right? For this audience, it shouldn't be necessary for me to say that deep network training is costing a lot of money and it costs a lot of cloud resource. By the way, I know deep network training costing a lot of money, especially after once my student forgot to close the AWS instance for me. And yeah, then I know how expensive that can go. All right, so how training from scratch could benefit from sparsity? Nothing to borrow. Is sparsity still happening? So that will go a bit beyond the classical lottery ticket hypothesis. We just keep observing the experiment. Like a biologist, we just do a lot of observations. We look at the training dynamics, and we found something really interesting. Sparsity's dynamic actually looks very heterogeneous when you look at a different granularity. For example, in pruning, we have unstructured sparsity, which is element level, and structured sparsity, which is typically on channel level. If you look at the dynamics of unstructured sparsity, how each element being zero or non-zero during the training, that looks very chaotic even until the later of that, because that's perhaps too redundant a graph. But if you zoom out and look at the channel level sparsity, for example, I can use an empirical measure by saying that let's compute the total Fourier norm of all the elements in a channel, in every channel of the convolution network. So you would get a channel level node graph, right, of the network. And if I just ad hocly say, okay, whatever channel in this round gets into my top 20% largest all forbiddenness norm across all the channels in my network, I call it my big channel, and other guys are small channel. This big channel versus a small channel distribution, surprisingly, will converge, or let me change our way to say that will be stabilized very early in training. So what I'm trying to tell you is, so what we have see is, in most of network, regardless of, and this is again verified in both convolution network in BERT. So we have one iClear and one ACL paper to say this thing. In the first 15 to 20 of the total epochs, if you don't look at the element-wise importance versus unimportance, but instead look at the structure-wise, the structure-wise importance was actually decided pretty early, in top 15-20% in the total epochs. And they keep stable across the remaining of the training. In other words, before, and remember, in the first 15 to 20 total epochs, usually the accuracy is still at most 60 to 70%. It's not mature. So in other words, you can understand the deep network behaving this way. Deep network itself, the big network, is a program manager. It will get a task, and the first thing it did is divide and conquer. It will first decide, okay, this channel, you do this channel, you do that, and all those channels, the other channels unselected, you are probably not important for this task. So I call this a homework assignment problem. That the deep network will first decide this subnetwork, this substructure will be responsible for what in very early beginning of the training, less than 21st to 20%. And after this decision is made, this assignment is done, all the training process actually become relatively local on the element level. So even when the network only have 60 to 70% of accuracy, actually by that time, the important connection subset, important channel subset already decided. In other words, it's already decided who will do what. This happens early. So based on this observation, with same conjecture, pruning could happen early as well. I mean, channel level pruning. So we propose a so-called early bird phenomenon. And we show that you could train the network for an early number of epochs, stop training, and construct the channel node level graph as I just described. Only keep those channel nodes with high energy and discard those who are not, and then keep training with this early identified important subset. It recovers performance on CNNs, BERT, and VITs. So this is, and I would also like to comment that this phenomenon perhaps has been identified by many relevant, other relevant observations. For example, there was a great paper called Critical Learning Period that shows that there is an early point that a network will be sensitive to permutation and other things, and after that, the network will become more robust. There are several other papers that reveal the important structural formulation period in the early training of network. But in the later, when network enters the so-called convex-like optimization trajectory, it seems pretty robust to perturbation. And we also observe the same. So I think this early bird thing should be all relevant to the observation and showing that some important structure being formed in deep network weight in the early stage. That's my thoughts. Okay. So far I have been bragging to you that the lottery tickets, the original lottery tickets is very expensive. And I'm telling you that there are multiple ways to utilize either transferring knowledge or early emerging phenomena to reduce the price to get you a discount ticket. But do we really need to pay for the ticket? This is my next question. So let me try to ask a more ambitious question. Is there a way for you to get a lottery ticket nearly for free? You find a ticket by not doing anything at all. Before I answer this ambitious call, let me first ask a question. If I ask you to write one line of code to generate me a sparse neural network, what would you do? One line of code. How about just generate me a Bernoulli distribution over the weight and do me a random pruning, right? Simplest thing we can do. Okay, random pruning. Never thought of. Poor kids and family. So if you look at the CVPR papers every year, look at those pruning papers. Most of them will have random pruning poorly placed in the first row of the table and showing that my pruning method can outperform random pruning by 30% on ImageNet. Okay, that's what you would expect, okay? So that's really the poor kid that every fancy pruning method have to first beat before they can publish in CVPR whatsoever. Really. So I'm not trying to argue that random pruning is all the fancy pruning method has nothing meaningful in past development. They are probably still useful in post-training pruning in conventional small models. My argument is instead, random pruning is not necessarily poor if I train a sparse network from scratch. Actually, it can be very strong. We again did it as strong as all the fancy pruning method that you published. What can make it strong? Sorry, again, we did a lot of experiments. And in this paper, a lot of experiments. One thing I liked about this paper is it reports a lot of things that will not work from our experiment. From the 7 or 8 things we have tried, there are only 2 things that we find to consistently work. That is, number 1, when network get larger, random pruning's performance gap with all other fancy pruning methods diminish. So if the network is as big as the universe, random pruning is perhaps as good as anyone. This is the first slogan. bigger network favors random, bigger network do not favor fancy pruning, and random pruning get a chance here. Number two, while I claim you shouldn't pay alien tax, there is still a small fee you want to pay for random pruning. That is layer-wise sparsity distribution. We find this to matter. If you prune network to give uniform sparsity level ratio per layer is a bad idea. We have both theoretical and practical reasons. And instead, we have investigated several statistical distributions, and we find one distribution called the Edison kernel to be practically most useful. Basically, a take-home message, if you don't know this, the take-home message is for larger layers, we will give a higher sparsity ratio. And there is a non-parametric distribution to generate that ratio. Those are only two things we seem to matter. And when the two both conditions are satisfied, you get a big enough cake, and you get a properly designated plate size for each layer sparsity. Here comes the slogan that I'm, in general, very proud of, an empirical result. We empirically show that when you train wide ResNet on ImageNet using random pruning up to the pruning ratio of 50%, which means half of the element being put down to 0 from the very beginning, its accuracy is indistinguishable from a dense wide ResNet from the trained on ImageNet using the same number of epochs. Sparse training equals dense training when network is large. How large? It's not ridiculously large. It's just wide ResNet. But also, wide ResNet is the minimum size I can make it work. ImageNet is also the minimum data set I could make it work. ResNet on ImageNet does not work. I'm going to be honest with you. Wide ResNet will work. So seems network need to be really wide in order to make it this random pruning happen. And when I say random pruning here, I'm always talking about pruning at the initialization. Start from step 0, randomly put 50% of element down to 0 and training from there. No extra step to find alien lucky sparsity mask. And even better for that is, I think for people working on sparsity, no one will get surprised. Sparsity is a very good regularizer for noise, attacks, and the attacks out of distribution. And we find that the sparse network also have superior out of the OOD detection on city quantification, adversary robustness, and net distribution shift robustness on this model as well. All better than the dense wide ResNet. So, and those come with 0 price. So that's how I like it. A random network without West and bells. The algorithm table, as you can see from this part, in that paper is a pathetic 2-line table. But the result was what I like. Okay, so I guess I want to stop at the empirical part here, but give you a few more slogans, what a sparse network can do for you. I have been mostly talking about efficiency. But other than efficiency, sparse network could potentially be win them all gear into all other aspects. For example, we have found that sparsity performing as its traditional regularizer role seems to contribute to more data-efficient learning. We have spent 2 papers to show it to be true empirically for both image generation and recognition. In fact, on the recognition paper recently in Europe, we find simply using appropriate layer-wise sparsity regularizer help us outperform almost everything we know in few-shot learning regime. So we tried on the few-shot benchmark, and the sparsity alone seems to be, I don't want to claim, but it seems to be a good thing that you can need. And also, it helps the sparse model apparently could reduce the storage, and when you try to communicate the models in federated learning, it's a blessing. So we show that a sparse network give you a blessed federated learning as well as in triple AI. And on the data efficient side, that actually get more of my interest. So we are recently starting a collaboration with our university's neuroscience department, and they are now teaching me how to do experiments with monkeys. And we are indeed buying and raising monkeys to do neural constraint theory and observe the multitask sparsity pattern, how sparsity formulation could reduce the number of demonstrations needed for monkey to learn how to acquire things. And a side experience I learned from that is, well, a monkey is way more expensive than a PhD student. That's one thing I learned. Okay, And the sparse also appear to be more robust. We have works that show that on the empirical side, sparse networks are more robust to adversary attacks, more resilient to backdoor attacks, and more sensitive to detect outliers. And if you do a sparse ensemble, that actually all get boosted. Theoretically, we have an IClear paper shows that a sparse network is guaranteed to have higher certified robustness compared to dense ones. So I'll skip over all those, but welcome to check out the details. How many more minutes I have? 15. Okay. 10 minutes theoretical side. So for sparse neural networks, well, we also explored several of its aspects several of its theoretical aspects on generalization, optimization, and transferability. Those are three key questions I'm keen about. I will probably briefly talk about the optimization side. So Sam already did me a favor to introduce NTK this morning, a simplified analytics model for network dynamics when the network has a relatively lazy update. So I'll skip that introduction. So my research question here is, I actually want to eat my own dog food. So look at the empirical result. What I like most and what I'm afraid of the most, both random pruning can perform as well as all other pruning methods. So I don't know, one day I catch a bug from my students' code, so we decided let's prove it and make sure we make no mistake. So we want to theoretically characterize how good a randomly pruned set network could be trained from scratch, how its training behavior and end training loss could be compared with the original unpruned network. So that's motivated by our own empirical results. First, asymptotic case result. It's actually very straightforward. So if you want to skip those theory statement, sorry. If you want to skip all the series, I can tell you that basically means that if the network is the width goes to asymptotic limit, the network is infinitely wide, then pruning has no impact on the network's learning dynamics. I mean, random pruning. That again shouldn't surprise you too much, because if you have infinite amount of weight, infinite amount of neurons to propagate gradient, then okay, then sparsity really doesn't hurt much because you have infinite budget. So the NTK kernel under the infinite width sparsity is just the sparsity ratio power number of layers, L, times the original NTK bond, the original NTK. And if you consider the multiplicative effect will be canceled in the test time NTK, when the two kernels, one over the other, they will be cancel each other. So the actually learned function in the testing time were actually unchanged. So this wasn't anything interesting. A bit more interesting is the asymptotic, non-asymptotic case. So the research question here is, once you fixed a pruning ratio and we do random pruning sticking to our ratio, how wide is called wide enough for me to apply this NTK result? So so we mainly take our inspiration from a renowned paper from Sajeev Arora, Simon Du, and Exagra, other people in Europe's 2019, using your unexact computation with infinite wide neural network. And they have an important theorem show the convergence of NTK at initialization in the finite width. So while at the first glance, to adapt this result to sparsity may seem easy, I actually insist my student to add this sentence to the abstract because we are asked by the review many times. I would argue that it's misleading to think this non-asymptotic proof of a sparse network could be easily adapted from the dense network. And I'll tell you why. Two things. Number one, so there are two important parts in this proof. So number one, in the forward part, you need to prove the feed-forward result concentration using sub-Gaussian concentration. So here you have a Bernoulli mask, and you need to add Bernoulli into new concentration. This is not super challenging, but this needs to be done. But another thing that makes this process actually more non-trivial is the backward process. And if anyone have interest or anyone happen to know this field, that paper by Sajeev and Simon have a key barrier called the Gaussian copy trick in the backward, basically utilizing an important linear algebra fact. That is, if x and y, two variables, are independent from each other, and W is a random Gaussian matrix, then Wx and Wy are also independent of each other. This is a foundation of their proof. And here, x and y are two input layers input, w as weight. So what here we will change? We have not a w, not a Gaussian weight, but instead w Hadamard product, a random mask. So it becomes Gaussian times Bernoulli. And for any matrix that is not generally Gaussian, this linear independence, this Gaussian copy trick, this linear independence no longer hold. So that will break the proof in the middle. So we actually did some other tricks to condition the realization of the mask, first fixed or random. I'm skipping the details, but the result finally will look like this. We can also give a non-asymptotic result on the minimum depth need, but with two important differences. Number one, this depth is inverse quadratic proportionally dependent on the sparsity, which is understandable. That only means that if the sparsity here is the percentage of is a percentage of non-zero element. So if the sparsity is small, means there are many more zeros. That means it needs the network to be wider in a quadratic inverse speed to match the gradient flow. So that's the first thing. Second thing is, in our proof, because of our proof, the construct, we would have an intriguing entanglement between different layers width on the right hand compared to the right end. So the consequence is each layer's width, each of the layers, here H is the index, each layer's width now has to be dependent on all other layers' width in the network. So a consequence of that in practice is, by our series construct, it's unlikely you could strengthen a network by just widening some of its layers, but not widening others. You have to proportionally widening all the layers in order to increase its optimization rate or its optimization performance. Of course, we don't claim this is a tight bound. So there is a chance this can be removed if it's further tightened. But I'm just telling you what we learned, and it seems to align well with our experimental observation. Sparse network seem to be sensitive to sparse ratio for sure, and also seem to be sensitive to the bottleneck. So you cannot have even one narrow layers left behind. If you want to grow wider, grow them wider proportionally. That's a take home. So some other, and this is some empirical result we figure out. Some other series result we will look down. One is how to explain there exists one sparse mask that could transfer across the data set. For the sake of time, I'm skipping that, but this is perhaps interesting for here, for some of the theory people here, because it's use a very unconventional theory tool. We work with the theoretical physics people from UCSB and use a statistical physics model called the Ising model or renormalization group to analyze the sparse neural network. Basically, we consider each of the neuron to be a particle with a spin, particle, and the connection weight between two particles to be our weight. And we show that pruning could be considered as a fixed point status of a multi-particle system when they start to self-group, and that's how Ising model come into place. I would be happy to talk about this afterwards. And we recently also show that there exists a sweet range of pruning ratios that a sparse network guarantee to generalize better than dense network. This is using feature learning proof technique and this result is under label noise. This is a manuscript under work, and I can also discuss individually. Okay, last 5 minutes, I'm going to talk about what are some new prospects of sparsity. I have been talking too much about using zero element of sparsity, unstructured sparsity, and fixed sparsity. But also, I'll claim that this is just a very, very niche subset of all possible sparsity you could play with in your network. For example, that's what I'm trying to say here. Let's do some sparsity that is not your father's sparsity. So first, training. I only briefly talk about the early bird phenomenon to training a network more efficiently. But sparsity indeed is a sharp sword to do scale up training. For example, we have recently, so early bird is one example. And recently we have done other work that show that you could use sparse matrix factorization to support higher order sparsity in networks. That is, you do not need to ask y equal wx. Okay, w is a linear layer. You do not have to ask this w to be sparse, because that's going to be restrictive. Perhaps a better idea is to let w equals S1 times S2 times S3, blah, 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 and each of those S1, S2, S3 is a sparse matrix. This is a sparse matrix factorization, and it can represent Allen-dense matrix with arbitrarily small loss. So we use this idea to introduce a high-order sparsity in training, and we have collaborated with our friends in Microsoft to successfully use this to train GPT-2 from scratch, and it works pretty well. And recently, my student is using this idea to retrain AlphaFold from scratch. So that's something we think can save a lot in both memory and also memory and potentially energy throughput. So another big aspect that I haven't touched today is called dynamic sparsity. As called as you don't just wear one mask during the training. You could keep changing your mask. So that started from a great work by my friend Dekoba in natural communication 2018, and shows that it is possible to use training signals such as a gradient to adjust the mask and activating passes that are deemed more helpful for the training. So you can change that. And that may naturally remind of a recent popular regime many may have heard of, mixture of expert that Google liked it so much. So you could train a multi-column network, each column called an expert, and then a selector to decide for each input you want to use a different expert. That essentially is a very coarse-grained sparsity and dynamic inference, right? So for time's sake, I'm skipping this demo. So we recently have done some work together with Google mixture of expert and show it actually can be generalized to as an efficient design tool for network with even better efficiency accuracy trade-off compared to conventional dynamic sparse training and pruning as well. One last page is very simple, and I guess I'm calling that simultaneously a bad news and a good news, and I like to use it to end this talk. So starting from this summer, I have we have killed almost half of my group's GPUs to try pruning on some models that perhaps no one has seriously tried before. So currently, if you look at deep learning models called pruning, what are the most serious people would do? Okay, someone will do ImageNet pruning, someone will do BERT pruning. That is called serious, okay? And so what we're doing here, so for example, Roberta Large, the Roberta Large model we are pruning, we actually doubled its size. So the model we are dealing with is twice larger than the biggest BERT model in BERT RIPPLE. And the protein data set have 1 billion proteins, and every other data set. So we basically choose some data set that is crazily big. And we also choose some models that are crazily big. And we use those crazily big combinations and benchmark how pruning methods still work on them. Is state-of-the-art pruning method still give us a competitive trade-off on those scaled up models? We have tried a method using weight magnitude, method using gradients, method using some method using Hazen, not all of them. And one thing also calling attention is here, besides the dataset size and the task, we also extend the task difficulty to a new level by introducing multi-step reasoning and very complicated biochemistry prediction. And even in translation, we do multilingual translation rather than single language. So we have assembled a benchmark of the most complicated task, model, and dataset that we could dream of. And on this challenging dataset, guess what I can tell you? Nothing works. That's what I like the most. So nothing works here has two interpretations. Number one, no pruning method evidently prunes better than random pruning on those big enough models. Number two, all those pruning methods can start to fail at relatively moderate pruning ratios. You perhaps already have heard enough. Pruning method can prune a CIFAR model up to 99% sparsity without losing a bit of accuracy. Too many fairy tales you heard about this, right? And now I'm showing you on those models, on some of those benchmarks, pruning 5% of parameters start to deconstruct the accuracy. So I'm not saying that pruning is not working. I'm just saying that I'm trying to convince you sparsity has a lot more work to do. And here is some of them. With that, I'm concluding my talk, and sorry for overkilling the time. Just want to utilize this opportunity to sell some of my excellent students and postdocs, and especially this guy is on faculty market. If you're someone you want to consider them, I would really appreciate it. That's all. Thank you.
Any questions from the audience for Atlas?
On your last slide, you said like pruning doesn't seem to work, right? Not exactly that, but
I have a lot of context for that statement. Yeah, go ahead.
Maybe it is because nowadays we use transformers, and most of the literature on pruning is on CNNs and ordered architectures. So maybe transformers don't like pruning than other architecture. What do you think?
I don't know, but I perhaps don't have a strong argument in support of that. Because on transformers, even on BERT, you can check on SAO and see how many BERT pruning papers people has published. And talking about that, I should give credit that there was, well, some of the BERT-inspired pruning method actually generalized relatively better than others, actually obvious better on this benchmark. For example, I should credit the optimal BERT approach, the O-BERT method, published by Professor Dan Lister's group. And that indeed works better than IMP and some other random pruning method, although still suffers performance decrease at a certain sparsity. So while this seems to challenge every pruning method, and on some benchmarks everything fails, on some other benchmarks there are still successors and survivors, I do want to make this clear. And the paper will come out very soon.
Thank you.
Anyone else? Maybe if there's one more question, we can take that. I think if not, okay. I can just give a quick comment about the theoretical results. We should chat more offline about this, but I just want to plug the result I was talking about this morning over the result you alluded to from Sanjeev Arora and his students. So we have a slightly more updated accounting of the rates there, and you can do much better than what you had on the slide for the width on the depth. So I'd be happy to tell you more about that.
I'm happy to chat, but indeed we are improving the rate now. Yeah, we should chat.
Okay.
Thank you.
Yes. Okay. Let's thank the speaker. Okay, for the final tutorial of the day, we're happy to have Professor Sai Ravishankar visiting from Michigan State University. He's going to close the loop on our talks today and tell us about sparsity, low-dimensional structure for imaging and machine learning. So take it away, Sai, thanks.
Thanks, Sam. So this is the last talk. Am I too loud? Okay. So when we started off earlier in the morning, John Wright was talking about inverse problems and compressed sensing, and that's where we began. And so to top it off, this last talk will take us back to inverse problems and sparsity and connections to deep, and then on to deep learning with a focus on imaging. So just a quick shout out to my group. Many of my members are here who contribute. Some of them contributed to the works in this talk. I'll cover some background in the beginning, and then I'll be talking more about our very recent research for most of the talk. Firstly, starting with supervised learning of sparse models and sort of regularizers in inverse problems, and learning these regularizers in a supervised way. And then I'll move on to learning regularizers with no supervision and with no training data. And then the last part of the talk is going to be going back to supervised learning, but then focusing on building robustness into the learned networks for image reconstruction. So here are a bunch of images from different imaging modalities. There are lots of different imaging modalities out there. MRI, X-ray CT, ultrasound, different kinds of microscopy, to name a few. And in all of these imaging systems, it's often not trivial how you form these images from the data that's collected. So an important goal, sort of in computational imaging, is to form images from the collected measurements of the data, measurements of the images. And these are often indirect measurements rather than direct pixels of images like you observe in your camera. And often the objects you're imaging are not discretized. They are continuous functions. But then for our purposes, when we do image formation, we discretize these images onto pixel grids. And image reconstruction is important in a lot of applications in medical imaging, in material science, in physics applications, in astronomy. For example, the algorithms that went into making images of the black holes that we heard about in the news in the past came from sophisticated image reconstruction algorithms. And typically, these algorithms rely on a model of the imaging process so that you have an image X you're trying to estimate, but you only observe the measurements Y. And a simple measurement model is a linear model connecting the image X and the measurements Y by a measurement operator A. And on top of that, there may be some noise in the process. So the H denotes the noise. So even for a simple linear model of the imaging process, there can be complexities in recovering the image from those measurements Y. So for example, a simple way to reconstruct the image X would be by solving a least squares minimization, where you minimize the difference between Y and AX. AX is the representation from the imaging model of the measurements. And you can solve this least squares problem by using your standard tools, compute a pseudo-inverse or do conjugate gradients. But the challenge is that many image reconstruction problems in the real world are ill-posed, so the solution may not be unique, for example, or they are ill-conditioned so that computing the pseudo-inverse would tend to blow up the noise in your data. So here's an example. So this is a cartoonish setup of CT where you have an X-ray source, and that's emitting X-ray photons, and those pass through the object that you're trying to image, and then it hits a bunch of detectors on the other side. And sometimes the source and detector are rotating around the patient, like it's in common medical CT scanners, or if you're imaging materials, the object may be rotating on a table and so on. But every time a set of measurements are collected or projections are collected, you're basically collecting a set of measurements in this Y vector and corresponding to a set of rows in the operator A, or the measurement matrix. And so depending on how many such views you collect, so from different points in the circle, the source will emit X-rays, and you collect measurements. Depending on how many of those angles or views you collect, you can get reconstructions. If you sort of do the pseudo-inverse reconstruction, which is called filter back projection in CT, then if you have enough views or enough locations of the source from where you collect the measurements, from wherein you get the measurements, then you can get a good reconstruction. But if you have limited data, then the conventional algorithm gives really bad images. And especially if you have 2 views, 4 views, it's very poor. In fact, one of my students will talk later in the poster session of how can you learn something that works for this few views. And another example is MRI, where the data is collected in the Fourier space of the object. So think of this as the object. This is the Fourier transform. And then samples of the Fourier transform are collected. And this is done often in a certain regular manner with a certain sampling trajectory that satisfies Nyquist sampling conditions. And if everything falls in place, you get a good image by computing an inverse Fourier transform of this collected data. But often, this process is very slow. So in MRI, the goal is often to speed up the scan by collecting less data. But if you collect less data, your object may end up being very blurry, or there may be aliasing artifacts if you collect the data incorrectly. And so this kind of led to the field of compressed sensing, where basically you could folks said you can collect data, but in a sort of undersample the frequencies in a certain random way, and then your image reconstructed by simple inverse Fourier transform turns out to be not as terrible. So these methods that just do the pseudo-inverse kind of reconstruction are not as good as we are seeing in cases when you have limited data, or when you have corruptions in your data, or the imaging operator is not well behaved. So in those cases, it's often useful to impose regularization on top of sort of minimizing a least squares loss. So the least squares loss is, in typical imaging systems, you may have, depending on the imaging physics and the measurement noise model, you can have much more complicated data fidelity functions that are not just least squares terms. And then you impose regularization. So sparsity is a kind of regularization that can be imposed to sort of make the problem more tractable. So you can, if you have infinitely many solutions, you would select the sparsest solution. And so that kind of was a big breakthrough in MRI with compressed sensing, that you could collect fewer measurements, sort of randomly sampled in K-space. These are the red dots, the samples that are collected. So you could collect much fewer measurements and then exploit the sparsity of the image in sort of a wavelet space. This is going back to John Wright's talk. He kind of showed a picture similar as well. And exploit that and in regularization, and then you could reconstruct the image from much fewer measurements than you would normally collect. So, however, the reconstruction process now is, with this model-based reconstruction, as I called it in the previous slide, is more complex because you need to solve an optimization problem. And depending on the regularizer, whether it's convex or non-convex, you may have issues of how do you initialize and all of those things. So designing these regularizers, there's been a lot of research in imaging on how you would design the regularizers. And going to the theme of this workshop, sparsity, low dimensionality has played a key role in the design of regularizers for these image reconstruction problems. Sparsity as well as low rankness has been exploited heavily. And a common sparsity model is that we assume there is an operator W, like the wavelet transform, for example, that when applied to your image, sparsifies it. So the L1 norm, as we saw earlier today, is sort of a way to measure sparsity, and it's convex. So you can plug that in as a regularizer, and as long as you know the sparsifying operator, you can solve this optimization using any of the standard tools in convex optimization and kind of get a reconstruction. And more recent works have looked at learning these transforms or dictionaries, and these dictionaries could be, or transforms could be learned from a collection of images, or they could be learned even from noisy data or undersample measurements. So all of that is possible. What we are going to focus on is how can we learn these regularizers in a supervised way. So if I have samples of noisy images and corresponding clean images, can I learn regularizers that, when plugged in to this optimization problem, would give you the best reconstructions? So that kind of leads us to this sort of a supervised way of learning regularizers, where basically I have a training set of noisy images and clean images. XTs are the clean images. And the goal is to find a sparsifying operator, W, such that the reconstruction that's obtained with it, so you solve an optimization problem and get a reconstruction, and you want to find an operator such that this reconstruction is as close to the ground truth as possible in a sort of, say, for example, a mean squared error sense. So if you kind of stare at this problem, you can see that this is not a standard optimization problem. This is a bi-level optimization because the loss function you're optimizing on the top depends on this quantity xt star, which is coming from a different optimization problem. So, so that's kind of, that makes it a bi-level optimization. And there could be additional regularizers, J of W, like W, you could enforce it to be orthogonal. We saw that coming up in earlier talks. Or there could be sparsity in the weights, like Atlas talked about. So how do we solve this sort of bi-level optimization? So if we look at the literature, so the challenge is that we have to, if you take gradients through the upper level loss function, you need to compute gradients of this X star, which is coming from an optimization. So it's not clear how you compute that gradient because it's not a closed form expression for X star, XT star. Now, there are a few approaches that people have adopted. One of them is unrolling. And so basically, you run an algorithm. I think Yima talked about this. So take an algorithm for the optimization problem, say something like ISTA, and unroll it for many iterations. Often cannot be too many, because then you run into memory issues. So unroll it for a few iterations, and then kind of use that as a representation of X star, and kind of learn the weights in this unrolling. So the issue with this is that you cannot often unroll for too many iterations, and you run into vanishing gradients and other issues. And if you run it for unroll for only a finite iterations, then at testing time it can create issues, as I'll show later in my talk. Another approach is sort of replacing something like the non-smooth L1 norm with a smooth relaxation, like the Huber loss. But then this introduces a relaxation, right? So you lose the exact sparsity property. And also we have observed that if you do the smooth relaxations, the performance also suffers. So we want to really solve the bi-level optimization with a non-smooth regularizer. So the way we are going to do this is derive an implicit expression for the solution of the L1 minimization problem. And then we will look into when that implicit solution becomes explicit, and then that will lead us to kind of going into a gradient descent algorithm with an explicit expression. So here's kind of the theorem. And what it's saying is that let's assume we know the solution of the minimization problem, the lower level problem. So if we knew the solution, if we have the transform W, we can compute the sign of this W times X star. And this quantity, this vector S, only has the non-zeros in that sign, so only the plus ones and the negative ones. And W0 and W plus minus denote sort of a subset of the rows of W corresponding to the 0 components of Wx star and the non-zero components of Wx star. So once we compute the submatrices of W and the sign pattern, then we can actually use KKT conditions or Lagrangian dual analysis to derive an expression for X star in this lower level problem. And the right-hand side, the expression depends on the sign pattern and on the submatrices of W. And think about it as, a way to see how you derive this is think about KKT conditions and assume the sign of Wx star is known. If the sign of Wx star is known, then basically the L1 term can be relaxed to a simple linear term. You can think of it as the sign pattern or the sign vector transpose Wx because you know the sign. Then that leads to simplifications from which you can derive a closed form expression. This is an implicit expression and not explicit because the right-hand side depends on X star as well. Because the sign pattern, W0, W plus minus, all depend on the sign of Wx star, which depends on X star. So that's why it's an implicit closed form expression and not an explicit closed form expression. So how do we make this an explicit closed form expression so that we can compute gradients and learn a transform? So here's an example. So consider a scalar denoising problem where everything is scalar. We have a scalar y, which is noisy version of x, and w, our transform, is also a scalar. And if we kind of write out the lower level loss function, we can write the solution explicitly because it's a scalar optimization. And it turns out that in this scalar setting, the x star kind of looks like this triangle, and y here is sort of the noisy signal. And if we look at the sign of wx star in the simple case, the sign of wx star turns out to be piecewise constant. So there are regions where it's +1, -1, +1, or 0. And what that means is that the sign of wx star, so that's what this is, sign of wx star, is piecewise constant. So there are regions where the sign is fixed. And if the sign is constant in those regions, the implicit closed form expression becomes explicit. Because if you fix the sign pattern, everything on the right-hand side is fixed. So it becomes an explicit function of w, and then you can compute gradients of x star with respect to w. So that's kind of the trick. And so if you look at the loss function q of w for this one-dimensional problem, it's not a convex loss. It's not convex. It's not smooth. It has multiple minimizers. Apparently, it turns out those minimizers are kind of equivalent. They have the same loss function, but this is not, we have observed empirically, this is not in general true for this kind of optimization. But the important thing is that the sign pattern is piecewise constant. Another case where we can analytically show the sign pattern's behavior is if your W is orthonormal. If your weight matrix is orthonormal, then basically you can derive a closed form, an explicit closed form expression for xt star, and involving soft thresholding the transform signal and applying the transpose of the operator. And in this case, you can show that on the Stiefel manifold of orthonormal matrices, the sign pattern, the sign of wx star, is piecewise constant. So if you're doing gradient descent on the manifold, then the sign pattern is piecewise constant, and therefore the implicit closed form expression becomes explicit again. And so, but in the most general case, it's hard to kind of show that the sign pattern is piecewise constant, but we have empirically kind of extensively checked that the sign pattern, even in the more general case, tends to be constant in neighborhoods of these transform operators. So once your sign pattern is fixed, then you can basically turn your x star, the formula for xt star, into an explicit expression, and you can compute gradients. So your loss function kind of looks like this. This is the L2 loss, and you can take the gradient, apply chain rule, and take the gradient further through x star, and these are the expressions. So now that we can compute gradients, we can design our algorithm. How do we solve this bi-level optimization? Kind of an exact gradient descent algorithm. So we kind of initialize our transform matrices with the identity, and this turns out to be an important initialization compared to random initialization, which we use in neural networks. We found that the identity is a better initialization, and maybe it's tied to sparsity, so that's something to think about. So basically, for every training pair, we would solve the lower level optimization problem to find x star, and from x star, we can find the sign of wx star. And once we know the sign of wx star, we can compute the gradients, because the sign determines the closed form expression for xt star. And from that, we can compute the gradients and update the transform and process another training pair or a batch of training pairs. All of that is possible. So now let's look at some experiments of how this kind of transform learning works. We looked at denoising 1D signals as well as images. And so these are two kinds of one-dimensional signals. One kind is piecewise constant. So these signals would be sparsifiable ideally by the finite differencing operator. And these are kind of smoothly varying signals that are sparsifiable by the discrete cosine transform. So we kind of had a ground truth transform to work with. And then we learned the transforms from these kinds of signals in a supervised way by, with noise in the process. And you can see that the learned transforms very closely resemble are ideal ones. There are some differences. In fact, those differences lead to a slightly better denoising performance for the learned transforms because they are learned with supervision. So they are learned for the task. And this is for images. We worked with the Urban 100 dataset where there are many different patterns in the data. So we wanted to see if we can learn different kinds of textures and in our filters. And turns out you can. And then we trained on a set of images and we tested on a different set of images. And this is kind of showing the peak signal to noise ratio for different denoising algorithms. BM3D is sort of a canonical benchmark that people have used for a long time. And analysis KSVD is sort of learning this transform operator. This is from Mickey Elad, who is one of our speakers. And so this is learning the transform operator, but without supervision, directly on the noisy data. And BLORC is our scheme, which learns with supervision. And then after you learn, you apply it for denoising. So what we found is that higher noise levels, the supervised scheme works better. Lower noise levels, analysis KSVD is slightly better because it learns features on the data, on the noisy image itself, and if the noise is less, then you can learn the features more reliably. So, and we also looked at how does the transform evolve as you increase the noise. Is there like a phase transition in the behavior of this, of the transform learned in a bi-level way? So what we see is as we increase the noise level in the training data, the transforms is fairly robust to the features are fairly robust to the presence of large amounts of noise. The only thing that changes is the scale of the transform because we kind of removed a regularizer parameter in front of the L1 norm. Instead, the transform itself absorbs the scaling that the regularizer needs, the strength that the regularizer needs. And so, but at some point, basically the features change. So going to very high noise levels, you don't get the finite differencing structure anymore, but it's a different structure that's kind of more appropriate at those high noise levels. So suddenly there's a phase transition in the behavior of the learned filters with this approach. And the last thing is we wanted to compare to some more off-the-shelf solvers for a bi-level optimization problem, like say CVXPy, where we basically computed the gradients with our blocked scheme, which is sort of an exact gradient, and compared it to numerical gradients. And also did the same for CVXPy. PyTorch here is basically we use our closed form expressions and just computed the gradients with PyTorch. And so block kind of gives you better errors in computing the gradient because it's a closed form expression, and it's also slightly faster. So that's kind of the takeaway. And an extension, so everything we talked about here was with a linear model. And something that we are working on is, or we are interested in is, how do you extend this if you have a neural network instead? So if W is a nonlinear operator, then we kind of know that if we have a ReLU network, it's piecewise constant with respect to the input. So using that property, we could still linearize and use our similar analysis even for a nonlinear setting. So that's something for future work. So that's kind of the first segment of my talk. If you have any questions, I'm happy to take before I move on to more deep learning. So the key takeaway is that having kind of more systematic gradients is helpful rather than doing black box optimization with CVXPy. So for these settings where we have sparsity regularizers, we can learn we can derive the algorithms more carefully, and that can be helpful. So our next part of the talk is going to be on learning without supervision. So there's no training data or very limited training data. And we want to learn regularizers involving neural networks. So the setting is, for the application we'll look at is MRI for this part of the talk. Previous part was image denoising or signal denoising. For MRI, basically, we have a measurement operator. And if you're doing something called like multi-coil MRI, you have multiple receiver coils that collect the data. And then so you have, for each coil, you have a corresponding measurement operator and a corresponding set of measurements. And this is sort of the traditional regularized optimization that you would do. Now, so we saw sparsity-based approaches, compressed sensing, and blind compressed sensing is sort of where the parameters of the regularizer are learned while doing the reconstruction. So if you're learning a transform or dictionary, you can learn it from the undersampled data or the noisy data itself. So that's blind compressed sensing. And what we saw just before is sort of learning the same transforms in a supervised way, regularizer in a supervised way. But that was kind of a simple regularizer, right? So we have deep learning that has shown a lot of promise for image reconstruction, MRI, CT, and other applications. Now, but often they require large data sets. So our interest was, can we learn deep priors without any training data? So just from a single image measurements. And this approach is called deep image prior. So basically, a network is learned to predict a reconstruction by just optimizing a data fidelity loss. So if you're doing denoising, the network is trained so that its output fits the noisy image. And that's it. That's the training loss. And once you train this network parameters theta, you pass a fixed input. So the input is typically fixed and randomly chosen through the network, and you get a reconstruction. And you could do the same if you have a more general inverse problem, like for MRI. You can do the same kind of optimization. The key is that the network is learned from the measurements of a single image rather than from a data set. So you have to do this optimization every time you're trying to scan a patient or do something else. But there are challenges with deep image prior. So if you typically the cost is optimized using something like Atom. And the issue is that because you have no training data, there is an overfitting phenomenon that's observed with deep image prior. And because of this overfitting phenomenon, people have proposed various tools to get around it. So what is this overfitting? So if you kind of look at an image denoising problem, so this is kind of a noisy image. I hope you can see the noise. And this is kind of the clean image. So if you focus in the darker regions, I think you can see the noise. So the way deep image prior works is you initialize the network weights randomly, and then you minimize the fidelity between the network output and the noisy image. So as you do the optimization, initially the image output looks like noise. The network output looks like noise. And as you optimize more and more, the network output, the PSNR, the peak signal noise ratio, improves. You get kind of more denoised images. But as you iterate over and over the network optimization, you get really the noisy image in the very end. So that's the overfitting that you get a denoised image at some point, but after some time, it just gives you the noisy image itself. And the same issue comes up if you're doing a more general inverse problem like MRI reconstruction. So you initialize the network randomly, and here we basically undersample the Fourier measurements in K-space. So initially, the network reconstruction looks kind of random because the weights are random, the input is random, the network input is random. But as you optimize the network more and more, you get something that looks reasonable but still very noisy. But as you optimize even more, the PSNR drops and you get something that's very noisy. Basically, what it's doing is it's adding spurious perturbations in the null space of the measurement operator. And there is no control in the DIP training that prevents adding these spurious perturbations in the null space of the operator. So that's one issue with deep image prior. Another issue is spectral bias. I think there's another talk maybe tomorrow by Madhi who may talk about spectral bias. So spectral bias is the property of deep CNNs that they typically learn low frequency image content much more quickly than high frequency image content. And there has been recent analysis with neural tangent kernel analysis to analyze how this happens, and particularly for signal denoising. And so it also affects the performance of deep image prior for other inverse problems like MRI. So here's an example where we undersampled the Fourier space by 4 times. And this is kind of showing the reconstruction with deep image prior of different frequency bands. So reconstruction of the low frequencies, the mid frequencies. So the yellow portion is the frequencies over which you compute the error of the reconstruction. And then high frequencies. What you observe is that the low frequencies are reconstructed very quickly, and then higher the frequencies, that they are reconstructed more slowly. And at the same time, there is also the overfitting phenomenon. If you run more iterations, the errors all go up. So the spectral bias may or may not be a bad thing. So it's in a sense a good thing, because it allows you to capture the low frequencies of the image quickly, and images typically have a lot of low frequencies. So it helps to reconstruct the image quicker than the noise. So in that sense, spectral bias is good. It may be seen as a negative in the sense that you are not reconstructing the high frequencies as quickly as you would like. So these are the issues, and a number of works have tried to address some of these issues with deep image prior. For example, by constraining the architecture of the network, having a lower parameterized neural network to kind of reduce the degrees of freedom during the training, or using additional regularization, or injecting Gaussian noise in the update of the weights, which I think Ima also alluded to, which is sometimes referred to as Langevin dynamics in gradient descent, or by controlling the Lipschitz constant of the convolutional layers of the network. So these have been, these are a kind of a splatter of different techniques that people have used to address the issues with DIP, and these mostly focused on denoising, and the improvements are kind of, there's some improvement, but not significant from using these tricks. So we wanted to improve DIP by careful choice of the network input and regularization. And our motivation was a recent work where basically they showed that you can choose a network input that's almost like the image you want to reconstruct, and then magically, or well, maybe expectedly, DIP works really well in reconstructing the image. But the thing was that there was no clear way in which we weren't clear how they chose such an input, right? So, but the way to think about it is, if you have an image that looks similar to the one you're reconstructing, then all you're training the network to do is to transfer the style of the image to something that's more data consistent, more consistent with the measurements that you have collected. So that's sort of this reference-based deep image prior. And in practice, how do you find this reference? If you have a collection of images and you only have like highly undersampled measurements of a patient that you have scanned, then probably the best you can do is get a reconstruction by some existing algorithm and then compare it to your database to find a reference that's similar. So that's what we did in our experiments. And so here's an example of how this sort of reference-based deep image prior works. So this is sort of the vanilla DIP, deep image prior. And clearly it has artifacts that we couldn't get rid of. And we chose a reference. This is from the FastMRI dataset. We chose a reference that's somewhat similar to the image we are reconstructing. And when we learned the weights in the network with this input, it gave a pretty consistent reconstruction. So compared to the ground truth, it's a lot closer. And the choice of this reference has some effect. So if you chose the reference less carefully, then the PSNR, the peak signal to noise ratio, drops somewhat. So this kind of seems promising. The other thing was we still don't have any regularization. So what we wanted to introduce was additional regularization, but that's something that could alleviate spectral bias. So we chose our regularization so that it's looking at consistency of the Fourier space of the reconstructions with respect to the references that we have on hand, but only at the high frequencies, or only at the complement of the frequencies that were sampled. Typically, the sampling has more low frequencies in K-space, so if you look at the complement of the sampling mask, it will cover more high frequencies. So we thought this is a way to maybe give more preference to higher frequencies in the regularization. So here's kind of the results with these methods, comparing the overfitting spectral bias behavior of vanilla DIP, and then these two other methods. One is using a reference image as input, and the other is with this additional regularization that we introduced in the previous slide. So with these reference-based methods, there's a clear difference in terms of the performance. The reference-based methods perform a lot better because you have some information that you're exploiting compared to the vanilla DIP. And so the overfitting still happens, but it's a little slower and more benign. And if you look at the reconstruction of the low frequencies and the high frequencies, the behavior is, the plots are more benign for these reference-based methods. So the challenge here is that we still assume that we have access to some references, whereas the original deep image prior was designed to work with no training data. So how do we kind of design a robust deep image prior scheme that uses no training data? So that brings us to our what we call self-guided DIP or self-supervised or whatever you'd like to call it, and where basically instead of assuming a known input or reference that goes into your network, we optimize the input along with the network weights. But this has to be done a little carefully. If you just blindly optimize the network input and the network weights, we observed it doesn't work as well. So we had to kind of use our observations from working with references so that if you look at how it works with the reference is somehow related to the ground truth. So you can think of it as a perturbed version of the image you're reconstructing. And somehow the network is able to remove that perturbation at its output. So if we think of that as some kind of denoising, then basically training the network to act as a denoiser by introducing, having some perturbations, that is key when you're trying to optimize the network input along with the network weights. But the thing is, we don't have a reference here, and we don't know what is that perturbation. So we basically ended up sampling these perturbations eta from a distribution. And this could be, we didn't see any particular preference for a distribution for those perturbations. But what you can sample from those, the perturbations from a distribution. And then we also introduced a smoothing in the end. So you can smooth the network output over different initializations of these perturbations because you don't know what is the right perturbation. And that's kind of also inspired by recent techniques in classification called randomized smoothing, where if you have a classifier that was just trained as it is, if you introduce adversarial perturbations, then the classifier is known to can fail. But randomized smoothing tends to smooth the classifier so that random perturbations or small perturbations do not change the output drastically. So that's coming from the classification literature. And so you can see the output here as sort of a randomized smooth network output. But it's important that we have this sort of denoiser regularization for this method to work. So this is kind of showing the effect of this denoiser regularization. So if you did not have that regularizer, so we just optimized the network input and weights, and we did not have a denoising kind of regularization, then the performance drops quite a bit compared to when you have this regularization. So these are sort of the ingredients that go into our self-guided deep image prior scheme. And so we tested these methods or these improved versions of deep image prior on the fast MRI multi-coil knee dataset. And we worked with sort of a supervised, well, we also compared with a supervised network. So we had to do that to see if these schemes can beat a supervised network trained with many images. So here are the results. Actually, we chose a pretty over-parameterized network, and we found that that was necessary for it to work. And so here we are comparing performance for MRI reconstruction at two different accelerations, 4-fold undersampling and 8-fold undersampling, comparing the reference-based methods and the self-guided DIP with the supervised method and the regular vanilla DIP. So all of the proposed methods outperform vanilla DIP, often by several decibels. So there's a clear improvement in performance over vanilla DIP. But the interesting finding was that the self-guided DIP, which learns completely with no training data, adaptive to the image or to the measurements themselves, performs the best. So that is very promising that as long as we do the deep image prior setup in a nuanced way, that it can give very promising performance, and performance that even beats the supervised scheme that was trained with with a larger data set. And so this is sort of visuals comparing the different versions of deep image prior, the reference-based schemes or the self-guided scheme with the supervised network. And I'm not sure if it's clear, but this, the supervised network tends to produce some over-smoothing in the zoom-ins, and the self-guided scheme kind of seem to alleviate that effect. And again, these are the PSNR plots and the errors in different frequency bands, low frequency, high frequency. Vanilla DIP has the characteristic overfitting, and the self-guided or reference-guided schemes don't. The self-guided scheme, the PSNR seems to keep continuing to increase. Like, does it just continue to increase? And no, no, it doesn't. So at some point, it also overfits. There is also overfitting with the self-guided scheme. It's just that it takes more iterations, so it's slower to run. So that's that wraps up the second portion of my talk on how we can learn neural network regularizers with no training data, basically, for imaging. So if there are any questions, I'm happy to take before going to the last part on building deep networks that are robust. Yes.
Yeah, thank you. So you said you are not sure what was the initialization for deep image prior?
No, no, no. The original deep image prior uses a random input and also random initialization.
Yeah, that's true.
Right. So that's what we used for when we compare to the original deep image prior.
Yeah, thank you. That's true.
Yes.
Yeah, so sorry, a quick question. I'm just curious, just correcting if I'm wrong, right? Because when you talk about DIP, one of the issues is that really is unclear what is the optimal number of iteration, right? And this self-supervised DIP still doesn't solve that problem, or can I say that?
It doesn't resolve overfitting.
Okay.
It kind of has a more gentle behavior.
Alleviate that kind of things a little bit, right? Okay.
Yes.
I see. Thank you.
So there are a few things, right? One is overfitting, one is performance, because having no training data, how do you get really good performance? The last thing was spectral bias. So in terms of performance and overfitting, there is some benefit with sort of this the proposed schemes compared to the regular DIP. And the fact that it's doing better than a supervised network is quite promising. So we are working on trying to extend some of the NTK analysis to these other DIP methods, but that's kind of in the works, and hopefully we'll have something in the future. So for the last part of the talk, this is going to be back to supervised learning, but now with deep neural networks. So with deep learning, there are multiple ways in which you can use deep learning for image reconstruction. One category of methods is called image domain learning, where basically from the sensor data that's collected, we would perform an analytical reconstruction. Think of this as a pseudo-inverse applied to the measurements. And you get a sort of a corrupted image, and then a network is learned to denoise this image in a supervised way. So that's called image domain learning. You can, and so that's a sensor domain network. And then you perform a simple analytic reconstruction, assuming the data is now perfect. The analytical reconstruction works very well. Another approach is AutoMap, which kind of removes the analytic reconstruction step in between and just goes directly from the measurements to the image. And this method requires a fully connected layer in between, or there have been some tweaks of that. So that kind of consumes a lot of memory and computation. The methods that are very popular are these hybrid domain learning methods, where basically there's a neural network, but the neural network is also combined with the forward model or the measurement operator that, or the known physics of the imaging system. So trying to use some known priors about how the imaging measurements are collected together with using networks in the reconstruction process. So this is an example of such a hybrid domain learning method called MODL, or model-based deep learning, where basically the method tries to solve this optimization. So there's a least squares data fidelity term and a regularizer. This regularizer is just trying to just trying to have a network that auto encodes the image. So this is an auto encoding kind of regularizer. And so this reconstruction depends on the weights of this network d theta. So what is done in MODL is an alternating minimization is adopted for this minimization, where basically you kind of introduce a pseudo variable z, which is the output of the network. So you alternate between updating the z and then fixing the z and updating x, which turns out to be just a least squares problem. And so the updating of z turns out to be like a denoising process. So that's the step where the x is fixed and it's passed through this network, and the network serves to denoise the image. And then the next step, the network output is fixed. So this quantity is fixed, and then this loss function is solved with respect to x using conjugate gradients, and that's this data consistency step. And this process is unrolled for several iterations. And then the network is trained end to end with supervision. So this is using sort of the unrolling approach instead of using bi-level optimization like I talked about in the first part of my talk, which would be the more nuanced way of learning a regularizer rather than with the unrolling. So we'll see quickly what happens because of doing this unrolling. So this is the output of MODL with where the k-space was undersampled by four times. So it's a quarter the data that was collected, and then the reconstruction was performed. And the network was learned with supervision. And what we found is that if we introduce even tiny perturbations in the input to the network, the output can basically collapse. That the tiny input adversarial perturbations can basically destroy the output. And there are other kinds of perturbations to which the network is unstable. For example, if you change the sampling rate, so instead of collecting 4-fold undersampled data, if you collected 2-fold undersampled data, or so you're collecting twice more data, then the network just fails. Or when you're doing the unrolling, instead of unrolling for 8 iterations of the alternating optimization, if you unroll for 16 iterations at testing time, again, it fails. So the unrolled deep network is really unstable to a variety of perturbations. And so the question was, how do we alleviate this lack of robustness in the deep network reconstruction? Right. So, and I mentioned adversarial perturbations, and you might be wondering how is that related to image reconstruction, because the most common scenario you might have heard about it is for image classification. In fact, I think there's a talk tomorrow about it. So in the image reconstruction setting, think of the imaging measurements that you obtain, and those measurements go into a reconstructor. So if you may be able to find perturbations of those measurements that would basically cause the reconstruction to diverge from the target image. And those kinds of perturbations would be adversarial perturbations. They could be really small perturbations, but if they're adversarially chosen, they can cause your reconstructor to fail. Another question would be like, well, these adversarial perturbations or adversarial attacks may make sense for classification because there may be an attacker trying to fool your network. But if you're in an MRI scanner, nobody's going to attack you, right? So, but you know, it's sort of it's not the fact that it's an adversarial perturbation, but the reconstructor could fail even with small perturbations. That's concerning. So for classification, many methods have been proposed to address the lack of robustness of deep neural networks. But these approaches are much less developed for image reconstruction for inverse problems. So in sort of our work, we proposed a way to make a deep unrolled network more robust by integrating this technique called randomized smoothing, which I alluded to in the second portion of the talk. So randomized smoothing, so this is sort of what we would call as end-to-end randomized smoothing, where basically X is the input to a reconstruction network, and F denotes the unrolled network like MODL, or it could be any deep neural network. And so typically we would just pass the input through the network and get the output, that's our reconstruction. But with randomized smoothing, what would be done is you perturb the input to the network by some perturbation nu that's drawn from a distribution, and you average the output of the network over this distribution. Or basically, this leads to a reconstruct that's a smooth reconstructor. It's basically trained to handle all these perturbations. And this is a trick that's been used for classification, but recently there's also interest in doing this for image reconstruction. So an end-to-end randomized smoothing process would basically take the MODL network, which is unrolled for several iterations, and then pass a sort of perturbed inputs to this network, and then average the outputs that come at the output of the network. So, but it's not clear if this is the way to do randomized smoothing. The question in your mind should be, what are the components of the network that are robust? What are the components of my reconstruction network that are not robust? Let's try to understand that first, and then we can see which components we need to make robust. So that was kind of our research question. That is, where should this randomized smoothing kind of robustifying operation be introduced in a deep unrolled network architecture? And then how do you train the network in the presence of this randomized smoothing? So for the first question, our choices were kind of obvious. We are kind of unrolling this alternating optimization with a denoiser and data consistency many times. So we just looked at end-to-end smoothing, which is smoothing at the output of the network. We could introduce smoothing at every iteration of MODL. That's an option. That is, after every denoising block and data consistency, you could do an averaging so that you introduce noise here at every block, and then you average the outputs after these two, basically an iteration. That's one option. Another option is to do this only for the denoiser, because the data consistency block that's basically a physics-based block, right? There's no neural network in there. So an alternative would be that have it only in the denoising block. So those were the two options that we considered, and then the question is, how do you train the network with this sort of randomized smoothing operation built into it? So what we adopted was sort of a more common approach now in computer vision, which is pre-training and fine-tuning. And so the pre-training we did was basically take the network in MODL and train it to be a denoiser, just a denoiser. So basically you have a set of images that you can simulate noise, add it to these images, and then train the network to be a denoiser. And then once you have this pre-trained network, you can fine-tune the weights. And so the fine-tuning loss has two portions. One is a typical supervised loss. Basically, you have this network with the randomized smoothing built into the network. And so you look at the output of this randomized smoothed MODL and compare it to sort of your target or ground truth and minimize the error. And that's basically supervised loss. And then we also had this important additional term, which is an unrolled stability loss. So basically, at every iteration of MODL, we are passing perturbed inputs. So xn is the output of MODL at the nth iteration, and we add some perturbations nu or noise, and we pass, and then we sort of do an averaging of those, right? So what we did was we want the output of the network with these perturbed inputs to match the output when the target or ground truth is passed through the network, because we are trying to train the network to be an autoencoder. So that these perturbed network inputs should match what you would get if it were an autoencoder, which is sort of the image, the target passed through the network itself. So this we call kind of the unrolled stability loss, and we had both of these components to kind of fine-tune the weights of our network once we pre-trained it. So basically, we tested out our smooth unrolling scheme on the fast MRI dataset, and we tested it with a variety of perturbations. So one was with sort of an adversarially chosen perturbation. So that's sort of the what's here as robust accuracy, where we basically, for every testing case, we've chosen we chose a small perturbation, but adversarially chosen. And then we also tried more realistic perturbations, just Gaussian noise or random noise added to the inputs of the network. So what we found was that compared to vanilla MODL, which is not trained to be robust, which doesn't have this randomized smoothing, the randomized smoothing based methods, so this is the end-to-end smooth network. This is SMUG, which is our scheme, but with this is the smoothing is done after every iteration. And this is smoothing that's done only at the output of the denoising network. So what we found is that the SMUG, with just the smoothing done for the network output, is a lot more robust in the presence of both random noise as well as adversarially chosen noise compared to all the other methods. So there is a level of robustness that comes in with incorporating randomized smoothing. And this is kind of showing plots behavior of our algorithms with different kinds of perturbations. So here we are just adding the perturbations or these noise perturbations to the input of the network and increasing the strength of those perturbations. So as you increase the strength of the perturbations, basically the regular vanilla MODL fails, and even the end-to-end randomized smoothing fails. But if you incorporate randomized smoothing in a more systematic way inside the unrolled architecture, that seems to give you more robustness than these other methods. The second plot is basically looking at what happens if you change the sampling rate at testing time compared to training time. And again, we found that with SMUG, the image reconstruction is quite robust when you change the sampling rate compared to the other methods, vanilla MODL or even the end-to-end randomized smoothing. And this is showing what happens if you train with 8 iterations of MODL and then at testing time, you unroll for many more iterations, right? So the vanilla MODL is known to fail when this is done. Basically, if you just unroll for a few iterations and train the network, it doesn't work if you run the whole optimization for many iterations at testing time. It just, so that the PSNR just drops. But if you introduce the randomized smoothing into the process, the reconstructions are relatively stable, even if you run for enough iterations. So, although the network was not trained to be robust to these perturbations explicitly, just introducing the randomized smoothing into the unrolled architecture provides automatically a level of robustness against a variety of perturbations. So here is sort of a visualization where this is the ground truth, and we had perturbations in the input. With vanilla MODL, you can clearly see artifacts arising in the output because the network fails in the presence of the perturbations. And this is with end-to-end randomized smoothing, which seems to alleviate a little bit the artifacts, but they're still there. And then with the proposed SMUG approach, you see pretty much the artifacts have cleared up. So it's more robust to perturbations. And these could be not just perturbations, these could also be distribution shifts between the training and testing data that one would need robustness for. And I think tomorrow one of the talks is, I think by Dr. Heckel is handling this. He's going to be talking about this issue of distribution shift. So that's pretty much it for the talk. So to summarize, I started off with talking about learning sparsity regularizers for inverse problems in sort of a bi-level optimization framework. And so I kind of said that this is a more preferred approach than kind of doing unrolling or other relaxations for learning regularizers. And then we switched on to learning deep neural network-based regularizers and with no training data. And then we switched back to doing supervised learning of networks, but then we looked at how do you make the supervised learning more robust to different perturbations or changes in the experimental settings that would be crucial for things to work for imaging applications. And there are a number of different future directions possible, NTK analysis for our deep image prior schemes, analyzing the robustness of the SMUG approach more theoretically and so on. So these are directions that we hope to continue to work on. And I would like to acknowledge our NSF grant with Ching and the ARS Foundation for the medical imaging support. And that's it. Thank you. happy to take any further questions. Yes.
So I want to ask again about initialization. Did you try random initialization?
For which method?
For the MRI.
Random initialization of network weights?
Yes. No, the latent space.
Random initialization of the... Well, we typically started with random initialization for the network weights for the, if you're talking about the input, that depending on DIP, or we had different choices for the network input.
Okay. So you didn't try random input?
We did. So okay. For the, what I call vanilla DIP uses a random input to the network.
So which one is better, the random one or the one that you have an image?
Yeah, it's the other one. So if you have an image, whether it's a carefully selected image, a reference, or if it's self-guided, if it's optimized, the image is optimized, both of those seem to do better than assuming a random input to the network.
Okay, thank you.
In a sense, when you have the reference, it kind of makes the problem a little easier because the network knows something about what the image looks like, and it's just trying to learn what's new that's sort of consistent with the data that's collected. That's a way to think about it. Any other questions? If not, it's the end of the day, so I'm sure all of you are looking forward to your dinner, so hope you have a good dinner. Thank you.
Thanks again, everyone, for attending the tutorials today. I think just 2 quick announcements. We'll be tomorrow in the main hall 1, down towards the end entrance, for regular talks from the speakers and an opening early in the morning. You can check the schedule online. And if you're presenting your poster tomorrow, we will put up online some poster board number allocations for what's already been posted on the website. And you can come in as early as you like and set your posters up in the morning. So thanks again. See you tomorrow.